ఏదో ఒక 2 థింగ్స్ తెప్పిస్తే కాదు సార్.
Good morning to you all. Welcome to the Atal FTP. Dear participants, we have completed 2 days. So the day one, the Dr. D. Ravindra Garu explained the civil and mechanical aspects of a agri PV systems in the first session. After that, the article discussion number one completed. The afternoon session, Sir discussed the inverters, the different types of inverters used for agri PV systems. So the Sir explained the beautiful way the concept of inverters, different types of inverters usable for agri PV systems as well as other applications. So after that, that is a 4 to 5. The second article, that is second article is discussed. So the second day, that is Dr. L.N. Sastri Garu took the two sessions, the session number one and session number two. So the sir also explained in the beautiful way, and then so in the yesterday we discussed the two articles, which is related to the agri PV stations in the Maharashtra state and Maharashtra state. So all of you try to complete the article discussions reports. So we created the mail. So all of you try to send the reports to the mail so that we can send to these reports to the AST. That is one thing. So the every day we are sending the feedback link. So you need to fill the feedback daily basis. So the next one is we are placing the quizzes also we are placing. So try to complete these three activities are you have to complete all the three activities on a daily basis, because the sessions are starts from 9 o'clock to 5 o'clock. So therefore it is very difficult to complete all the things. So that try to spend some time so that after 5 o'clock, so that you can complete the this workshop successfully. That is a thing. So the next one is the dear participants, do you have any accommodation issues? So the co-coordinator Mr. Nagaraj Gar is available. So yeah, his house is also very near to the college, so you can contact. So I think first day we faced some problems, so we solved all the problems. Even in the first day, some issues related to the internet connection. After that, after 1 hour, we rectified the problems and we solved all the problems. So, you should feel like your house here. So we made the all the arrangements in such a way that so you should feel so this is like your home. So that is a thing. Everything that is food and tea, snacks, everything is completed. So that if you have any issues, so the please try to inform to the Mr. Nagaraj Garu and myself. So the Nagaraj sir is always available here, walk up to 10 o'clock to solve various problems. So today we have a beautiful sessions by Dr. V. Sandeep Garu, so from NIT AP. So sir is a very experienced person, and we are very closely associated with Dr. V. Sandeep Garu. So the sir given lot of support to this institute, especially electrical department. So we are very thankful to the sir. So the sir published various various papers, research papers related to electrical vehicles and yeah, power systems. This sir is a very expert in various aspects of electrical systems. So sir also conducted so various IEEE meetings and various programs for the students as the faculty. So, always I wish to attend the SAR IEEE meetings conducted with the SAR. So the lot of information. Okay, we can get the lot of information for the SAR presentations. So today we have two sessions. Two sessions in the. So here is a small adjustment today. So there is article discussions 12 to 1 and 4 to 5 actual schedule. So that there is small modifications in the schedule. So the SAR will take sessions continuously. That is which starts from so the morning session one session after 12 o'clock also 12 to 1, we are not discussing the article discussion. After we are shifting the afternoon session. So please note that. So I already distributed all the articles. So the article number 1 today, that is a current status of agri voltaic systems and their benefits to the energy, food, environment, and the economy and society. This is article discussion number 1. So the next article discussion 2, the case study on power generation from the agri-voltaic systems in India. So these two papers will be discussed afternoon session, that is 3 o'clock to 5 o'clock. So these are the small adjustments. So the as usual the break will be given 1 o'clock. So 1 o'clock to 1:30. So after that the second section starts again 1:30 to 3 p.m. For the 3 p.m. to 4 p.m. That is article discussion number 1. 4 to 5 article discussion number 2. Okay, so these are the all of you try to note these points. So now coming to the today's thing. So we are very privileged to have a Dr. V. Sandeep Garu from NIT AP as our speaker. So these sessions have very highly interactive and extremely useful. Sir has an impressive record, having published a significant number of research papers in the reputed journals and conferences. Now I would like to invite Dr. K. Rajni, head of the department, to share few words about Dr. V. Sandeep sir.
Good morning to one and all. So myself, Dr. K. Rajni, HOD Triply. Today's resource person, Dr. U. Sandeep Kumar sir. He is from NIT AP and he is a very good academician and researcher. So all of you utilize this opportunity to grab the knowledge and use that knowledge to train your students as per the current technologies. Thank you. Sir, please.
Sir, please, sir.
Yeah.
Now, so the sir will speak about the today's two sessions briefly. After that, the first session will start.
Yeah. Thank you very much, the organizers, particularly Department of Electrical Engineering, Fitna and Lara Institute of Technology, and I'm glad to be part of this FDP program. And very innovative topic on agriculture, PV systems, and electric vehicles, and it's a pioneering sustainable energy and transportation solution. Today, mainly I'm going to take two sessions actually. So one on this opportunities and challenges for agri PV systems, and second one afternoon session that is on key performance indicators for the agri PV systems actually. And this is a very innovative topics actually, very very close to the electrical engineering domain, particularly PV solar systems actually. And we'll see now today's session, how the agri PV systems are emerging, and what is the Indian scenario, how it is suitable to Indian context also. Like that, we will see some kind of opportunities. Okay, so thank you. So we'll start the presentation. We'll continue. Okay, thank you. So if any questions in between, you can ask, or we can discuss at the end also. We'll see. Yeah. Just. Another point. Some other point. Yeah. No. Yeah. So this is the outline of my presentation. So one is, first of all, we'll see introduction to energy demand, and because this is very close to this topic, because we are talking about in agriculture, what kind of an energy requirement is there, and overall, and whether we are I mean suitable to accommodate these kind of new technologies into our one of the main application of agriculture. We'll see that. And next is development in solar energy system. And before integrating with agriculture, let us understand some kind of uh, developments in solar. That's what I'm trying to do that today. And next is sustainable goals achieved by the agri PV system and what kind of developments has happened so far. And particularly in this, what are the challenges with the agri PV systems and opportunities with the agri PV system. And finally, we'll make a conclusion with the summary. And we'll session is open for interaction with the question and answer session. So this is how the presentation is now made today. Now we will have some kind of expectation. Generally, the students or faculty. So they will look for new content of knowledge from any FDP program. You can also search for some project ideas and then explore for new directions for future research. Also, you can also take some kind of help for current research and improvement. And also, you can know about publication and research. And finally, it's a great opportunity for all of us, to linkage, have a connection with domain experts. And it's inspired by a lot of global development, teacher continuous learning and experience now. Now look at some of the kind of as electrical engineers how we can contribute to different sectors and all, so including our own core engineering. Generally, we design and develop new technologies to generate, store, and transmit, control, and convert energy input. But nowadays, actually, we are also dealing with information data communication. That is bringing the interdisciplinary into electrical engineering. Now look at this kind of, this is a framework actually you can apply to agri PV systems also. So where we can try to generate the power, this land of farming, and at the same time we can also store the energy into there also. That is also possible. And of course we can able to control and convert also. There it is if at all any applications are there. So mostly we don't depend on transmission there. So that is not required because that is comes under directly decentralized power generation. And now, what is the fundamental route in identification new technologies now? So one is we can see what is the current state of our state of art of current state of that particular technology. Then we'll try to identify what are the problems in existing technologies in market, and finally we'll see what are the future developments. So this way, if you follow this three-step model, then every project will be innovative. So that's what the meaning here. Look at this. This is what the electrical engineer. We see that generation, transmission, distribution, generation, and we every stage we come up with some kind of innovative or emerging technologies all the time. And now we can see the utilization point of view. Now we can bring some of the application where solar can be integrated with the agriculture application also. So that is one thing here that we are trying to discuss. And at the same time, now people are focusing to include these kind of emerging technologies with microgrids or smart grid electric vehicles, like for example using IoT, machine learning, and artificial intelligence, big data, and blockchain and data science and cyber physical system. And now you can see there the technology sometimes we need to synergize the technologies because the application requires beyond the core engineering principles actually. So maybe if you want to communicate or the user with or any vendor or a utility, so definitely we need to depend on these information technologies and all. So that's how the technologies are now coming together actually, and then they will come to with so a lot of innovative products. And right now we are into industry 4.0 cyber physical system actually. So now even with these cyber physical systems also can be applied for the agriculture applications also. So that is very interesting to know about it. Now this is what the evaluation of energy systems now. So we'll see that now we already understand this applications of power systems and very well. And now see the developments of the smart grid now. So how the smart grids are evolving, and then India also now they are coming with a lot of improvements with particularly the smart meters. And next is cyber physical systems energy, and also we can bring the social layer also here because social layer is very much important where we are users and utility from the utility point. We are trying to take the decisions actually. So that kind of inclusion also is required, much required here. Now these are the fundamental areas where we are working as electrical engineers now. So where we work with renewable energy, power electronics, drives, electric machines, and smart grids, DC grids, energy storage, etc. So like, and we'll see particularly, these technologies, I mean, areas can be again mapped to particular application. Now look at, now we are going to talk about mainly today. So how the renewable energy technologies will be suitable for agriculture application and all. And now energy demand is increasing, and the particularly the agriculture sector also now they are not able to completely rely on these grid connected supply also, because that is not really, we cannot guarantee that 24 by 7 utility companies will supply to that. And government also is trying to plan some particular schedule to them actually to avoid the peak demand and all. So in such kind of situations, and in view of this future demand, so how the renewable energy technologies will help to this kind of agriculture sector and all, we'll discuss today. And this is what one of the statistics from IEA. So we can compare the statistics from 2015, what we already had, and then 2040. So our Indian global demand is going to be much more than double when compared to the previous year actually. And in you can compare with other countries also, energy demand is increasing. And to meet this energy demand, now one sustainable solution is so to go with renewable energy sector now. So in this renewable energy sector now we can have, these are the countries seriously working towards that actually. And by 2022 itself, we are standing in third place even now also actually. So in the expansion of renewable energy, so China is standing in first place, and then next is USA, and then so India. So right. And based on renewable energy, we have two options here. So one is we can have the power generation using grid connected. So another is off grid power generation actually. So now here so off-grid power generation now, so where we can much suitable for agriculture application here. So of course, if at all many large farming is there where we can have, if you have excess energy, that can be also connected to grid also. So that it can by kind of an arrangement also can be done with agriculture application here. And by 2017 itself, we achieved 25% right now. So we are 42% of global energy, renewable energy production that is happened through renewable energy. This was the expansion of the global renewable energy. It's doing well actually. So all the regions, and consumption also, as consumption wise also in future we are going to be standing as a larger consumer in the world. So that's good. That is positive, but still we have to how we can meet that kind of challenge. And variable power generation, particularly using solar and wind. So today, if we talk about the solar, it's solar and wind both are intermediate nature. So how we can meet this energy demand using this variable power generation, that we are. And why we are emphasizing with solar and wind or any renewable energy sources, because we have some kind of background that is happened. So that kind of analysis already did by IEA, International Energy Agency 2012. So they made some kind of a perspective with reference to the 2050 scenario. So indeed, they come up with three scenarios. One is 6 degrees, 2 degrees higher, and where we come up with the base case scenario. If you are continuing with the renewable energy, power generation using the fossil fuel, then our global mean temperature will rise by the 6 degrees. And whereas if you go with alternative scenarios, maybe carbon capture method, nuclear and all, then we can mitigate the global temperature rise to 2 degrees. But if you go with third option, actually definitely with a more sustainable and renewable energy production, then we can reduce even less than 2 degrees. And we can have comparison of statistics also, where so we see what is the advantage going with the renewable energies. Renewable energy, how we can try to help to mitigate the CO2 emissions also. So that is a scenario is also already developed by International Energy Agency. And our aim is now to achieve 50% energy reduction, reduction in energy related CO2s by 2050. So we emit CO2s with lot of other sectors actually, transportation sectors, industry sector. But now, so we are aiming to reduce the CO2 emissions in energy related, energy production sector by 2050 to the 50%. So this is way to be given to all the countries. Now we are also working on. So we now each sector now where we are trying to produce energy. So one of the good example now this today we are discussing, that is agriculture sector. So where agriculture certainly required the energy, the energy supply is required there. and how we can now make it that agriculture sector is independent from the grid utility, and then how we can make our own energy generation using solar. So that kind of self generation that we can do, and then we can contribute to CO2 reduction also. And at the same time, in the grid also we have new loads are coming. So in terms of electric vehicles and that. So now we will see that whether this our grid system, its current system, is able to stay unstable with new loads inclusive or not. So that's another topic to discuss. Yeah. So right now we have, this is the installed capacity in India actually. So by last May, we can see India close to 445 gigawatt of energy installed in India, and every month we are adding easily 1 megawatt, we are adding it actually. So that's a good sign actually. So now we can see that renewable energy itself, we have achieved this nearly close to 1 lakh 50. So 1 lakh 50 thousand of megawatt of energy we install it. So in terms of percentage, we can see there directly more than 30%, 33% of energy. So right now is installed through renewable energy. That means so in India 1/3 of energy is coming from renewable energy right now. Actually, there's good sign to improve that. And other side, actually, we can see that the power installed by the different sectors like central government and state government, private sector. So right now you can see that private sector is owning so 52% the actual power by the private sector, whereas central government companies like NTPC and other agencies, they are producing 25%, and state government is another 24%. So slowly you can see that more private players also coming into this power generation in India also. And this is a, I mean, division of renewable energy production in India actually. So wind power, we already cumulative achievement up to 46,000. We have potential up to 50,000, and we are already reaching to the maximum limit. So after that, actually, we are trying to focus offshore wind power generation. And now next is we solar, we have a target to the 2025 1 megawatt, 1 lakh megawatt. So already we achieved 85,000 megawatt. We already achieved. This is also good sign. And next is other sources in the small hydro, biomass, waste to power and wind. So these are all very small achievement, but cumulatively right now we are close to 1 lakh 50 thousand of megawatt of energy we install through renewable energy. And 2022 itself we achieved 1 lakh. Actually, last 3 years we added 50,000. That's what significant developments happen in India. And we have good statistics and the data that we can collect from NPP, so National Power Portal actually. And a lot of data is available where one can use this data for data analytics and analysis or something. And we can see that how grid is connected in India. So right now we have Power Grid Corporation of India is there, which owns the major transmission company and owns the interstate transmission company. And we have 5 regions like northern, eastern, western, southern, northeast, and all. So except southern, other 4 regions already synchronized. That is called central grid. And later we have synchronized with southern grid also using HVDC. And right now India is now we are claiming that we have one frequency in India. So that is what right. And we have, this is what interlink between different regions. We have well established HVDC links are there. And this how the energy management is happening currently in India. I mean India. So energy exchange will happen between regions and states actually using these links. And 2013 itself, 10 years ago itself, we have achieved that linking between southern and central grid. So one nation, one grid, one frequency, that we achieved that actually. Between linking, line linking between the Raichur and Karnataka, Solapur and Maharashtra, that we did it. And we have national load dispatch centers are there, and then state load dispatch centers are there. So through that we are trying to manage the energy. So these are all requirements, so we need to understand how the energy flow is happening in India. So between the states and different applications and all. So this how government is maintaining that actually. So these are the load dispatch centers in India actually. So southern we have at headquarters at Bangalore, and other 5 regions, other 4 regions are located in New Delhi, Mumbai, Kolkata, Shillong, respectively. And we have, this is a transmission distribution system, and then these are the distribution side. So we have very kind of complex kind of systems are available in India, and we have always challenges because India is a big country. And right now, I mean, almost like we have 6 lakh villages are there. So it is very difficult to map them everything, through this, sophisticated, good lines actually. So we have always challenges are there. And at the same time, we are recording highest transmission distribution losses 20%. So now even agriculture also, if it is fully depending on the grid connector system, and this more one of the, I mean, nearly 20% consumption goes to the agriculture sector in India also, apart from industrial sector after that. So now how to mitigate this kind of transmission distribution loss? So right now in India we have close to 20% transmission distribution losses. This is one of the biggest challenges. Now look at every sector now, if it is self-sustainable, generation happens, then we don't need to depend on this long uh, transmission distribution systems and all. And our per capita consumption also increasing. So right now we have crossed 1350 units per person actually in India. So and then we have close to 6 lakh villages as I said. So these are already fully electrified now. So now we have good connection with all the villages now. We can try to tap this energy from directly. But still we have challenges in India. So there are some hilly regions, remote locations, and where they have very difficult to access this energy by 24/7. So in that case, now solar is going to be a viable solution for the agriculture particularly. And our peak demand is increasing actually every year, and we can look at some of the seasons it's going to be peak. So how do you address this problem with current grid scenario? That's another challenge. And next is energy requirement. Every time in terms of million needs also increasing because our needs are increasing, infrastructure is increasing. So that is one. And this is what the energy production by volt. So we have a lot of renewable energy expansion is going on. So now we are trying to see that so what kind of applications directly we see using solar and wind. So direct. So that's what is coming with a lot of innovation. So it can be applicable for residential, commercial, and then industrial applications also. Of course, this transportation people also now inventing some of the technologies with solar and wind with the transportation sector also, even with agriculture. And right now we see that development close to 40% that we already delivered through renewable energy. So decline, you can see the decline of the coal-based power generation at the worldwide. So that is a good sign. And we already crossed 40% actually. So right now we have already 42% we are already producing from renewable energy from at a global level. That's a good sign. And we are in the band of this 30 to 40 band right now actually. So we are in band of 30 to 40 band. So in the renewable energy production, that's a good sign. There are some countries, still they are, very good. They are climbing, more than 90%, power generation from the renewable energy, like Canada, and there are some South America countries and then African countries. They fully depends on solar based. And a lot of solar based innovations are coming up well in African countries because they have very much abundant with solar power generation there. And our per capita consumption is now 1350 kilowatt hour, so units nothing but, so as of today. And that is almost like 1 by 10th percentage of developed countries. So we are consuming less. Okay, we see that we are producing like 445 or 450 gigawatt of energy. That is again less for this country, large country. But we are consuming less actually. That's a good one. But unfortunately, we are standing in the highest carbon emitting countries. So now we can look at the compare with the China and then USA and then India. We're standing at third place while emitting this 0.75 billion metric tons of CO2 emissions every. This is again. So that means what kind of energy efficient technologies that we are using it. So with reference to grid or with reference to off grid actually. So that means we have challenges always and opportunities with when you deal with renewable energy based also actually. And greenhouse gas emissions, this is what the why we are going with sustainable solutions using solar and wind or renewable energy, because we have seen the witness to the greenhouse gas emissions last 3 decades actually. It's increasing, but somehow we are trying to decrease this exponential rise actually. And we can see that India is somehow it's better. So when compared to other countries, actually, we are trying to mitigate our greenhouse gas emissions, but we can see that an exponential rise with China. It's a very dangerous to the not only nearby countries like China and others, but total world itself. So this is very alarming situation. And this is what already we discussed it, how the temperature rise will go up. So if you avoid, if you try to bring the, if you don't bring the sustainable solution to avoid this greenhouse gas emissions. And we should see definitely the applications of these sustainable technologies, and not only electrical power generation sector, we can see that industrial and transportation and buildings also. Wherever it is possible, let us try to bring this sustainable and based technology so that we can try to avoid the CO2 gas or greenhouse gas emissions and all. And this is what now broad area of renewable energy power generation. So one can focus on small, I mean wind. So again in this wind, small wind and large wind, actually based on the application where you want to install it, how much power you want to generate it. And next is solar based systems. Again solar also can be classified for domestic and commercial and industrial applications also. So now we are today we are trying to discuss more about with agriculture based sector and all. Next is small hydro. This is another also energy based. Again, also here we can classify large and then small and micro also or pico also. That kind of classification also possible here. And geothermal we have not exercised in India actually, but this is also another, I mean, good time of kind of energy that we can produce in terms of large volume. So that means more than megawatt. We can directly produce in terms of gigawatt of energy. We can do that actually. And wave and tidal, it's again, it's a pilot project. We have done it, but we are not done with, large plants. We are not done in India. And we can see sometimes, we should see that applications of renewable energy not only for power generation, and we should see other, direct and indirect applications also, so that we can bring this energy efficiency all the time. So one is power generation, that is okay, but actually you can see sometimes, solar directly can use for cooking application, heating application, water pumping, and transportation and buildings also. So this kind of applications also one can see, so that we can directly bring the more energy efficiency in the direct and indirect applications and all. And we have now blessed with good solar irradiation in country. So we can see this map actually developed by NREL for India, where we can see that an average we can India, so we can produce 5 kilowatt hour per meter square per day that we can produce. Okay, this is very good. So 5 kilowatt hour, 5 units per meter square per day that we can produce, an average in India. Actually. This is a good sign. That's what we have a lot of potential for solar. And now in solar also a lot of developments is coming up and new innovations are coming up. So even India also we can see some of the good plants of this floating solar power plants also in India. And in the solar actually a lot of developments happening with reference to solar cell developments actually. So I was starting with silicon carbide and then next is crystalline, multicrystalline, amorphous, and after that CAS and cadmium, tellurium materials and all. And people are talking with a micro thin film cells also actually. So a lot of developments is happening, and these are developed by this material science and nanotechnology scientists and all. So we can see that how in future how the solar cell efficiency can be improved now. So right now what we see that in market, so each solar cell efficiency is less than 20% actually. That's what another biggest challenge for this material scientists for them. And how can you enhance this solar cell efficiency? So right now there are we can see some research studies where they have proved that solar cell efficiency between 25 to 30% also, but still they was yet to be commercialized in the market. And this is how we can see that solar cell development, and then we can make see with series combination, parallel combination, then we can make a model, and finally you can have these models can be connected. We can make a one array. So this array will be available to in kind of one kind of plate available. So that we can directly install into our place and then we can generate the power. And maybe this is a ratings will be available based on the how many modules that you arrange in the array. So maybe start with 100 watt it's possible, 200 watt is possible, like that.
One doubt, sir. So before that, floating solar.
Yeah.
So is there any plant in India?
Yeah, it is there. It is there. One plant is nearby our Ramakundam. So near Ramakundam, this NTPT has established that actually. So one plant is there. So that is next is we can see that one another plant is Kerala. So one more plant in Rajasthan also. So three.
Both
So one high.
Wave and solar, both will be there. And one is solar, floating solar.
Sorry.
Wave or tidal is also there.
No. Only
Only
solar.
solar.
Only solar. and highest 3,300 megawatt, I think. So highest capacity of installed capacity 3,300.
But the life of normally what we say, the life of the material will be less when you are using steel. So if you are floating solar means the life will be less.
It's not so actually, but still that I mean, what do you say? Mm, what that theory is not proved well. I can say that. Okay. Still, we need to investigate. Okay. And both every technology it has its pros and cons. So this is one of the cons that you are talking about it. Still, we have challenges to overcome. Yes. And yeah. So now better understand now the solar system. Then we'll go to agri PV applications today. So in this solar, so this is very conventional solar energy system that we most of you are aware of it actually. So we have solar irradiation that we get, and then solar panel. We mostly we'll put it to if it is fixed plate, then we'll fix it to east side, and then with 45 degrees. That is a general way that we do that. And then next is we have this DC-DC converter because we generate from DC from solar, and but at the same time we want to extract the maximum power. Then we implement MPPT algorithm for DC-DC converter, and that DC voltage is not enough to boost to the grid level voltage AC in terms of AC. Definitely, again we use boost converter here. And since we have a DC link here, then we can use the DC-DC converter charge controller to the battery, because battery voltage something and then we generated voltage something else. So to map this again, we need to have a charge controller. So using the charge controller, we will try to again map this voltage equivalent to your battery voltage. And of course, we can do the sun tracking also. That also another phenomenon I can do that. And you can use the sensors or the photo diodes. Which one? This charge control. Yes, sir, this also can be done, or you can make separate one also. Because now, if you want to incorporate some battery separately, maybe this battery can be like your UPS system and all. There itself already inherently will be there. That also can be connected. Okay.
But present we are using without battery we are using the solar.
Yeah.
Directly we are generating.
Directly you are generating, you are consuming, or if you have any excess power, then you are feeding to grid. And you have net metering system will be there. So in net metering system, we will have a what is your consuming, what is your delivering to the grid. So that our utility company will make that as a minus in the electricity bill. And these are the trackers available currently in the market actually. Fixed tilt. So as I said, maybe each side 45 degrees you can keep them, and then it's a fixed, most of them like this. And now people are coming with some kind of these methods actually single axis trackers actually. So it will be tilt to one direction only. But whereas you can see that dual axis tracker, we have a tilting of the solar panel as well as tilting of this total layout also. So that is also possible dual axis. So this kind of technology is also coming up well in the market now. And but mostly these two, for the industrial, I mean large power generation application they will see. But we don't see this kind of mechanical structures for the residential right now. So maybe in future it may come in. And now this is what solar power characteristics actually. And we have a voltage versus power, and then for the different solar irradiation you will get a different term. Now our challenge is now to extract the maximum power irrespective of the solar irradiation. That's what MPPT algorithm we apply for this site. So right now, I mean broadly, we can classify 4 types of PV systems actually. And recently, I mean before Corona also, CEA, Central Electricity Authority, they have released some perspectives also guidelines actually. So one is so grid connected solar PV system without battery. Okay, whatever is generated directly pumped to the grid, that's possible. And another one is you can connect to the grid connected but net metering system with battery storage actually. So in view of grid disconnect from grid, or in view of any kind of I mean abuse operation from the grid, so that you can do that actually. And the other third one is off grid standalone system, okay, with battery. And fourth one is off grid system, a PV system without battery, that is independent operation for houses, street lights, pump set, etc. So this one. So one is grid connected with battery, without battery, and off grid with battery, without battery. So generally these 4 configurations are available actually. And right now we are talking about today this main application for solar. So this is off-grid power generation directly for agriculture application. If at all, if you have an excess power, definitely we can switch over to this battery based also in agriculture also. That is also possible. You can work it. Yes, yes. So that's what you have to choose your application. So that means your application should be able to accept the whatever power generated fully. Okay, load should accept. So that means suppose if you see that suppose you need to define first in that case a load profile. So what is my load profile? 0 to 24 hours load profile, and then how many days, weekdays and weekends, whatever it is. Okay, so that way you need to see the load profile. So your load profile, whatever the energy produced by solar in off grid, so that should be consumed every time. So you should not have any excess power. You should not have. That means so any ultimately you need to see the energy balance. So what is the energy balance again? So generated power equal to consumed power. So always you should see the balance. So if you don't have a balance between them generation and demand, then definitely this battery and grid connected will. If you have excess power, then what you do is two options. One is you can store the power in the battery, or if a battery is not available, even battery is fully charged, then you can pump to grid. Okay, or if energy is less from the solar, maybe some kind of solar radiation problem is there, rainy season or cloudy, whatever it is, or night times and all, then you can depend on battery. That's first choice, or you can depend on grid connection. But again, we need to see here what is the viable solution or in terms of techno-economical. So whether battery versus grid. Okay, suppose if you want excess power you require, so whether you should tell me that drawing power from the battery, drawing power from the grid, which is economical, is it right? So battery only economical. Possible, possible. But actually in solar, better to have battery because that as I said, first is if load profile accept is no problem. But in case of over the daytime, okay. So after the daytime, I mean after the daytime, then if you want loads is required the energy, then battery is good to supply that. So then this is the typical again in different fashion it is shown here. So we have solar and DC converter, inverter, and then we will connect it to mirror load. And you have MPPT controller this side, DC and this side you have a grid controller and inverter controller. Here always we should see that. So we should have this voltage regulation, frequency regulation, because ultimately as they know from the utility point of view or user point of view, we need fixed voltage and fixed frequency. Either in case of single phase 230, 50 Hz, and three phase if at all 450 and 400 and 50 Hz. So your inverter controller should do that to achieve this fixed voltage and fixed frequency that actually. And now this is what how the solar energy systems are trending now actually in the market. So we can see that now we have solar panels and we have a string inverter will be there. This is another setup here. So where you can see that directly connected. So there are two systems can be connected parallelly. That is possible here. So one observation you can see here, there is no DC converter. Okay. So whatever now here we are generating power from the DC, I mean using solar panel array. So that is directly that we can convert to AC. That is possible. Okay, without anything. But here we don't achieve that maximum power extraction. That may not be guaranteed here. Okay. But whereas here you can bring the DC converter here, and then you can bring the one common inverter. So that is it. But again, you can see that another disadvantage here with this common inverter if it fails, then total system you need to shut down. There is another disadvantage here. So and then we can have a modular way actually. So people are coming this way now. So solar panel with uh, this one inverter and this second. So this is how people are. Suppose even in our campus also maybe you have installed first 500 kilowatt solar panel. So this first module, and then later you will enhance to your power plant to another 500, another 200. Then you will add another module here. Then both are will be connected. So like that you can make in modular way, so that we can have some kind of decentralized modules, and we can bring the some kind of reliability into solar expansion of energy. That is possible.
If the normally voltage is not the same in the field and output voltage is not the same, so at that time how to maintain
if it is inverter. So that is the challenge definitely. If it is in the options of your DC converter, it's a definitely it's challenge. Okay, this is challenge to your inverter. Okay, but most of the systems right now, so DC converter is available. It's available even for large power systems. It's available. And this is a single stage, single phase, single stage PV system actually. So we have solar panel and then single phase inverter, and then you have LC filter, transformer, and so this is a simple one. So where most of the times we see this kind of configuration also. And next is single phase, single phase multi-stage PV system actually. So this is, you can see that inverter will be there, and now we can bring here high frequency transformer isolation between this primary circuit and this secondary one where you are connected to utility or loads, and then this AC again you can rectify to DC again. So this DC again rectify, inverter to inverter again connected to utility or loads. This is another one. But this has again advantage disadvantage because you are increasing number of converters here. But we are trying to bring the more power quality in this rack compared to previous one. That's the one advantage. That's it. And similarly, you can go with three phase. If at all your application at the end of the point, say a user point of view, utility point of view, if you want a three phase power, then you can use directly three phase power, inverter, then connected to filters, connected to transformer, connected to utility as well. That is possible. And one can bring this multi-string operation also. So where you can connect like this, we have solar system, DC, high frequency controller, and you can convert that AC to DC. You can have built a common DC bus bar. Now we can connect a single phase inverter or three phase inverter connected to utility. So this is also possible here. And typically this is a single phase grid connected system that we see in the market right now. So what we do is we apply MPPT controller here. So for which we will sense the voltage and then current from this. Okay, and then at the same time we need to see that what is a DC link voltage that you are appearing here actually. So we have the reference also. We will provide the reference. So I wanted to maintain this up because this reference is very much important to achieve this fixed voltage, fixed frequency here. So based on that, is very much important, and we'll try to find out what is the error. So this error will be given to PI controller. So using that will be given to current controller. So which will be help to develop this PWM pulses for this inverter. So at the same time, this current controller also require this sensing of the voltage, voltage and current from the grid point. So this is what is required here. And this is what solar rooftop power plants right now it's established in India. So we can see that solar panel is there, and then we have charge controller is there, and you have battery. So up to this is okay. So that means so you have DC converter is there where we implement MPPT here, and then store the energy to battery. And at the same time you can use a bidirectional inverter here. So we can convert this in DC to AC, and this AC voltage power can be given to loads, or you can connect it to utility. So when you're trying to pump this power to the utility, then you can use the net metering system. So that we'll try to see that whether you're consuming, whether you are delivering power to the grid. Okay. And now since it's a bidirectional now, so now you can charge your battery using this. Now you can take the power from the grid, and then through this bidirectional converter you can charge your battery. And next is the battery can directly also energize your load. This also it's possible. So this is what now. So that nothing but it's solar directly you can incorporate or integrate with home EPS systems. So when home EPS systems already battery is there, inverter is there. So now you can try to incorporate this so solar system with the home EPS system. So right now in India everywhere solar PV rooftop means this kind of arrangement will be there, and with the net metering system it's possible.
One doubt, sir. In the EV vehicle, normally we use the chargers. Is it AC to AC converter or inverter?
That depends on onboard or off-board. Okay. See, generally, if it is two-wheeler or four-wheeler, whatever is available right now. So those are the charger. Charger is nothing but EVAC. I'm EVSV. I'm talking about EVSV. Electric vehicle supply equipment. Whatever they give box, and we'll keep it on the wall, and then we'll take. So that is only AC to AC. Okay, AC to AC. So the conversion will happen is AC to AC inside the vehicle. Okay. And then of course after the AC to DC, And then you have a charge control similar to this car charge control. You have charge control in the battery in the vehicle.
So only for the charging purpose, we the DC one, not AC. At the terminal, battery terminals.
Yes, DC on.
DC one.
DC on.
AC one.
DC.
No, DC.
DC only. Yes, DC only. Again, it depends on rating. Again, so two-wheelers will maintain what is the voltage 48. Some vehicles will maintain for 72. If you go on, this is a light-duty vehicle. If you go on heavy-duty vehicles like buses, trucks, and all, they maintain 800, 900, even 1000 voltage also. So DC voltage. Then your charge control should be able to, do that. 1000 volts boost. That they should do that. So mostly wherever you have the battery application, so charge control is necessary. Because how do you map this in a battery voltage? So same whatever the specification of the manufacturer. So we need to see that voltage is now mapping to this using charge control. So that will. This is structure we see in this grid connected system in large power plants, whatever you see megawatt or gigawatt plants in India or wherever. So we come up with the solar plant with this switchboard production and then inverters. So this is LV panels and then AC panel. Okay, nothing but. And then we have power transformers and then we'll try to connect with the grid. So that means we go with a high tension panel and switchgear, circuit breaker arrangement. And then finally it will reach the substation. From there we will try to pump to the grid. So maybe your transmission line depends on whether it's 11 kV, 33 kV, 16, 66, 120, or beyond that 220. That's what transmission our voltage is available in India also. And this one net metering system is similar diagram, same diagram compared to the previous one. Okay. And sometimes you can use double metering system, but we don't use double metering, but still you can use that. So now we can have this grid to this whatever loads are there. So we can have one meter actually. So where you can have secondary meter from the solar and then inverter, you have a second meter. So but right now we don't use that. We are using one net metering single system where we have that both measurements are. This is a solar typical application now. Solar system establishment in the point of control monitoring and control and monitoring actually. So we have solar panels and then DC converter. We have DC link that will establish, and then inverter filter and finally connect to it. And where what we do, what are the tasks we do? Where basic control functions. One is current and voltage control that we do. And DC link voltage we need to maintain constant. Otherwise we don't get constant voltage, constant frequency. It's very difficult to get across the inverter here. And then grid synchronization. That is another challenging issue in the point of control function. And we also work on the MPPT islanding mode. Okay, if at all any abuse operation from grid, and then PV planning, plant monitoring, overall plant monitoring for asset management or something. And then we work on other ancillary services like voltage and frequency and reactive power control. So that's another challenging task. And fault rate to energy storage, harmonic compensation, and then constant power generation. We try to see that from solar panel. And this is what till now we discussed about power generation. But nowadays people are coming with some other innovative ideas for solar also can be used for the transportation application. So one example is solar EVs actually. But still this is again very difficult task to supply this full power to the traction motor. Maybe if the traction motor of the vehicle, vehicle is 20 kilowatt, the motor is there. But whether you have 20 kilowatt of solar panels on the rooftop of the car, that is a challenge. It's not possible. But the solar can be useful for those kind of vehicles as auxiliary power supplies. So that is what we can do. And of course, we can include this battery pack. So we can continuously energy this battery using solar panel. Thereby you can have cumulative. So if you don't use a vehicle and then you can cumulatively energize the battery and then you can try to see that full power sent to the traction motor. This is another way of operation. And solar hybrid EV. Okay. And here hybrid you can bring one is we can have connection of ultra capacitor or super capacitor, where we have dynamic surge operations or the hill climbing or something, any abnormal operation required. We want additional power for this fraction of time. Then you can depending on this ultra capacitor, super capacitor, and at the same time you can also use this plug-in option from the grid. So since you have a plug-in and you have a battery pack, and definitely this will bring the combination of hybrid actually. So this way you can bring that. And solar powered autonomous underwater vehicle, that's possible. Solar boat, that's one other size of flight. And we see some kind of good trials also on solar rechargeable aircraft also. So we have solar arrays on the wings of the airplane, and then we can have this battery storage, and then two motors will have its own propellers will be there. Okay, both are separate now. We can have one master control. So this also even including NASA also, they made successful trial on this actually. They did that, and this is how it is there. And you can see one observation here. There are two inverters are parallel connected. These are redundant inverters. Sir. Even one is advantage is we can have pump the more than rated power to the motor. So using two inverters. So you can have power sharing, that is also. And at the same time, for the reliability point of view, even one damages, other one will be there. So because safety and reliability is high important in this flying. And we can see now we can bring to solar PV application for agriculture. We'll come to that actually. Yeah. So there are some guidelines actually. What we know very popularly solar application for agriculture. So we know it for water pumping application. So that's what everywhere started. Not only in India, all the ways, all the places, and globally. So we see the application of solar systems for water pumping system. So we have some kind of guidelines and test procedures actually with reference to source of MNRE actually. So we'll see those now. I think I can show it now. I can show that. Yes. Yeah. I think it's not coming. How to bring that? Screen share. PPT కావాలి అది browser మీరు entire screen. Yes. Now, this we can see now. A government of India has released some kind of guidelines for people solar-based, water pumping systems actually. In this, somebody can help me. Like, I mean, we can scroll down this, page. Yeah. So this is a good document actually. So they talked about here, definition. They actually, yeah. So in this, they talked about, with reference to Indian standards, BAS, Bureau of Indian Standards, and IEC. So mainly, we adopted the standards, IEC standard actually. Later, we are compatible to the Indian standard actually. And then in this document, they clearly define, what is, solar PV system actually, and then how it is standalone operation is connected or not. And next is they have given water pump motor water pump setup actually, which is driving the motor. And then they also talked about controller, what kind of controller, particularly based on this DC converter if you are using for solar actually. So they are given this kind of system definitions and parameters. So if you see the parameters also now, so we can see these are the parameters we need to understand that flow rate, what is the flow rate for the water, because ultimately our aim is to pump the water. And then motor voltage in terms of AC DC, because we can use DC pumps also for the agriculture application. Nowadays we are completely relying on the AC. And then people are coming with multi-phase AC also, multi-phase DC, because now we can go with the three-phase and beyond also. But most of the application with the three-phase and single phase. and then power factor, and then frequency, motor speed, radiation, and temperature with reference to solar panel. And they are come with some kind of guidelines how to set the set up this kind of the test bench for the solar based water pumping systems. They are given the precautions now. So precautions also they are given, and these are the complete parameters. Okay, just now we have seen that, and in that we need to understand morely with reference to solar panel, solar array voltage, and then array current, and then open circuit voltage, short circuit current, maximum power voltage, maximum current. So all these things are there. Then go down. I think we have seen this. I think we can arrow. Yeah, that's better. So next is precautions for test setup. Actually, they have given that. And then priming arrangement. What is the priming arrangement is required? So for solar panels and all. So they have given the measurements also, measurement and uncertainty. So if the uncertainty in the measurement should be always less than 1% for voltage and current measurement. This is what we see that. Even we try to see the similar measurement for the calibration of the equipment also, measurement using instrument similar to that. And this is what the allowable head also they are given, sump well, and then what is the meters and all. Yeah, next. Yeah, they are given the drawing for the sustainable pump set. There's another also drawing is given, solar based. So like that, very clear guidelines are there available to us. So based on the solar, how we can incorporate with this solar with the water pumping system. So this is what again, typical solar radiation, hot and cold profiles. So typical one. So outdoor conditions, and then there are some simulator methods are there given. Yeah. Next. Measurements, yeah, solar radiation measurement we should do that. And then next is now importantly measurement of head, because we are trying to see the application for water pumping. So head is very much important. What is the delivery head? So that is important, because the quantitative amount that we are measuring water in terms of the head only. Okay. So flow rate, so that is another rate. So Q, that we need to measure with Q, meter cube per second. Okay, and calibration of the operators, definitely we should do that before testing or measurement. Yeah. And then they are given the test procedure. So per day, water flow test, first install the pump set, and then connect the pump set with the controller as per the manufacturer instruction, and then using the solar PV array simulator to find out what is the actual output from PV, and then controller we should do the connect with that with the profile, and then finally we see that performance operation with the realistic conditions and see that whether your delivery of head for water flow whether it is as per the desired operation or not. So these are computational test readings. Okay, how do you measure this total head for the surface of pumps? They are given the formula here. So heads. Okay, so this is a formula. Yeah, next. Some observations to follow during the testing. What are the calculations on that? This is the temperature value, water temperature values. Yeah, next. Next. Next page. So total water per day. So this is also very much important. Okay, because your efficiency of the water pump is will be defined as with calculation of total water per day. Actually, this is another important thing. And then water output per day per watt peak. This is also another important in terms of energy that we see whether your water pump system solar based whether how it is functioning. So per watt peak. And this is a formula, power mismatch formula. So what is the other factors? Efficiency of the solar panel array, then output current, output power, okay, voltage. These are all things we need to see that. Otherwise, we don't get the efficiency properly. And then what is the duration of the flow, start time and end time, and then during that time, what is the total per day flow in the liters, in terms of liters. Okay, if we try to operate the motor for so many hours per day, so this is how we will get the hours in terms of lakhs or something, thousands and all. Okay, so very detailed report, good report, it's given here. So to find out these are all standards what we directly adopted from IEC standard, and then we have modified our Indian condition, and then we named it a BA standard. Okay. So these are the referred ISO and then BAS and then IEC standards for the solar-based water pumping system actually. This one. So another report is next one, sir. This one. Second report. Yeah. So top. Specification. This is again. Maybe yeah. So maybe you can close website. Website they are asking to close and then zoom option. Control please. Yeah, it's okay. Now it's visible. Yeah. So this is another very good important actually. If anybody working on this solar PV based water pumping system, actually very clear technical details are given. Even I have seen one PhD where I was examiner for this actually. They completed thesis on the solar water pumping system actually. Now we need to see that how realistically this work can be applicable to practical applications like this in the field. We can see how this can be helpful to us. Yeah. Then, so they are given all the terminology definitions very clearly here in this report. Very good. And then construction details also. Okay, solar PV system and then pump and then controller. And then here the definitions like control capacity for to drive, and then MPPT and enclosure. Okay, and then insulator switch, and then what kind of communication system that we can do that, all these things. And solar PV system, now we can see that maximum minimum capacity range, so 900 watt to 22,500 watt. So that means, so minimum water pumping system in India is available 900 watt. So 900 watt system is available up to 22,500 actually, and then that's what now it's available. The power output of individual PV systems in PV array should be minimum of 300 watt. So that means if you are purchasing a solar panel from market, that solar panel should give the output of 300 watt minimum. So such a way that you should purchase it and then install it in the agriculture water pumping system. So this is all. So there's a peak. And then next IEC standards and all. It's a very detailed is given. So this in terms of power, we should follow that actually. And then next is your modular efficiency should be 16% to fulfill factor more than 9. So that means already we talked about solar cell efficiency in our model. So at least minimum 60%. That means we need to see that the manufacturer of the solar solar panel, you should specify what is the efficiency of the solar module actually. So these are another thing we should follow that. So next is and we can use two types of motors now. So one is AC induction motor, or you can use DC. Again, you can use PMSM and then PMBLDC and then SRM also you can use. So and then we can use this two motors are possible. One is surface mounted water pump. That means you will find the water pump setup, water and pump and then motor on the surface on the field only. But another one is submersible pump actually where we can see inside the air. So that will be vertical, where you see the vertical pump will be there. Okay. So any other motor pipe, then we can see the approval. Right now these two only available in the country, and we can see that starting with motor capacity is 1 HP is available. So that means 0.575 kilowatt, and then we can go up to 25 HP, that is 18.75 kilowatt. So that's what pump sets are available in India. Okay, it can be AC and DC, both are possible. Government is allowing that actually. So these are other harmonics also. They define that as per the IEC standard, THD for voltage and current should be 3%. So you should see that controller should be able to get that access. So 3%.
Normally in hospitals, sensitive equipment, they need only 5%. That I think is fine. 3%
Yeah, it's difficult. Okay. Yeah. But even now, the IEEE also relaxed to the 8% of the voltage. Current is 5%. Yeah.
but maintaining 3% is also very difficult.
Difficult. Yeah. But that is not our headache; it's the manufacturer.
Yes.
So they need to prove and then specify that in the nameplate or something. They already. Otherwise, government will not permit them to sell their product in the market. So they'll make some kind of test study. People, they do that actually. So they under particular condition they achieved it. Maybe they tried to see that one kind of load pattern and all. They see that they will try to do the market.
Sir, which DH we will concentrate, sir? Current DH or voltage DH?
Both are it.
Both are
Both. Yeah, this is about controller again. So MPPT definitely is required, but they didn't mention what kind of MPPT that you are using. So we have relaxed there. And next is these are all things, okay, controller, these are all things, we should display the screen. So power on and off, what is input DC voltage, output voltage, and frequency, RMS values, and then, HP, PV voltage, PV module voltage, pump status, kilowatt, total generation, all these things. These are all details should be displayed on the pump controller actually, as per their guidelines. And then we need to see that what is the earthing and lighting protection they have given as per the IS standard actually. This one. Both, both, both separate. So such direction and then performance characteristics here. So we see that here they have given it's increased actually. You can see that average daily irradiation, it's a condition of 7.15. Actually, we were talking earlier, so 5 kilowatt. But now they are talking about ideally. So they say 7.15 kilowatt per meter square that we can produce per day. That's what our potential in the kind of solar in India. So we can
Is
see
it beacon, sir? Or is it average?
this average daily, and then they have given again specifications for DC pump set. If you take the DC pump set, and then 110 liters of the DC water per water peak of solar PV, and we can use the head of 10 meters, and minimum is 7 meters. So that way you should be able to do that. And in case of head is 20 meters, then you can able to produce 55 liters. Okay, delivery of the water. So if you use 30 meters head, then you should have 10.5. Sorry, 50, 23. And then if you use 50 meter, 23 liters. If you use 70 meter head, 15 liters. If you use 100 meter, then 10.5. So like that, this again directly proportional. Is it right? So you have you have a direct relation between between head and discharge. Okay, head and discharge. Yeah. So these are all guidelines, the relation between head and discharge the government has given. Manning head. And then similarly for AC pumps. AC pumps again you can see. So 10 meters, so 99 liters. Yeah. Yeah, these are 20 meter 49. So 70 49, 70 14 liters. I think this is AC one, is it right? And here you can go with more head. So when compared to DC pumps, so in case of AC induction motor, we can go with more head. So we can also see the improvement also in the discharge also. And these are the general, requirements, actually construction requirements, general requirement, design, insulation, resistor test, high voltage test, leakage current test. These are all things we need to do as per the IEC or IES standard, actually Indian standard. And performance guarantee, we need to see that. And again, they talked about whether you are trying to generate the 7.15 kilowatt power per day. It's an average. So that's one. And we need to test that for 60 days period. And finally, this motor pump set which have a nameplate display. These are the parameters they should display. So if you are purchasing any pump, solar based pump, so they need to declare these are all items on the display actually. Next. So controller also they given this controller. So model number, serial number, voltage range, power range, okay, and then current rating, which country they make it. So all these things required. And also you should have an operation maintenance manual, OM manual. So that is also required because if you are, if at all anyone from user point of view required, then we can follow for service kind of thing. Then comprehensive maintenance and all this operation maintenance. Next. 5 years warranty. And then these are list of Indian standards that we applied directly to this solar based water pumping system actually. Next. So these are all different solar models. Now they are the solar model combination for they are given. So model structures, what is the thickness and all these things. Clearly they defined. Yeah, and then this mechanical structures. So for the solar panel and all. Next. Yeah. So pipes. So everything there is very clearly defined. And this is very interesting. This table. Yeah. Suppose if you use a DC pump set, DC motor based pump set actually, then you can see that there are 13 models are there. Suppose if you take the model 1, the peak power should be developed for this solar panel 900 watts. So 900 watts you can should develop, and then this capacity is 1 HP. So motor pump sets capacity 1 HP, but whereas your solar array is 900. You see, they always you should remember that so your solar power generation should be, I mean, rated should be more than your pump set. Is it because you have energy loss? Definitely. From solar panel to your converter and then motor to pump. So that energy loss will be there. Then thereby you will see that 900 here and then this is 750. And then you can see that head should be maintained for this model 12. And then what is the latest that we are generating per day? So close to 1 lakh. So 99,000 from head of 10 meters height. So we can able to produce 1 HP motor. Using 1 HP motor, then you can produce nearly close to 1 lakh liters per day that you can produce using DC motor. And similarly, you can see the different models. So you can see 13th model. So 9,000. 9,000 watt solar panel you should select it, and then a 10 HP motor you should choose it for water pump capacity, and then you should maintain this 45 meters head, and then per day 3,42,000 waters per day you can deliver it. Okay, so this is what the manufacturer will do that actually. So similarly, if you do any kind of research work, then whether your model is suitable to which model. So that way you can take, even suppose sometimes students are, we do the simulations also. Then students solar water. Then what is the solar panel capacity? What is the pump capacity or motor capacity? And then what is your load? Or finally, what is the outcome in terms of water discharge? So in terms of Q. So this is we need to see whether you are mapping to this or not practically. Okay. So next, this is okay. This is a continuation up to 26 model where you can go 18,000 also solar panel, and you can maintain head also 70 meter, and finally you can generate 4 lakh. And highest I think you can generate from this model, I think so. So 7 lakh 42,000 we can do that. So where we can use 15 HP motor, and then 25 meters head you can do that. So this is a good one. And this is based on solar power generation average of 7.15 kilowatt per day. But if it is solar power generation in your place less than 5, less than 3, then we don't get these results. Okay. Yeah. So still I think still continue. This shallow surface motor actually. This surface motor actually. So brushless. These are DC with brushless. BLDC motors actually. So these are BLDC motors actually. But you can see the power delivery, water delivery is less. This is a deep well, submersible pumps actually. So these are also other model. Whereas previous one, what we are surface models. So this is a deep well. So this is also I mean low discharge it has. Yeah, it's continuing for solar P28, and then only 1,71,000, and these are all 2 lakh and all. Yeah, yes, next. Yeah, next we'll go into next model. This is interesting again for the industrial motor, AC motors. So in AC motors again start with the 900, 1 HP, and then head is you can maintain to 12, and then your power delivery is 89,000. Okay, whereas in DC we are saying 99,000, whereas AC it is coming down actually. So these are another AC actually. Yeah. So this model is continuing. So for solar power, you can increase it, and finally, it's a aim to what kind of water output that is required. So that's what we need to see that. So whether your agriculture farm is required, what is the quantity of water output required per day. So based on that, you can choose a model. So accordingly, you have to choose that solar panel, and then so pump set is a combination actually. And accordingly, we have to make the infrastructure for the head creation. Okay. Yeah. Next one. So this continue. And then also this is a remote monitoring system. Now people are coming with some kind of innovative ideas for the solar water pumping system like IoT based systems and all, where we can start it with a switch on and off. And then we can see that what is the performance of the solar water pump systems, and then geolocations and consumer management, asset management. These are all things also we can do remotely, where people are coming with innovative ideas with IoT technologies also. So that is also possible here. Okay. And also they mentioned that what kind of communication technologies also that we can use that actually. And then the remote based on automation, timer mode and annual. Because ultimately we can build the system based on 3-4 modes. So all four modes are mentioned here. And then communication modes also given here. Command and demand, or push data. So push data and event and notification. So like that. So that's how we can see that some kind of interdiscipline, and also at the same time, if you require data storage, also we can take the part of this project. So that also you can do that actually. And these are all certifications actually. So if you want to get the recognition from MNRE government, if you want to become a vendor for this, and they have given some kind of guidelines also. I think we can skip this. I think that's it. Yeah. And yeah, you can go to my it's not this. Some of the companies are there. So we can see now, sir, there are some kind of popular manufacturers actually, and trending one. What are the technologies they make it actually? Very good companies are there, Indian-based companies. Where you can see one of the Indian-based company, multinational like Shakti Pumps actually. So they make a lot of innovative products, and they start with DC surface motor and then submersible pump. And they come up with a lot of innovations within a BLDC and SRM also. So a lot of even solar, they are the also pioneers in India, along with others like solar-based power generation systems also for water pumping. Okay. So we can see some of the models here. Okay, yeah, we'll take for 5 minutes break. We'll continue the session now.
So all participants, 5 minutes break, tea break. Later we will meet again and sir will continue.
Yeah. అదేంటంటే డైరెక్టర్ ఇన్ఛార్జ్ ఉన్నాడు సార్ అందువల్ల ఇన్ఛార్జ్ ఉన్న మొన్న ఐటీ డైరెక్టర్ ఐటీ హైదరాబాద్ డైరెక్టర్ మాకు ఇన్ఛార్జ్ ఉన్నాడు ఆయన ఇన్ఛార్జ్ ఏమో ఆయన పర్మిట్ చేశారు ఆయన మా ప్రమోషన్స్ ప్లస్ ఫ్యాకల్టీ ఇప్పుడు మళ్ళీ అడ్వర్టైజ్ చేశారు 125 అది చేయాలి డిపార్ట్మెంట్కి 10 మంది వస్తారు మా డిపార్ట్మెంట్ 10 మా డిపార్ట్మెంట్ అలాంటి ఇప్పుడు 11 మంది ఉన్నారు నెక్స్ట్ అకాడమిక్ ఇయర్ 10 మంది వస్తారు డిపార్ట్మెంట్స్ అంటే ప్లేస్మెంట్ పర్మనెంట్ కాదు ఇయర్ మళ్ళీ ఫ్రెష్గా అప్లై చేసుకోవాలి అప్లై చేసుకొని
మామూలుగా గవర్నమెంట్ వాటిలో కూడా 90% ఇవే ఉన్నాయి, 10% మన పర్మనెంట్ 90 దాకా ఎప్పుడు
రెండు సార్లు నోటిఫికేషన్ గవర్నమెంట్
ఫోటో తెస్తావా?
అట్లా వచ్చి పని చేసుకోవచ్చు. ఇక్కడ మీరు అంటే మస్ట్ నాట్ మ్యారేజ్ ఆప్షన్ ఇది పాజిటివ్స్ ఉన్నాయి. డిపార్ట్మెంట్ డిపార్ట్మెంట్లో డైరెక్ట్ మీరు ఏ ఫ్యాకల్టీ చేయాల్సి అప్పుడు డైరెక్ట్ ఆ సబ్జెక్ట్ గురించి పని చేయొచ్చు. దానికి కావాల్సింది ఏం చేయాలంటే నేను హాస్టల్ కంప్యూటర్స్ కూడా ఇస్తాను. వచ్చింది అదే మీరు అడ్రస్ చేసి డిపార్ట్మెంట్ వాళ్ళు రెండోది మాకు ల్యాబ్ చేశారు. చాలా మంచి ఎక్విప్మెంట్ ఉంది డిపార్ట్మెంట్ అక్కడ కూడా సేమ్ లేదు. డిపార్ట్మెంట్ ఎంత ఇండిపెండెంట్ అది చాలా దాని ఫండింగ్ సో అది డైరెక్ట్ ల్యాబ్ మా ల్యాబ్లో ఇంకోటి దాన్ని వీ హ్యావ్ స్టార్ట్స్ ఫ్యాక్టరీ స్టార్ట్అప్స్ ఆల్సో మీరు వచ్చి స్టార్ట్అప్ సో అప్పుడు ఏంటంటే అడ్వాంటేజ్ ఏంటంటే పార్ట్ టెస్ట్ మీకు ఏంటంటే చేసుకోవచ్చు మీరు ఇక్కడ కూడా చేసుకుంటే మీ సీనియర్ మీరు రీసెర్చ్ ఇంటర్న్షిప్ కంప్యూటింగ్ సైడ్ ఇప్పుడు చూపించాలా ఈ సెషన్ It's coming. Yeah. So, yeah, we'll continue the session now. Okay. So I was talking about some of the popular manufacturers actually. Then no, this is the one company where they come up with a lot of innovative products, particularly solar based. So they are the one of the pioneers in India. There are many companies also there, but this is a very Indian company based on Indore. So based on Indore, and now it's a multinational company. So they come up with a lot of innovative products with the solar DC, solar AC, and then in the innovations of submersible pumps and all. So we can see that a lot of specifications, technical specifications also related to MNR. So like that, each manufacturer they used to give that. So these are the good product links and all. If at all if you are working in this area, then if you want to wish to work it, then you can go to this catalog and then just see the specification. So this specification you can take it as input, and also you can take the guidelines from MNRE and then you can start the work for this water pumping application. So this is how you can start the work. So just we'll go down for the different items what is available. And this is surface motors available. Okay, different motors, solar based and that. Okay, so suction pumps and other things. So we'll go to the next tab actually. Here we can go to next tab. So where we can have energy calculator, we can keep one area, maybe we can keep the Hyderabad, maybe something, this is the area. You can select that actually. We'll select that area. Coming. Now, maybe you can go to, we can refresh, we will refresh the page. This is the one page, where we can see that how what kind of energy savings we can do if we switch out to solar actually. So now we can enter the location and then we can put the average bill, and then we can choose what kind of customer you are, residential, commercial, and industrial. Then we can see that what is the recommended solar system size that we require, and what is your current bill, what is your electricity bill after the solar installation. So that kind of mechanism is available here. And now what is your solar score also, that we can see what is the return on investments also. So what is the lifetime also. These are all things that is possible here. Look at it. So another, we can see another one. So this is another good one. So where this NREL, so National Renewable Energy Laboratories or Department of Energy, USA. So they come up with a lot of innovative technologies in this agri voltage systems and that. So nothing but solar agri PV systems here. So then we can see one short video. We go down. We go down. Yeah, this we can. Yeah, this we can keep on. Yeah, my system audio is on. We'll keep this. Yeah.
Energy with agriculture. And agriculture can be vegetable production, it can be pollinator habitat, it can also be pasture grasses that can support animal grazing.
This is how typically you see this now agrivoltaic systems actually in the field real applications.
Two different types of
So
pollinator
where
mixes.
they combine these ideas, concept is here. We can use the same land what we use for farming for the solar power generation, and also for the application mainly for farming applications. And again here we have different technologies are coming up in here, solar based only. Okay, so based on the what kind of farming that you do that actually. Even the technologies like transparent systems are coming up well, and then semi-transparent. Okay, many things are there. But it depends on what kind of farming that you do have. Maybe in the most of the US area they do for potatoes, and then broccoli. So those kind of fields are required less solar irradiation. So so that we can install the solar panels and then we can use that energy for solar this farming and water pumping, and then other beyond this energy application in the field actually. So those are the things people are really implementing for this practical applications. In this website, they mentioned very good case studies, and they also talked about a lot of benefits also, and challenges also they discussed in this website of NREL. This is a good one to refer it actually. So next is we have other one, that's the other source we have. So that is second. Yeah, these are benefits. So crop production we can increase and other things, and then how the agri voltaic systems looks like and all. So they are given some kind of case studies and all. So good one. And then what are the projects they are implementing with the different places and agencies? They referred it actually. So it is a good website actually. So not only for agri-voltaic, we need renewable energy application. That's a good source to refer it actually. And next one is this Inspire. So this is a very good website. They developed it actually for agri-voltaic map. So in this you can see that mapping. This is for USA. So in USA, so where we can see that what are the places where these agri PV systems are installed. So agri PV systems are installed here. So now you can look at this crop. You can see that the activities. So habitat, grazing, and then greenhouse or crop. Or we can see the what kind of solar technologies, monofascial and then biofascial, transient PV. So there are different technology, and also what is the size you can see, and what is the solar array, and based on that you can see. And in US, they have installed more than 589 sites. They installed the solar agri based system, and they have contributed to 10,000 megawatt of energy. So 10,000 megawatt of energy installed for the agriculture sector in the field itself, in the land itself. And then they spread to this 62,000 plus acres actually. So this how already they are well developed in this US actually. So they have given a very good map here, and we can scroll down for a lot of details. And they used to give this details of this a lot of projects where they are implemented. We'll go down this tab. Yeah, this is what they give this project name, and then where it is implemented, what is the size, and then when it is installed, what is the solar technology installed, and type of array, and next is whether is research is going on or not. So whether it's completed project, ongoing project like this. It's a complete database, and we can download the data also. If at all, if you are anybody working for agri PV systems and all, so it's an open source actually. So on the top also we can see. So they are. I think we'll go down and then come down. Yeah, these are open energy information data and resources. If anybody wanted to work on this agri voltaic systems and all, then we can freely download this data from this website actually. So the very good source is available to us actually. And then we'll go down quickly. And also if you want to contribute, there is a tab is given. So you can install. Suppose your newly plant is established, then we can entry our entry. We can make entry our entry. So that this is my plant established. We contributed this. We'll submit evidence. So they will make entry. So like this. So we go down quickly. And these are all different. I said 584 sites they installed it. So these are all records they're maintaining well. I think complete list is given in the same page. I think so. I think list. You can drag down. I think so. Okay, I think in this page, 584 sites information. Then we'll go to another one actually. So another tab. Yeah, we'll go to next one. Yeah. So this is another one actually. Is US department. They also promoting the agriculture department. They also promoting separately. The complete one actually. This is another one. I think this is. So they are given some good funded projects. They are increasing funded also for the research and all. So every year they are trying to increase it. So right now we can see that increment of funding in last years, it's more than almost like a triple to the previous year, 2021 actually. They are increasing their funding for this research and PV based agriculture system and all. So that is what I wanted to show you here. We'll go to next one. I think they're the same one. Yeah, they do a lot of activities and all. This so you can see lot of solar based farming and all. So this is what arrangement you can see. I'll also show some more pictures on it.
So here we see, sir, that panel angle inclined angle. That is almost vertical, not at all 45 degrees.
No, it's not more than it's about 60 plus. That means we are trying to define that wow, when you wanted to tap the energy, and then what is the amount of that energy to be utilized, like particularly for water pumping or something. Okay. Suppose the plants are required the water maybe early hours. Okay, then they they try to fill this solar panels accordingly. Yeah. Next. Yeah. So this is the last one. Where is that now? Okay. Now we'll minimize this tab and then we'll go to PPT. Yeah, PPT. Yeah, you can. Yes, you can slideshow. This is what we are talking about it. So far in previously, we discussed about the testing procedure for solar photovoltaic based water pumping system as per the guidelines of MNRE. And then next is we have also see the specifications of the solar panel, and then water pumping, water pump and controller systems and all that we have seen in detail. And also there are some leading manufacturing examples. Just now we have gone through some of the agencies where they are promoting this agri PV systems and all. And we can see for agri the solar, we can see a lot of good definitions and all. So ultimately here, we'll see that what way we are trying to synergize is both solar and then agriculture practices combined together. So that is important here. And we have a lot of advantages always here in terms of agri-economical environment point of view, and then socio-economical benefits also always we used to get it if you combine them. And we can see what are the solutions are required here. So generally, so one is PV installation should do that, and at the same time we need to provide that sustainable agriculture activity should, so that both should be co-located. So that's what always we have to see that solar and energy should be co-related, co-located, and at the same time light management also can be preferred, because all the plants or all the fields may not be acceptable for completely if we enclose with solar panels. That depends on what kind of farming or agriculture that we do that. So that's one here. And generally, the examples like solar serving as a shading for the barriers, verticals and abdominal, those things and that. And also greenhouses can be used for the other gardening horticulture purpose. Suppose generally they keep some kind of mats and all, green mats and all for horticulture purpose. But you can use some kind of transparent transparent sheets of the solar thin films also. So those can be used also greenhouses also. That way also you can use, you can incorporate this solar system there. That is also possible. And basically now here it's a combination of sustainable agriculture with renewable energy sources that we will try to bring the combined technologies of agri-voltaic systems now. So here we are trying to address the lot of global level challenges and society level challenges. One is population is increasing. So how do you meet this demand in the case of food supply? So that's one, and that too the healthy one, and food security, and at the same time extraction of fossil fuel. So directly here the agriculture sector is now fully dependent on this grid connected system. Now we can bring the renewable energy, we can try to reduce the burden from the grid, and at the same time water scarcity also is available. Now using the combination of these two technologies, we can solve this kind of global and societal based problems and all that we can do that. And history of this agri-voltaic or agri-PV system, when it was started. So it was started in 2011. Is one paper, So the author was mentioned first time in agri-voltaics. That the term he has brought it actually. The author name was Dupes actually. So he is the author actually. So now people are talking about these are the different names. You can see that actually in literature and everywhere. So agri photovoltaics, and then agro photovoltaics, solar sharing, agri solar, agri PV. So we can see other synonyms also for this day technology. So first time that was introduced in 2011 with the case. But actually, this already concept was emerged in 1986 itself. So that was the first authors, Gonsbergic and then Gustav. These two others was come up with solar energy production for the cultivating of this in agriculture and energy generation in the same place, in the same land. And applications, we can see there are different practical applications from the references actually. One is Raspberry farm. So Raspberry farm under elevated in agri PV systems. Now it's already located in Netherlands system. This is one application practical. They have laid out like this. And then another is permaculture and then horticulture application where they require a greenhouse. These greenhouses now we can use with solar transparent systems actually. Solar transparent sheets. So that is also possible here. And next is sheep grazing and then open field agri PV. Now wherever they sheep they try to grow them and now there is one where they bring this solar system. So another is wherever you have agriculture based buildings are there. So now those buildings also now we can build with solar based on those buildings and all. Then you can bring the more energy efficient there actually the buildings. Okay. So these are the application. And now coming to trending innovations now. So in these technologies now, so you can come up with reintroducing agriculture with the existing lot of large scale systems and all, so that we will try to bring the smaller system that is possible. And at the same time, dynamic agri supporting to the wine production and all. Now we can see these are the already we have some knowledge about single axis, dual axis. Similar kind of technology we can use this is here also. Whatever the solar panels are light down on the top, so we can try to tilt them and then make them a dynamic position. So accordingly, we can try to extract the energy also. That is also possible. And same thing, we can also try to make the shadow also. If your plants are required shadow, it will tilt also. Not only for energy generation, it will also apply for the dual application like this. And next is this is next generation of semi-transparent models. Now it is almost like a transparent. Okay, it's visible, but it's a semi-transparent. Like that kind of solar panels are now coming up well for this particular application actually. And now we can see two ways. Okay, solar panel, not only sunny. So we can also see other applications like if at all rainy season is there, we have cloudy and rainy season. Then this can be used for water harvesting and redistribution and increase the water availability because you have a slope instead of falling down directly going to earth and then getting into earth or something. And we can use this is a tilting of the solar panels. We can use them and we can try to harvest them and then you can store the water also. So that can be pumped to again plants also. So this is what we can do. This is a little significant, but still it will have impact. There is no doubt about it. And next is whenever you have a sun, then definitely we can try to produce the energy, and we can try to create a shade and reduce thermal and then radiation stress on the fields or plants. So generally these are the ways we can try to use solar for both cloudy and rainy, and then next is this is sunny also. And advantages, yes, we do have a lot of advantages, but primarily these are the one is we can reduce the competition from the land, from the use of land. Is it right? So now we can previously, we can one example like we can use 100% potatoes, and then we use 100% solar separately, and it's separate lands. Two separate lands are required. But whereas you can combine them on the same land, one place, then we can see that 103 percentage of potatoes and 83% of solar power. So which is like greater than 186 land usage efficiency that you get. So that means you are trying to do, reduce the land usage. So that way you can bring the competition for use of land. That's one thing you can bring, and you can protect the crops against the extreme weather conditions and all. Where we can see a lot of this condition in African countries and all. So where you can bring this technology, and of course in India also maybe Rajasthan, some places in part of Gujarat and all where you can do that. and reduce the evaporation, and then less water for irrigation required. Okay, wherever you have less water irrigation, then we can do this. And next is reduce the carbon footprint for the agriculture, because agriculture sector also sometimes it may not be directly but indirectly. Suppose wherever we use sometimes, mostly we use some kind of diesel based, energy for agriculture application where you require energy and all, for emergency water pumping and all. So we can try to avoid them such kind of fossil fuels based application, and you can bring the solar based, and then you can contribute this, solar carbon footprint and all. So that way you can bring it. This is another advantage. And fifth one is promote the preservation of the ecosystems and then biodiversity. And sixth, reduce the dependency of the fossil fuels. Just now we discussed it. And foster the welfare of the rural community sector. And we can create the job creation that we can do, because we are bringing the technology into agriculture, the solar based, and at the same time we can also increase the incomes. So whatever now farmers are getting the incomes from the agriculture, we can increase their incomes also through production, that we can do that. And next is new source of renewables from farmer and energy production. So not only they are not just using the energy for their own application, but they can pump that extra energy to the grid also. They can earn money also. So that way also they can generate the higher incomes in the compared to conventional way. That is another advantage. And also we directly contribute to SDGs, Sustainable Development Goals, as declared by UN, United States Nations actually. So one goal is, second one, that is no hunger, because the agriculture sector directly 100% we are target to no hunger, no this goal, SDG goal. And second one is, sixth one, clean water and sanitation, where we are directly coming working on the solar based water pumping systems and all. And next is affordable and clean energy, because we are bringing the solar technology for agriculture sector. And the 13th one is climate action. We directly also this agri-voltaic systems and all. We will try to mitigate the CO2 emissions and then greenhouse gas emissions also when compared to conventional situation. So these are the very, direct possible, targeted to the sustainable goal achievements and all. And we can classify the what kind of agri PV systems are available. Okay, so we can classify them like this. One is, structure wise. Okay, so one is we will bring the classification of open and closed. So where you have open, so interspace is there, overhead space is there. So there are two types of structures, mechanical structure you can do that. And here we can have fixed one axis, we have single axis, dual axis. So like that we can do. And here in closed way, so here we can say greenhouses we can build closed one. So another is, the upcave buildings. These are also both are fixed one, because there is no tilting. So once it is fixed as a houses like kind of arrangement. And these are the applications where we have greenland farming, farming, and these are all different, agricultural activities for crops, so gazing and heating. And then next is, this biodiversity PV, and beekeeping, so honey beekeeping, all these things different applications. Right? So this how we can classify this application wise also. And these are the challenges. Okay, the mainly now we will talk about these challenges, opportunities with this, agri PV systems now. So one is, identification of suitable crop pieces now. So now this is very much important starting one actually. First of all, you need to see where you want to bring the solar technology into agriculture. What kind of field, what kind of farming. So whether it is required, if it is required, what kind of structure is required, how much of energy is required. So what is the space is available. So if you bring that kind of technology, then how much of production of my field production can be improved. At the same time, what is the advantage if we bring in the solar? So all this kind of calculation we need to do. Suitably, we need to bring this technologies here. So accordingly, based on the cropping, based on the farming, so we need to select your PV system, because PV system arrangements and technologies are different to different. So different crop species and all. This is very much starting step, important starting step. That is, we need to analyze first. So that's always we have challenges. We cannot directly tell that this is a particular solar technology is meant for this. Okay, it's a very challenging. Okay. And second step is, development of novel PV systems and technologies here. So just now we have seen some of the technologies like, tilting, and then semi-transparent like that. So even some more technologies also coming up. I will share in the next slides now. So a lot of novel PV systems are coming up according to your suitable crop species or farming. So what kind of technology you need to identify and place them in the appropriate place. So that is another one. That is another challenge we have it actually. So and then next is modeling. So that means people now we come up with the modeling of PV system as well as modeling of this farming. So before implementing this PV system, agri PV system, so one can do this. Nowadays there are some kind of softwares also available. Even there are some softwares like PV systems now we can model with ANSYS and COMSOL like that. And similarly there are modeling system for farming also available. So now they are trying to combine this these two kind of software outputs and then see the complete modeling for the agri voltage systems and all. Okay. So both we can do that actually. So both renewable energy and plus sustainable agriculture we can together model them, and then finally you can see that what kind of technology we want to implement in the field. So once it implement, then we need to see performance assessment. Is it right? So now whether the system is working fine as per our desired conditions or not. So those things we need to see the performance assessment, analyze, we do that. And next is operation and maintenance. This is very much important. It's not simply we install there and then we leave it. It's not like that. So we need to see that what kind of operation you do as per the manufacturer specified, and maintenance also required. So solar also required the maintenance in terms of maybe if you have included with battery maintenance is required. At the same time, maybe solar panels, if at all any requirement is there, then we can see that. And next is legal frameworks for water. So right now is the government's also slowly coming with legal frameworks already well established in India for the solar water pumping system. Just now we also discussed in the detail. Similarly for this solar based solar agri systems also legal frameworks slowly coming up here. So some Western countries just now we discussed that US they already well developed it. So India also this slowly is coming up now actually. So we need to follow that actually. So legal frameworks and policies whatever. And finally, the success of these agri PV systems it depends on social action. Is it right? So we go to farmers and then we go to users now. So if you try to influence this PV system, then so they should accept it. So they should accept it because there are challenges. Challenges in terms first is we require high initial cost. It's not a free. So installation of PV system, even the government gives subsidy, but still it's a cost effective. I mean, it's not cost effective. So but someone has to bear the initial investment, high investment, and also we need to convince them with return on investment. So what is a return on investment? At the same time, how it will help them to increase their income. So apart from production, I mean also from the energy generation. So all this application we need to tell them actually. So completely this is the success of this agri system depends on what is the acceptance of the society. Like horticulture system, but it is a transparent. So you can sky is visible now. Whatever radiation is required to the plant from sun is already transmitting to this one. So now we get the same time we can also generate the power. So that generated power you can use for watering purpose or any other purpose also. So that's the advantage here, high reliability, and this is technology is mature technology is already available. So semi-transparent PV models are available in the market. This is one application, and this is only one disadvantage is this is so non-uniform light distribution. It's not a uniform distribution of the light actually because you can see here. So solar cells are there, here is not there. There's a disadvantage here. Maybe if your trees are falling here between them, then it's a non-uniform. So that's again disadvantage. And also it is a glass to glass and high weight. So transparent means is glass to glass. On the glass there is a thin film will be laid out actually. So that's another disadvantage here. So when coming to this technology, this is a thin film. Okay. So cadmium tellurium semi-transparent system. Now it looks like this. Maybe if you want to may put them some kind of a bees, okay, honey bees kind of thing, then this is a structure you need to have. And you can see this is a solar panel now you can heat similar to what we do have solar crystalline or something. And cadmium tellurium like this, they're semi-transparent now. So this will have uniform light distribution on the ground, but it has a lower efficiency, high cost, and lifetime. So this is a disadvantage of this sector. So this is a challenge here. And next third one is organic based PV system. So wherever you have organic farming and all, now this is a structure you can build it actually. But this is a advantage here, flexible, low weight, uniform light distribution is available here. But the disadvantage of this system is low efficiency and not commercially available yet. This is India also, and lifetime also it's again we need to recheck it. So it's not like what is the original plant that we do have. So original plant that we do have it nearly 20 years lifetime manufacturing. But this is lifetime, they cannot guarantee, I mean, more than 5 years or something. Okay, that's a challenging task here. So another one is, here, luminescent, this PV. So this is also another one. You can see that, greenhouse model one, this one, and this is also same one. This is the interior one actually. So where we have customized transparency is available, high reliability, also increase useful life for plant, but it's a high cost. Only commercial available in USA. So only the USA only available. No other countries having this technology. This is the one challenging task. And now you can see the semi-transparent here, another new novel technology, concentrating PV models using the Fresnel lens. So this is another one, actually, where you have a lens and diffuse light and then direct sunlight now. So now we can see diffuse light, if you come here, this is the direction, and if the direct sun, it will come here, this one. And less TV area is required, so that is one. And this is a dual axis tracking dish type. Okay, so beam filter it is having this type. So where this type generally we use solar, for a solar cooking application, and then solar thermal application. So same way we can bring this dual axis this type also we can bring for a farming application. That is one you can see. So that is one novel technology we can bring here this type. So this is another optical micro lens based technology here. So this again we can see efficiency will be 29% under the sunlight directly. So that is what we can do that. And no tracking systems is required. So whatever now energy required because of the optical micro PV cells, we can directly bring them to the energy usage. So this advantage here. So another new technology is flexible, lightweight PV models now. So this is meant for the integration to the greenhouse models actually. So wherever you have a greenhouse models are there, now you can bring this then lightweight flexible model. So we can try to make it tilt. So maybe some application where required tilting of the solar like a house kind of arrangement. So where we can bring this light PV models and all. And now I was talking about modeling actually. So now we can bring the modeling of both modeling of PV modeling and crop modeling. So now we have software separately, and there are some combined softwares also available now in view of the recent development. Now first one is starting is what is the first step of starting modeling. So what is the solar irrigation model? Where your farming is there. So what kind of location is there? So how much of energy you are generating average daily energy production in terms of kilowatt hour per day per meter square, that we need to bring that irrigation model. And then now what kind of shading scene that we required for the practical land scene. Okay, so whether you require plants are required, what kind of percentage of shading is required. So in terms of irrigation, that we need to see that. So that input will be given to your solar PV model. So then it will be given to the plane of the solar array, and then modular temperature will try to control them. And finally, you see whether your array is performing as per the shading conditions or not. So I require maybe temperature is this much temperature. So I will try to control the shading according to tilting of the solar panel and technology. And then finally, you will try to yield the energy production. So that energy will be supplied to whatever application, water farming, other auxiliary supplies and all. That way you can see. And similarly, one can model other side. So crop modeling here. So what is the irrigation required for the crops, and what kind of evaporation and then transmission and the soil water balancing is required, and finally what kind of crop management growth that we required as per the desired application, and then how the crop is yielding now. So now we can see the both yielding of the energy production as well as crop growth, and based on that we'll see the overall system performance, and then we will also calculate the economics, because already we are trying to we'll invest the solar, is it right? Now what kind of investment will come? So this solar inclusion, how it will help the plant management or growth and all. So how much of cost I can reduce on the operation of this farming. At the same time, how can I increase my income? Because other part also generating power. So using solar. So apart from the need of this crop, so over and above how much of energy I'm generating, and then I'm selling to the grid. So this is also important here. So we'll so far this is what we discussed it today. Okay, in the first session. So let me summarize to this now first morning session now actually. So mainly in the morning, in the beginning we have started with this energy demand and status. What is the status of in the country with reference to other countries, and because our energy demand is increasing based on the needs and the infrastructure increment in the country, and we have seen also what kind of developments and what kind of innovative technology that we need to bring for the energy generation in India. And at the same time, we also discussed that how renewable energy will contribute to this to meet the energy demand. Okay, so to address this climate change, global warming, and issues and that, and that's how we discussed it. And also we understood that renewable energy not only for power generation, we have other direct and indirect applications also. And particularly this renewable energy, if we talk about it, so solar, it has already very much successful. So in India we have 85,000 megawatt of energy already installed so far, and we have a target to 1 lakh megawatt then. And mainly that is 85,000. We have seen that ground mounted solar based application for directly grid connected system. And slowly right now it's coming up well for the domestic and residential customers now. So recent, government also, they have tried to popularize for this 1 crore solar households in this budget also. So like that is coming up. But we should see that solar applications not only for direct power generation, we should see other applications, particular other sectors also. So one popular potential application where you can find with agriculture sector now. So that's what main theme of this FDP also, and where we started understanding the application of PVs in the agriculture sector, how the agriculture PV system will take advantage, will bring the advantage in case of cropping, and then farming and all, and where we can try to bring this reduce the land use, at the same time we can also increase the production, increase the economics also. So that is what advantage we see. And directly also we are also contributing to these sustainable development goals declared by USA also. And we have a lot of challenges as discussed, okay, in terms of technical point of view, both PV and then cropping or farming also. And one has before choosing it, we have systematic approach. So as discussed then, so that is we discussed like yeah, this is important slide. So where we have a lot of challenges. Okay, so in the challenges, we need to identify what is the crops, and then what kind of PV system that we are trying to adopt it, and at the same time modeling. Before entering into practical deployment, then one has to verify that whether whether that model that you are choosing it, whether it is suitable for your application or not. Then we can judge by this modeling applications, and then we'll once it's installed, then we go with a performance assessment, and then finally we need to understand good understanding about operation maintenance also. And at the same time, all the time we need to follow the government regulations and policy to make this technology sustainable also. And ultimately the success of this kind of technologies, social acceptance, this is one of the main challenge to all of us actually. And this is what we discussed so far in the morning session. And if you have any questions, okay, I'm happy to answer that.
Dear participants, today's session number 1 is completed. So session number 2 starts now. That is at 12 o'clock. So it will continue from 12 o'clock to 1 o'clock. After that, we will take a lunch break from 1 o'clock to 1:30. Again, 1:30, sessions 2 are continued up to 3 o'clock. Okay, after that, 3 to 5, okay, 2 article discussions are there. That is 3 to 4, one article. So the 4 to 5, another article. Okay, so these are the small adjustments in the today's plan. Okay, thank you. So the second session starts now. So the first session, thank you sir for explaining the opportunities and the challenges of agri PV systems in the session number 1. Now the session number 2 starts now. The title of the session number 2 is Performance Indicators of a Agri PV Systems.
So we'll move to second section now. that is performance indicators of agri PV systems now. So right now, at this point, we understood, what is, agri PV systems and how it is installed, and what are the challenges, and then, opportunities. Okay. So now we will also continue with, the same line actually. So already we well understood about challenges. Okay, in the technical point of view, that is one. And at the same time, once the system is installed now, so we need to assess the system is, whether it is as per the, desired applications or not. So then we need to bring some kind of, performance index. Okay, so what way we'll try to performance index. At the same time, we need to see what kind of, opportunities also. So already we have seen that, solar system, agri PV system, what kind of, application that we receive. This is now I'm trying to bring some new concept here in the type of, opportunities now, microgrids now. So now people, now we talk about, solar actually. But in the future also where we can bring this wind energy technologies also. Wherever we have a small wind potential available. So now we can bring this, small wind technology combined with solar. Okay. So same microgrid or nanogrid technologies can be implemented for the same agriculture farming application. So this is what I'm bringing here now. So we are also good, blessed with, wind energy potential now. So I mean we have 50,000 megawatt is available right now, and we can see that, these are the maps. You can see that, a very good wind potential is available right now. Okay, and a lot of, places you can see these are red mark places, and then, uh, violet color one. So where you have good potential, and this is the map will tell you that power generation above the 50 meter, where you can generate the power 50 watt per 50-meter height, and then you can see that these are places where you can produce 200 watt per meter square. Okay, that we can do that, and we have potential of 50,000 and all. And we have some strategic locations. Already Government of India identified there are some strategic locations where we have very good wind potentials available. And we should understand what is the basic phenomena, how wind energy conversion will happen. So these are all, innovative ideas on where you can incorporate this, small wind technologies in combined with the solar also. That we can take as one of the opportunity where we can come new technologies with agri. Then future also we can talk about an agri PV wind technologies also. That way also we can come up well. And where this is one basic structure that we see have wind turbines actually. So we have wind turbine, we have pitch system, and then blades, rotor, and then gearbox, and then generator, and then anemometer will be there. And then complete this system will be called as a, necklace that will be top on the wind turbine. Okay. And then we have two controllers here. So air controller where we can try to control, you can try to take the direction of the wind turbine, and also you can do the fixed control by tilting the blades also. That also you can do that actually. So these are technologies with mechanical related technology. And here also we see that, a lot of wind turbines is available. Okay, sizing is increasing now. Right now we can try to get this. One single turbine can produce 15 megawatt of energy. We can produce it. So that kind of thing is available in the market. And we have generators like, synchronous generators, and then squirrel cage, W-fed, and permanent magnet generators are available. And based on the, kind of, power generation, whether you want fixed voltage, variable speed, fixed speed, and variable voltage, then based on that we can choose this generators and all. And like solar, here also we need to work on, MPPT, because different wind speed, and you will get a different power output. So and we need to track the maximum power here.
Sir, one doubt, sir. In the generation system, frequency speed is not at all constant. If we use the synchronous generator, how we get the speed?
One is, inherently, you will have gearbox. The first one is, you have a gearbox here. So this it will try to regulate your speed, and accordingly it will try to give the speed of this, generator speed. That is one mechanism is available. Okay, and second one is, here we have power electron converters which will regulate the voltage and frequency. Yeah. So two controllers will. One is mechanical point of view, is a gearbox. So another is you have power electronics. So two ways we can do that.
This is yeah, this is one fixed wind speed here. So where we have gearbox and then induction generator, where induction generators are capacitor bank for excitation. Otherwise, it will not be voltage buildup will not happen. It's similar to your DC motor excitation. Okay, DC generator excitation like that. And we have power electronics and connected to transformers and connected to grid. This one. And variable speed, if you have variable speed now, so W-fed induction generator, now your power electronics will come into picture of the rotor connection. So not the state. So now this advantage here, so your rotor power is less and so your frequency, slip frequency S into F, and your converter cost also will be reduced. And this converter rating also 30% of the rated power. Suppose this is 1 megawatt, but this is only 30% of the 1 megawatt rate. So cost also will increase. But only thing is the initial cost of this machine will increase than the conventional induction motor. So that is one a disadvantage. And we have permanent magnet synchronous generator PMSG and wound field synchronous generator also can be used here.
Sir, normally permanent magnets have the energy up to certain level, certain years. After that, the life will be reduced.
Yeah. Any technology, we market for lifetime is, some years. Is it right? Solar is 20, even wind technology is also 20 to 25 years life. So that is a life, even for vehicles also. Is it right? So we need to accept that maturity right now up to that years, as specified by the manufacturers. Any technology, it has its own lifespan, so that we need to agree. Nothing is permanent, life. So that is.
But normally in literature, in wind generation, similar induction motor is induction generator is used.
Yes, but it has a disadvantage two ways. One is it requires excitation. Okay, what happens is, as shown in the previous diagram. So this excitation, it will be provided through capacitor banks. Okay, suppose your plant is off for some hours, few hours. Okay, it's not operating. Maybe so wind and lot of storm, rainy season, whatever it is. Then what will happen is this capacitor will de-energize. Again, you need to charge the capacitor to give this reactive power to the this generator. So that is a one disadvantage. Okay, and second one is we need to operate this generator always above the synchronous speed. If it is 4-pole machine, synchronous speed is 1500. Then you need to run your generator. So above the synchronous speed maybe 1510, 15.8, 1512, something like. Okay, it is not beyond the 51 Hz. It is below 50 and 50.454, 50.2, 50.3 like that. Then that regulation again here required 50. Then your power electronics will take care of that. Even though you're generating this power, so above 50 Hz, okay, and your power electronics will take care of the frequency regulation that we can do. And the mechanism how it starts is generally first is you have a machine, okay, induction machine or any machine, DFIZ or a synchronous machine, whatever it is. Then first is we will try to operate this machine as a motor, because if you switch on this whatever the wind turbine form, then using this inertia of this wind speed and turbine, it won't be rotating your generator, because generator inertia is more compared to this this inertia. Then it won't help to rotate by itself actually. Then what we can do is firstly they operate they take the power from the grid and they run this machine as a motor first. They try to take it to nearly synchronous speed. This suppose you take the induction motor, so it will go to rated operating speed. So maybe 1500 is the synchronous speed, then 1480, you can go to 1480, 1485 speed. Then you can bring the speed and then operate the motor as a rated condition. Then you switch on your turbine. Then it will push it to above synchronous speed. Then once the moment it goes above synchronous speed, then automatically instead of drawing the power, you already established the lines. Then it will deliver the power to the grid. Same lines. So here you don't need to change any mechanism. So that observation you'll see that the power analyzer plus minus indication whether you are consuming the power and delivering the power. So that way the mechanism they used it in practical.
Sir, normally in the generators, we are not generating, we are not taking power. That is for the 14 energy. Is it possible in the induction generator?
Not possible. Not possible. Voting not possible. Huh? Yeah. I mean, I mean, not possible. Voting not possible. And this is what the arrangement generally. So we have a wind turbine, and we have a generator. We have a again, we will get a variable speed. First of all, variable speed that will try to mitigate this gearbox, and this gearbox will ratio will be like 1:3, 1:5 like that. And then you have here variable speed, variable voltage, and variable frequency that we have. Then we will do the grid generator side converter, that is AC to DC. Will do rectifier, and then we will have a DC link voltage and then inverter and connectivity. So here we implement this grid side, and here we implement power control, nothing but using MPPT control. And similarly here now we develop this WFET induction generator also, where we can bring this power electronic converter in the rotor set. Rotor power is less, frequency is less, and then this investment on power electronic converter is very much less compared again. So this is what here we call it in a full scale, whereas here this is a rotor set actually. And this is a permanent magnet, and this is a synchronous generator, same structure. So AC to DC and then DC to AC. So that way you see. And if you want go on increasing, then we can have more distributed one actually. Distributed storage we can implement. Now we have DC link option is there. Then you can connect a battery and then charge controller and then connect with DC link. So that way you can charge your store your energy into battery. Like that you can do that. It's possible. And at the same time, we can also think about centralized storage system. Instead of decentralized storage system, each farming is required, wind farm is required one battery. That we can eliminate and then bring so one centralized large energy storage system also we can bring that. So that is also possible here. And DFIG also similar way you can do. You can have a modular. Maybe this plant is 1 megawatt, and then you can add another 1 megawatt. Like that we can add to modular way like solar, what we discussed in previous session. And solar converters full scale. This is a full scale because these two converters are connected directly state. Suppose this generator is 1 megawatt, so these converters also should be having minimum 1 megawatt capacity rating. So that what is a full scale converters that we require here. So now these wind farms also can be application we can use for DC HVDC links also. Because region to region, one region to another region, if you want to have interconnection, then you can use this variable power generation. Now we can connect it to other region, and we can connect it to region also. That is also we can do that. And now people are talking about solid state transformers, where we can try to eliminate this conventional transformers for the grid integration or the regional interconnection. Then you can bring this solid state transformer, that is AC to DC and then DC to AC. That is also possible. But here application is HVDC, that's why DC to AC and then AC to DC. And finally, the conclusion in the wind farms actually. So now, if you have a multi-stage scale, then it is now we should assume that that is we are having high-speed generators. So when you have high-speed generators, then you will have multi-stage gauge system that is required. And when you have this one-stage gauge system, then you have medium speed. So medium speed means these are all kilowatt generators. Kilowatt generators and all, then we use one gauge system. So gauge ratio will be fixed as per the manufacturer. And here we have provision will be there. And in the market we have now electronic gauge systems also available. So according to the speed of the rotor, we have multi-stage. Then accordingly the electronic gauge system also will tune to that ratio also will be chosen. That kind of arrangements also available. And there are direct driven system, low speed generators. So suppose there are domestic applications, residential application, where you have a rooftop. Even I am going to talk about this a small wind for the agriculture application also. So where we don't require any gearbox system, so directly you can take this permanent magnet generators now. So without any gearbox, directly you can connect it to the wind turbine. So whatever you get the variable power, variable voltage, so you can have an AC to DC converter, and then you can store the power into battery. So through battery again you invert it through inverter DC to AC and then connect it to loads. Okay, so that kind of arrangement we can do for direct drive with low speed for domestic or residential applications. And instead of going with the multi conversions, AC to DC and then DC to AC, then one can go with directly AC to AC conversion using matrix kind of conversion. That where we can get variable voltage, variable frequency, then we can convert it to fixed voltage, fixed frequency. So that kind of topologies also one can think about it actually. And typically this is what the scenario of wind generators, wind power generation system. Here we have options here, but whereas solar we have different technologies, so like that. So here also we have different generator based on your application and size of the system. So we need to choose the generator here, and gearbox is optional, but small scale system not required, but large scale system, medium scale system, gearbox is compulsory. And then AC to DC we do that, and DC to AC inverter and then filter connected to here. So in case of WFET, you have this line will be there where rotor will be also connected to, and you have 3 winding transformers you should use it. Okay, in case of WFET. And here we do the voltage and current control, DC link control, because we need to get constant voltage, constant frequency, grid synchronization because we are connected to grid. And power maximization, we will do the apply the MPPT here, and fault right to grid support with reference to this grid. And the energy emulation here, wind turbine you are using it here, and the energy storage, because the wind will be almost like 24 hours, then we need to store the energy. So like this, power quality issues, these are all we need to control and then monitor them. And another application where we can think about in renewable energy perspective, that is bioenergy also. Okay, in farming, agriculture, because agriculture it's a major sector, it's giving the bio. Okay, in India also, is it right? Everywhere. So why can't you think that bioenergy also one kind of energy resource for this energy for the agriculture sector. So that is also. Now you can think about the applications like you have a solar, you have small scale wind, you have a biomass, bioenergy technology also. So that way you can bring some kind of hybrid energy system for one sector agriculture in the same place, in the same land. Okay, beyond it's a solar, and one is energy we can form, we can get this energy. One is gasified form. That means ultimate output from bioenergy can be biogas or producer gas. And next is liquid, I mean ethanol and then methanol and biofuels that we will get it. And then next is solid fuels also, that we can get the output of the biofuel, that is also possible. And now we have systematic routes will be there where you have what kind of feed that you are giving as input to the biocase, and then you follow some certain conversion routes. Okay, whether you wanted to gasifier or whether you wanted to liquid, whether you want to fuel solid fuels and all. So accordingly you choose that path. Okay, and we have different stocks are there. One is we can classify them stocks, feedstock, bio waste, there is organic waste, and then sewage sludge and manure, and then processing residues and all. And where you have some kind of where processing industry are there, some byproducts will come. So there are all processing residues, you will collect them. And then locally collected feedstocks from agriculture, forestry, and then energy crops and all. And next is internationally traded feedstocks will be there, where we try to buy them. So that is a trade products will be there. Okay, so you can use them for energy generation, that is certainly. And we have this, we definitely we can claim a sustainable solution, because we are trying to address the energy challenges and social challenges, economic challenges, environmental challenges also. So these are like solar and solar. Similarly, we can impact more also. And how we can generate the power. So now this is one thing. What kind of components are required for bio energy generation in case of agriculture application? Now we can see biomass, gasifier is required, intake, fuel, mixer system, gas flow and measuring system, air measurement system, and then you have engine, generator and loads. So you can see this broad diagram. So we have airflow here. So this is measurement, and you have gasifier here. So now this biogasifier now output will be sent to your engine in the form of producer gas. Okay, and this engine will drive this your generators. Now you can connect the generator, single phase generator or 3-phase generator based on your application of loads. Okay, we can use here synchronous generator, or you can use induction generator also. Both are possible. And same picture is detailed, it is given here. So you have biomass, gasifier, then generator, you have loads here. And the AVR will be there, also automatic voltage regulator will be there to maintain the engine speed is constant, and at the same time we'll try to control the output of the generator also. So that is AVR control will be there. And this is what I did the work in this 2013 I did it actually as part of my PhD. So I did this. I contributed one chapter actually. So where we have this fruit petals and leaf petals actually. And ideally lot of leaves summer we find out. We try to capture them and collect them, and then we make petals, and then these are wood petals actually, wood petals and all. Then we put them into this biogasifier is available in the campus actually. We put them in the energy resource, and then we have three nozzles for the biogasifier. We tested for one nozzle fire, two nozzle fire, and three nozzle fire, and we need to see the what is the optimal input flow for this nozzle fire. So that we need to analyze this. So once it is fixed that, then now we can see this the engine. So this bio engine is now connected to this generator. So this generator I have designed specially, it's novel generator. Okay, and it's a single phase 5.5 kilowatt. Okay, nowhere is available. So generally you will find a single phase motor, motor itself 2.2 kilowatt you will find. So beyond 2.2 kilowatt you will go with three phase because of losses. Okay, so major application we see air conditioning, not more than that, not more than that. But here this I have designed this generator 5.5 kilowatt single phase, it's induction generator. Okay, that is I have designed it. And then is we connected this specially designed generator with this bio engine, and where we see the energy of the goods. So this is induction generator, but here the challenge is we have to run this generator above synchronous speed. Okay, so who will run that? So your engine will run. So engine speed we need to maintain. So one is we have, of course we have controller, but at the same time, so you have input flow that should maintain your engine speed above synchronous speed always. Okay.
Biogas, is it steam based or
Gas based. Gas. Producer gas. Okay. How much? Pressure I don't remember. Okay. Yeah.
which gas that air heat that will be blow on the normal biogas?
Yeah, it's a producer gas, but it is visible. I mean, it's on visible spectrum only. Okay. Yeah, but we need to see that what is the calorific value of that producer gas. Okay, so again, what is the mixer? Again, if you mix these two, or if you again these petals, even if you make small size, these petals if you make in a larger size, that will also impact this producer gas output. Okay, every input we need to calculate what is the calorific value of energy input. Okay, similarly, what we calculate, petrol bunks and calorific value of petrol or diesel. Similarly, here also we need to do that exercise. And finally, we come with the optimization. This is the combination best suitable for producing more energy from this input combination that will be fed to this one. Before that, we have done that all the exercise. Finally, this is the conclusion. Huh? Sorry? Better generation, I don't remember exact the value, but is uh, between 60 to 70 something like 60 to 70. But again, we compared this value with conventional diesel generator system, because the same application, we propose for rural application, agriculture application only, and then we replace with the synchronous generator with the diesel genset. So that is already available in the market, is it right? Then we compare this performance with the conventional DC generator system also. So that way we try to come up with some outcome, more efficiency at the same time less cost when compared to this. Because the diesel cost is incurred, but whereas here these are almost like free cost. So that's the advantage. Input is free cost. Right? And similarly, this can be adapted to the farming also, where we have in the same farm, farming, so their residues will be there. They don't need to buy it, from outside. So whatever feedstocks are required for power generation, they collect from their own farming, their own agriculture land also. Then it's a free of cost for them actually. So,
Leaf credits is there.
leaf.
Leaf would bring
Leaves, and then we try to crush them, and then we make the powder. So that powder will be converted into these petals like chalk piece kind of thing actually.
Small
So,
size.
small size. Yeah.
So 1 kg wood and 1 kg leaf.
Yeah.
Like that we mix.
We didn't mix it actually. We tested for separate. Separate.
So then we combine.
Yes. Then we found, I mean, of course, we will get a more energy from wood petals because these doesn't have much calorific value of these leaf petals actually. So wood petals have more actually. But another point is, a sustainable thing now to talk about it. So burning. Okay. So that is again, by what we trying to see that. So using burning, you will try to produce the ash also. So we need to provide a solution, alternative solution for ash usage. That ash will be again converted into some bricks, something like. So that kind of other sustainable solution we need to think about.
Last we put in the smoke.
Smoke also. Yeah. Yeah, that's what we need to analyze that, whether you are achieving this, complete zero cycle solution or not. Okay. Even for solar and wind also, even manufacturing stage, they emit emissions. Is it right? So like, yeah. So then, what we can do is, once we understand the solar and wind and bio, then we can try to combine them as a microgrid. So now we can think the solution of, for agriculture, solar, we have a small wind, we have bio. So now we can form a microgrid application where we have combined, cluster of loads, distribution generation unit like solar, wind, bio, and then you can have energy storage systems also in coordination with reliably supply electricity connected to host parts. That means you can have provision to connect to the grid. So earlier also solar we discussed that we can have grid connection system also. But only point is, this grid connection or a connection to the host power system, we should do at distribution level. Okay, not at the other level. I mean, high power level. So distribution, what is the distribution in case of us? So three phase 450. So three phase 450 you should do. In case of single phase, 230 50 years. So that point is called as a PCC, point of common coupling. Okay, very popular term in literature. And we have clear definition from IEEE also. A microgrid consists of group of interconnected loads, DERs, with clearly defined electrical boundaries. Very important. That means wherever you are trying to establish, we should know what is your electrical boundaries. That means what is how much of power is generating solar, how much of power is generating wind, and then load. That means generating. At the same time, loads also you need to decide. So ultimately, so that means you need to define whether you are achieving energy balance or not. So this energy balance will declare that what is your electrical boundaries and which can be operated as single standalone controllable entity, and it can be operated in either grid connected or grid isolated mode. That is nothing but in off grid mode. So that means ultimately it is single standalone controllable entity. And we can see that three types we can make. So one is AC microwave. So your ultimate output is AC. Is it right? So whether whatever source you have, and then you have whatever power electronics you have, and finally you have to bring AC output at the end. So you can connect to loads or you can connect to grid. And second one is DC microgrids. Okay, DC microgrids again. So ultimate output is DC. Again you have different loads. I mean different generation, but still your output is DC. And next is hybrid microgrid now. So here you have both combination AC and DC. Okay, both combinations possible. And you can operate these microgrids like in a grid connected, a grid isolated, and at the same time you can make a transition. Suppose if a microgrid is operating grid connected mode, then you can switch over to off grid mode. Then if it is operating off grid mode, then you can switch over to grid mode. That is also possible. So we can define as per IEEE standard 2030.7 what is a microgrid control system. So a system that includes a micro control function that defines microgrid as a system that can manage itself. This is one feature. Right? So whatever if you want to develop the control system, so it should manage itself, operate autonomously, and control and disconnect from the grid. So mainly these three features should have it. And for exchange of the power and supply of ancillary service, nothing but reactive power particularly. So if the microgrid requires reactive power, ancillary service required, and your voltage and frequency control. This comes under ancillary service again, and which includes the function of microgrid energy management. If it is a microgrid controller, if it is implemented in centralized system. So ideally, as per standard, so you need to build a centralized form on. But people are now coming with now different ideas, decentralized also, distribution control also. That is also possible. Now this is some good diagram we can understand better here. So now let us assume that this is a microgrid now. So you have a transformer here, you have circuit breaker here. So this is a bus bar here, AC distribution level. You have different feeders, feeder A, feeder B, feeder C. So feeder A, now you can see these are loads, arrows. And you can have, this is one solar system, this is maybe another wind system, this is energy storage system. Each generating system will have its own microcontroller. Nothing but microsource controller with power electronics. Solar itself will have power electronic AC, DC to DC and then inverter. Similarly, wind also AC to DC and then DC to AC. And energy storage devices, nothing but DC DC charge controller and then inverter like that. And you have circuit breakers, cross section of circuit breakers are there. So a total A feeder can be disconnected by opening the circuit breaker 1. And similarly, circuit breaker B, there is no generating source. Okay, and C, so will be connected through CB3, circuit breaker 3. These are loads, these are sources actually. Now we have one centralized controller, that is CC. Now, one operation is, this is a complete microgrid which can self-sustainable. It can run its own. If it even if you disconnect CB4, is it right? Then it will operate in grid isolated or off grid mode. If you want a grid connected mode, you close the circuit breaker. That's it. And next is if you don't get power from the grid to the feeder B, feeder B also can get power from either feeder A or feeder C. That is also possible. Is it right? So that way you can have it actually. So this is AC microgrid structure where you have a solar, so wind turbine and then battery. Suitably you can connect to filter, power electronics filter and then connect it to this common AC bus bar at distribution level, that's called PCC, where you have connection to establish a connection to grid. Okay, and then you have loads. So this is what ultimate output is here AC only. So distribution level. And this is a microgrid one can build it. So now we have multiple sources. We can consider solar, wind, fuel cell, and then battery and conventional grid also. Then we can create one common DC bus bar. Okay, maybe 400 voltage DC bus bar or something. Now we can create but here the disadvantage of DC microgrid. Each DC load has different voltage levels. Is it right? So now you look at our own applications like mobile phone, printer, charger, laptop, desktop. Is it right? So even batteries, EV batteries, everyone, every equipment or device, so it will have its own DC voltage required. Now we need to classify. That means we need to bring its own DC converter here. Then we can simply classify them if possible. One is high voltage DC bus. You can establish by charge controller. This is DC to DC, and then it is meant for traction and industrial application. Now we can have a medium voltage now. So now one converter. So data centers, EV charging, HVAC, water pumping, but maybe some same voltage. Okay, or if at all these systems have inbuilt DC-DC converter, from which again they will do another conversion. Low level, again DC-DC. Like. And then low consumable loads, again lighting applications are. Maybe you can depend on low voltage DC bus bar. You can convert them, you can bring them through this DC-DC converter. So now we can establish the communication also, and then you can build one smart controller. And this is hybrid now, where you can see that now two bus bar. One is common DC bus bar and then AC bus bar also. Now, if at all, if you have DC loads, suitably with connection of DC to DC converter, you connect it to DC load. And next is if you want AC loads, you use inverter and then connect to AC load. So that way you can bring here both DC and AC loads in a single platform, that is hybrid microgrids. And energy management, yes, we have as said just now. One is centralized. Okay, so that means it will try to connect all the information from different sources and load. It will come to one server node, one common node. So there we will perform your task and take this controllable action to that particular place. Maybe power electron. Suppose you want to control voltage and current, then it is directly dealing with power electronics only. You are dealing with power electronics. So like that. So this is centralized. So another one is decentralized here. So decentralized here, you will create some kind of super node, maybe related to one is related to one generating sources, another is related to loads, another is related to control point of view. Then you will try to decentralize, and then among them you will have established linkages between them, communication linkage. And last one is distributed now. This is getting very popular nowadays actually. So any feed can be connected to any feed. So directly, indirectly. So that way connection is available here. Right? So more all are trending, but these two are getting now very popular now, decentralized and distributed now. And the challenging task with the renewable, always, when the frequency go down, your active power deficit. Okay. So with the active power, whenever the active power deficit is there, then what is the thing? Say a frequency goes. Suppose you have if your power generation active power is less power than the rated whatever desired one, frequency will go down less than 58. Then if the active power is surplus, then what will happen if frequency goes above 58? So this is what you get. So because this generally in case of grid connection we don't face this problem because it's connected to grid. Now grid will maintain that stability in point of active power control. So we don't need to do that actually. But in case of standalone mode, so these are the challenges with the frequency control in grid connect. I mean microgrid. And here that's what I was talking. So voltage regulation, grid connected mode, generators will do that. So we don't need to follow that actually. Grid will take care, and frequency also. But here in islanding mode or off-grid mode, your generators are completely responsible for it. So generators then one point is we can do multiple stages. We can do the voltage regulation of frequency. One is fuel control. We'll do the fuel control, whatever possible you can do, we can do that. That's one stage. And next is generator control. So generator, maybe generator speed we can control and we can regulate the voltage and frequency. That is another one. Third stage is we will do with the power electronics. So we can do with the 3 stages that we can do that. And similarly frequency also. Reactive power, here we don't need to take care. So if any load is required reactive power, then your grid will support that. But whereas here in islanding mode, grid is absent, then exactly your generators we need to supply. Suppose wind generator is there, it is capable to give reactive power. Then we should take from reactive power from it. Okay. And other faults also islanding operation is different from grid operation. And overall, we need to perform control actions at different stages in microgrid. Suppose if you are trying to combine them, different sources like solar, wind, and bio, and even other sources and loads and all. Then we have these are the controllable actions we need to perform. So one is device level. So device level means directly you are dealing with equipment devices. Okay, they may be generators or power electronics or loads. Is it right? Then we can do this voltage and frequency control. Directly we will deal with power electronics. And then current and power control, power electronics. Reactive power control. Using power electronics we do that. Generation control. That again we do that with on generator. So load control and energy storage control with the battery. Islanding detection, fault detection, protection. These are all control functions we deal with device level. So mainly power electronics engineers will do that actually. And next control area is local area. So load management, energy management, automatic voltage regulation, that is AG is very popular. And then fast load scheduling, and disconnection, desynchronization, disturbance recording, all these things in local area. So that means it's within the system, but it's a control action structure. Okay, your controller will do that. So mostly this power electronic, beyond power system engineers will work on this. And next is supervisory control. It's beyond our microgrid setup. So that means you are trying to establish a connection with the microgrid with something else, maybe utility company, or with one microgrid to another microgrid, like that. Then where we can do generation, load dispatch, optimization, spinning reverse, and then reconfiguration, black start. Whenever you suppose your complete energy is 0, okay, then we will depend on renewable energy to start your system again. So it's from 0. So your solar and wind help there. And next is production coordination, forecasting, data management, visualization. They all comes under supervisory control. So beyond that, another control is the grid interactive control, that is related to markets, interaction, and SCADA systems. So where we will try to come to trading. So mostly with the trading, electricity market sector. So these are the areas where we can contribute actually in the microgrid sector. So that way you can see the challenges if you are operating combining with the different sources and forming a microgrid for a particular application, whether it's agriculture or any other application, then you have different control actions that you need to perform, different stages. And we have good standards now. I recently, say earlier, we don't have standard with reference to smart grid actually, or this microgrid. In 2018, they bring one standard of DER interconnection and smart inverters actually. So this standard will talk about this interconnection between distribution energy resources and power system. So we have power system grid, we have distribution, solar, wind, other thing. So earlier standard was talking about only power interface between them. How do you link to grid? That means you can operate with grid connected, grid off grid mode. But this new standard will talk about communication interface. Okay, so that's what in starting also I said. So nowadays, along with the power flow, we need to also understand communication interface also, or data interface also. And at the same time, we need to understand other standard 2003. So IEEE, sorry, same one, previous one, IEEE 1547 2003 standard. So that doesn't talk about this dynamic support requirements and DER actually. But in 2018, it's really clearly mentioned, about dynamic voltage support. By supplying this or observing reactive power by doing under voltage and over voltage events actually. Okay, what you do generally, if you have under voltage conditions are there, what you do? So you need to supply the reactive. If it is over voltage condition, then what you do? You have to observe the reactive. So then this is already known phenomena, but this is not recorded as a standard. So the first time they brought it in this standard amendment in 2018 actually as part of it. Then they talked about how to stabilize this local voltage generally, because we are working at the distribution level. And 2014 also another important standard revised is amended in 2019, IEEE for 1519 harmonics. People we work on PhDs now by the measurement to analyze the performance of our system. See your bus voltage at PCC distribution level, if the voltage is less than 1 kVA, so your total harmonics is percentage should be 8%. So earlier it was 5%. So now it was relaxed to 8%. That's one thing we should know. But individual harmonic is 5%. By your bus voltage is 1 to 69 kV, then your total harmonic discharge should be 5%. Your bus voltage is 69 to 161, then 2.5. And if you go in high voltage, then your total harmonic discharge should be come down. So that way it is given. But current distortion is same. Okay, if the short circuit ratio to the load voltage, then that ratio if it is less than 20, your TDD is should be less than 5. So there is no change in current TSD, but there is a change in voltage TSD. Okay, so if you are trying to climb this TSD in your system, voltage TSD, see if the bus voltage, whatever output voltage, I think most of us we work with operating voltage, distribution voltage is on. Then we should see that 8%. Which one? It is an individual harmonic. That individual harmonic content. No, it is a cumulative, because sometimes we try to see that other harmonics also. I mean third harmonic, if it is option, then fifth, seventh, and up. Okay, but it is individual actually. If you're trying to point out one particular, not every individual. Yes. If it is every individual, then it won't be 8, no? It will less than 5 or maximum 5 1. I mean, for particular application, if you want to dominant harmonic fifth harmonic, then your dominant fifth harmonic should be 5%. That is the target you should take. In case of your voltage is less than 1 kV. Then voltage flickers also they defined it actually. IEEE 1547 they declared that actually your flow voltage flickers should be medium voltage, high voltages 0.6 to 0.8 and then 0.7 to 0.9 respectively. So this is given. And current harmonics, yes, this is less than 5. UK IEC standard, this is less than 5 only. And UK standard that is less than 3. They maintain. I think yeah. In in the previous session also in the morning, we have seen that current harmonics also this is a voltage, but they are given 3%. Is it remember? Here morning also we have seen that voltage and current harmonics should be less than 3% for solar water pumping system. So based on this only they are given individual harmonic 3%, but whereas standards will tell us less than 5%. IEEE has relaxed it recently 2018 to 8%. And we have good summary also by NREL, so IEEE 1547 and 2030 application that we can read it. And then these are series of standards. Okay, they talk about interconnection between different sources, and then how to design operation, and then with the battery connection, all these things. They come up with a different serial numbers actually. So this is a good standard for the this renewable energy integration with the grid and then hybridization also. Similarly, smart grid also is a good one. Now we can see some extension to this actually, because once you're trying to establish this kind of a hybrid system, then we need to see that what kind of interconnection we were giving with the grid connection. Okay, because communication is required. So nowadays the smart grids are going to help us actually. These are emerging now. So we can see that some of summary of this. What are the applications of the smart grid now? So we can directly help to address the problem of future energy demand as discussed in the morning. And smartly, how do you tackle the problems of climate change and global warming issues? And then how we can smart grid will help penetration of high renewable energy and microgrids establishment. And then how do you integration of this electric vehicles into the system also? And of course, our aim is to bring into electrical system sector with high efficiency, reliability, and stability also. And finally, as a consumer, everyone, any stage from starting with generation to utility, we need to see that to minimize our cost also. Okay, and it definitely going to use computational communication technology. And one line we can define it's going to be end-to-end cyber enabled electrical power system. Okay, so that means any stage we can implement this smart technologies, say end-to-end. And these are the major benefits. You can see that one is we can integrate them renewable energy, and we can help to decarbonize the power system, and we can allow reliable and secure two-way power transmission and communication or information. Already we know that information and communication is two-way. That is we know that. But power, so how it is? Anyone can tell? How it is? Power is bidirectional or two-way? Huh? Sorry? Not communication. I am talking about powerful only. Not communication. Communication is bidirectional, that we know. Okay, but power also can be bidirectional.
Induction generator. We should take the power as induction motor for operation. Later we should use that power. So we need the bidirectional power.
Yeah. Okay.
That's solar also sometimes the power is not there. At the time we want to start the batteries, we need the power. So the solar power is more.
Yeah. Yeah. So this bidirectional will happen, using power electronics. That's what he is mentioning. Sir is mentioning about applications actually. So in this applications, you need to incorporate bidirectional power electronic converter. Then we can supply the power as well as we can consume the power also. Okay, that's one. And that means already direct. We can see. Battery. So already we have very good example in our home. Home EPS system is there. So we will charge the battery, and then we discharge the battery. So bidirectional is happening already. So similar way you can think about it. And at the same time, two-way also with related to grid connection, where you consume the power from the grid. At the same time, we also pump to the power to the grid. You may be using solar, using the battery or any other source. That is also bidirectional. That is also possible. So using power electronics and the battery, so now we can bring this two-way power flow also. Okay. And now is other advantage is we can enable the energy efficiency, effective energy demand we can do, and customer choice. Right now we don't have any customer choice, but in future we may have some kind of customer choice. Okay, right now it's very difficult to implement in Indian scenario. So maybe every locality, every place is connected to one distribution agency. Maybe this line is maybe connected to southern and eastern. This place. Southern. This place is connected to Southern Distribution Agency. So my place is connected to Eastern Distribution Company. So now we don't need to other charge like mobile or TVs. We have other different players are there. Wherever who are offering the best prices or package, I'll switch over to other one. But here in electricity, we don't have a choice. But the choice may come even if the inclusion of this energy trading if that happens. That is also we'll see. And next is it provides a self-healing and then from the power distribution attack and operate resiliently against cyber intelligence. Since we have cyber intelligence, we may have cyber attacks also. We'll try to mitigate that.
Sir, is there any system to maintain good power quality in micro?
There is no system. I mean, practically whatever solution, but only that's through power electronics.
That's the reason.
Fact devices. Fact devices. And you can see the application same. I think we have seen a lot of applications with fact device application with renewable energy. Even solar with StatCom, that is available.
What are the problems?
Microgrid is voltage and frequency regulation. The main problems because it's isolated from grid, and your input is varying. Okay, intermittent nature of sources, solar and wind. So voltage and frequency will vary. So that's the main problem. And at the same time, another problem is reactive power also not problem because when you try to establish this microgrid setup or a renewable energy base, first of all the first step is we need to see what kind of system that we want to establish. Suppose first point is loads. Suppose for example you take your college is the case study. You want to include here renewable energy, whether it's solar, wind, whatever, bio or whatever. First is what is your loads, load pattern. Okay, what is the load pattern? What is the load profile? And then we need to see what is the average load and peak load. Okay, and then what is the maximum load? And then that is again working days, weekdays, all days. Is it right? So then we need to calculate what is the energy demand. Then we will also compare with your conventional electricity board bill, how much you are consuming at all. Then you will understand your energy consumption or everything. Then you propose what to be added to your your system. Okay, suppose you want 100 kilowatt of energy you are consuming as a peak load. Then whether you wanted to install 100 kilowatt directly, is it right? Then you should see that what is optimized mapping that we need to see. Then what is the combination again? If it is you want to choosing two systems, solar and wind, then solar how much, winds how much, and battery how much. Battery is compulsory again. So this kind of sizing we have to do. So this sizing we'll do in the modeling stage actually, first thing. And then finally, we need to see that energy balance will happen at any stage of operation, any condition of operation. Okay, already load profile is there. So irrespective of any point of load profile, so you should see the energy balance in the system. That will occur with maybe a storage or grid connection. Okay, we'll take a help of battery or grid connection and energy balance should come. So that way you do that.
Nonetheless, based on which one we want to design, sir, on base load or peak load?
Base load only, maybe. Generally base load. We go with the base load. Okay.
Based on the base load, we want to.
But we need to see what is the peak load impact also. Peak load, how much hours? That is also another issue. If the peak load is not, severe, in terms of hours, operation hours, then we can go with the base load. Okay. Because we cannot sometimes we cannot completely rely on the renewable energy because new technologies and whether it will operate or not. Okay, because of that depends on weather conditions, geographical condition. Then we cannot disconnect immediately from the grid. Suppose I am bringing one solar system to the college today, then whether I can disconnect from grid, no. So I will not disconnect. So I will see the advantage. Then I see the performance of the solar, and in terms of both technical and economics. And then in future I may disconnect. I can disconnect from the grid. So that way, electrical. Sorry. Yes, electrical boundaries. Yes. Yeah. That's what previously also we discussed. We need to understand what is your electrical boundaries. Actually. Okay. This is one example where end consumers also as part of the smart grid. Even this is also directly applicable for your agri solar PV application. So already we have seen that solar the farmers also can generate the income, high income for generating power also, they can feed the power to the grid. So what they can do is now that point, so assuming that there is a condition is peak time usage is there, then you can generate the power, even residential condition, agriculture condition, then you can sell the power to the grid and you can earn money. This is possible, is it right? Okay, but only condition, we should have a dynamic pricing in the system. Okay, right now we don't have dynamic condition. This is static, is it right? All the customers are divided as per the electricity boards. You have domestic customers. So again in domestic, again they classified A, B, C, and A is less than, your consumption is less than 100, less than 50. Then your band is 100 to 200. Your band is this. Again they fix the slabs. So each slab has a price. Is it right? And then again commercial. So this institute will come under commercial. So this I think they charge 9 rupees or 8 rupees. 15 rupees, like that. So more than 10. So like that. So like that. Okay. But our institute, I think government they charge less. I think so 9 rupees. I think.
Only charging 50 rupees, sir.
Ah.
But we are purchasing solar power. It's costing 6.9 rupees.
Okay. Great.
Okay.
So yeah. Yeah. So I was talking about the pricing. So dynamic pricing, we should enable this feature actually. Then you will get it. It's similar to example like in a share market also. You see, so whenever the share price is less, then what you do is we'll try the more shares. When the share price is high, then we'll try to sell my share and then get the profit. Okay, like even sometimes we can do average also. So like if you are buying the share at the high price, 100 rupees a share, and then next time it will come down to 50 rupees or something. But earlier you lost. Then you buy more shares now at low price and then make it average high. Then you can gain some profit again. So that way. Similarly, you can do with the electricity markets also. This is also possible. Smart grid, now you have more information you can get from this website actually. You can register here with email, you will get continuous update. And we have one association like International Smart Grid Action Network is available. So we'll get a lot of inputs and data also available here. That's one. And Indian context, we have Smart Grid Forum is there actually. So here, yeah, we will get a lot of white papers. Even for PG students and PhD students, they offer internships actually. Even institutes like colleges also, I think colleges also they can take membership. There is some registration fees will be there, so they can take the membership also. This is a government supported forum actually. Okay, smart. So any developments in India smart grid as on today, if you want to know, so you can go to this website and get the details. And next is officially we have National Smart Grid Mission is there that started in 2010. We have a lot of targets was there initially, but that was not, fully satisfied. And recently we have taken one target, to install, this 1 crore smart meters by 2025, I think so. Okay, right now we have installed as on today 50 lakhs plus 50 lakhs plus smart meters are installed. So even Andhra also they started. So Andhra also they started installing this smart meter. It's different from conventional digital meters. So it has a different energization will be every 15 minutes interval. It gives all the parameters and it has IoT connection also. So we don't need to come to your house and then give the electricity bill. So automatically generated will come to your email or mobile phone, whatever it is. So that way. And but actually,
using that meter, you can turn on the load.
yeah, you can have that interconnection. But if government should give that project. Right now they are not giving it. So they are taking the advantage to the from the utility point of view. They want to take that one. But if they give that flexible to the user also, that is possible. Possible. And right now, Indian government has taken these are the priority areas. One is automatic metering infrastructure, smart meters, peak load management, quality power management, outage management, faults and all, microgrids or distribution systems and all. And they are given pilot projects also, some state. And for us, Southern, they are given 3 projects. For Mysore, one, and Pondicherry, another is at Telangana Transmission Distribution Company. They have given 1 project. And 5 full projects they are given. And, this is smart grid projects. One is Chandigarh, one is Rajasthan, Jharkhand, and Odisha. One project, I have seen personally, this IIT Kanpur. So I visited when I visited IIT Kanpur. So they are established a small pilot project here also. Yeah. So in future, it's going to be like this actually. So one option wherever you are application, whether you are there, domestic or commercial or industrial or agriculture, whatever application you are generating the power using the renewable. Okay. Then if you want to connect with the participate in trading, what we can do is we don't need to depend on completely on grid all the time. In future, what we can do is we can do the peer-to-peer energy trading also can be done. Suppose let us assume this one community aggregator will be there. So you have different loads and these things will be there. When you have battery aggregator, we have prosumer. Prosumer means he will consume as well as deliver because he has solar is there. Is it right? So that way you become a prosumer. Here also prosumer. He is a prosumer because he has a solar system in his house. And then we have another system. So we can try to connect each feed to another feed. Okay. And then you can start trading. Okay, now your home is there. In our home, you have a solar is there, small wind is there. Then you can consume it. If you want excess power, you can sell the power to your neighbor. You don't need to depend on grid. So no connection with the grid is not. Okay, that way you can do that peer-to-peer energy trading. So this is what emerging now. So people are doing a lot of good research on this. In future, we may see this. So this how from our side, we are slowly entering into energy trade. Okay. So already this energy trading is there at the control level, I mean hierarchy level. So between the regions, already we have different regions, one region to another region, one state to one state. I think you heard about sometimes, one state is borrowing or selling the power from another state. If the, deficient of the power or surplus of power. So that is already happening at the trading between the government agencies, between the private also. Okay, we can buy the power from Tata Power. We can sell the power to Reliance also. So like the trading is happening, but actually, at the ground level, we can do this trading also here. Actually. And similarly, the same concept can be implemented for agriculture also. Okay, if you have agri PV system, then we can do trading from other. So because all the farming systems are side by side, is it right? You don't have any kind of isolated farming. You don't do that. So all the farming agriculture things will be so connected to each other now. So that way you can do that. Actually. This is what energy trading you can do different layers. So first is application. What is your application? Business layer, control layer, ICT, information communication, physical layer. And you can do the this trading. Three types. One is centralized one. Okay, this is one. Everything will be connected to one coordinate. So he will be able to control the things. Okay, that is one. Second one is this is a decentralized one. So we can this peer will have one control, this peer one control, this control. So all the different peers it has its own control. And third one is distributed. So everyone able to connect it to each other. So this one. Now trending is between this decentralized and then distributed one. So these are steps we have to register, and then we have to see forecast because now we are trying to, depending on the solar and wind, other renewable energy sources. Then we can see the forecasting thing and market clearings and bidding and energy transaction, and finally you have to see the settlement. Okay. So we'll take a break now actually. So we'll continue the session after the break. Okay.
Dear participants, now you can take the lunch break. Then we'll meet 1:30 p.m.
Sorry.
Photo, sir.
Yes.
Thank you, sir.
Okay, man. Thanks.
Dear participants, if you have any doubts which is discussed in the morning session, if you have any doubts regarding the agri voltaics or PV systems, so you can interact with Dr. Sandeep sir. So the sir will explain. Some of the participants in the lunchtime they are asking different questions. So therefore, the sir will give the solutions to your problems, directions. He will give the direction to your problems. Some of the research scholars are working in the smart grid technologies and electrical vehicles. So the sir published the many papers related to electrical vehicles. So sir will explain. There are some participants or research scholars have many doubts how to publish the papers, so like that. So you can ask any question. Sir is give the solution to any problem. Okay, as per my knowledge, so I benefited a lot from sir sessions. So that's why I'm telling you. So all of you try to interact with sir and get the knowledge. Thank you.
Okay, yeah. Thank you for attending again. Okay. So we'll continue the session now actually. So with the previous discussion now we were discussing with other opportunities with not only with solar, other small scale wind and then bio. And then further we have discussed with this micro hydro applications. I mean sorry, so microgrid applications also. And then also we have seen what is the importance of this smart grid. So in view of this recent developments, and ultimately we need to connect with the grid. Okay, and at the same time we wanted to establish some kind of good synergy between different energy communities also. So then in that kind of scenarios actually why how these smart grids will help us actually in view of this penetration of high renewable energy, and at the same time whether we can get some kind of customer choice also, how we can get benefited also. And one good benefit that we are going to get in future actually through energy trading. So we can do the peer-to-peer energy trading. Okay. So as discussed in the previous way actually, so one we can have some kind of an energy trading that we can do. As discussed, with this help of this diagram. Now we can assume that different customers are there. Okay. And they are the community aggregators, and then there are some consumers also where they can, consume the power as well as deliver the power. And now we can see that peer-to-peer connection we can establish and for trading, and that way we can have less dependency on the grid. So in future also that kind of new technologies may come with the help of blockchain, and we can start trading between the neighbors with the neighbors also. So this is the latest trend is going to come up actually. So in this a lot of advanced technologies including AML and then blockchain. So where we is going to be play a good role in this, and of course data analytics part also. And to build these kind of platforms, actually, we need to build different layers in the execution. So one is an application layer. This is the first one is maybe first one is you can see that the physical layer we need to establish here. So what kind of distribution system that you are constructing, and then next is what kind of smart metering infrastructure that you are building with associated with your loads and generating systems and all. Then once you do that, actually, certainly we need to have this, communication infrastructure protocols, information flow is required. And then, of course, once this system is established, definitely we'll do some kind of, energy flow between the different peers to peers. Okay. So in that case, whether we see that, how kind of, controllable action that will perform through your, devices, control actions, particularly power electronics, that we need to establish. And next is business because ultimately you come to trading application, because now we are trying to see that what is understanding about, so trading mechanism, what is the financial statements, and whether you are new entity or old entity, so like that. And finally we will see that, this complete platform as application layer. So that means, user, okay, end-to-end persons, P2P person, they are able to see that all the total, information on their mobiles and website or something like that. So that way they will try to interact with them. They will be also as a part of the system actually. So this is one application is going to be come up. And next is, P2P energy trading frameworks. Now we can classify them. One is, centralized one. So in this centralized one, so what we can do is, this speed, this is a controller coordinator will be centralized one. So all the peers will be connected to him only. This aggregate is going to be give a decision control things. So this is what centralized control will happen. And second one is decentralized. So where you can try to do each peer will have decentralized, and then, try to connect them each other. Okay, this peer to this peer and this peer. And third one is this is the distributed one. So all the peers will be connected to each other, and it have more flexibility will be there when compared to other one. So this is one we can do. And so steps how to follow this, involve into this trading, P2P trading. And because this is very much important actually, even in PV, agri PV systems also, because when you have a surplus power, when you wanted to connect with the grid and you want to sell the power to the grid, then this kind of trading will help us there in the agri PV systems also. So now let us make, first is, registration. First you have to do registration. Maybe that particular platform, they will have some kind of website kind of thing. Then with all the entries, details and all, we will try to register them. Okay. And once they validate, they will accept that actually your application. So then is, they will ask you what kind of forecasting that you have. So that means you need to prove that, I'm establishing this is a solar based system in my farming or field. So how much of energy I can generate annually, okay, per day. So that we need to prove that with the forecasting things and all. So then they will see that your potential. Yes, I can add this user to this, P2P energy trade. Suppose, this system is big. Okay, suppose assume that this trading is happening in terms of, megawatt, gigawatt. Then if it is where your contribution is maybe something like less than 10 kilowatt or something, then people will not accept that your registration actually. So that kind of issues may come in the future also. So that's what you need to see, that you need to see that appropriately, you need to place the trading and see that your forecasting is matching to their requirements actually. So then that requirement is matching then with your forecasting, then you can able to participate in the bidding. So there will be bidding already, as mentioned in the due to dynamic pricing. Then people will see that, they wanted to see that, demand. Okay, yes, I have demand right now. So I don't have any surplus power. I have less deficient in the power. Then I wanted to borrow some power actually. Then I wanted to pay maybe solar only 3 rupees per kilowatt. So like that they will try to bid it. Then people will try to bid from a different peers. Then who will be giving the less, price and all actually with the conditions and all. So then it will go to market clearing, and once it is going to the market clearing, then when it's clear, then these are the people are, not accepted. These are only technically qualified and financially and all, like the market clearing. And then finally you take the energy transaction, you do that. So once the energy transactions happen between the P to P, then we will do the financial settlement. So finally they use the P, the first P, we have supplied the energy, he is going to get money for what he supplied. So this is what blockchain technology is going to become as part of this, P2P energy trading actually. And
normally the private people they selling low price in the government. What are the reasons?
one is, we need to see that cost analysis model actually, I mean, what kind of level we have to see. See, thing is, government is, government it's a complete, total entity. They don't look into only that particular power generation or system, because many power plants will be incorporated, many transmission distribution system, loads, I mean, utility, everything is. So they treat it as one single entity under electricity board. Okay, but whereas if you look at individual, so my individual thing is very small when compared to that larger system actually. So then obviously, I wanted to sell power reasonably at a low price. Okay, the my model will accept that, but whereas that government model will not accept, because already government systems, boards, they are in loss because of maybe sometimes they use subsidy, sometimes they use I mean, they use the power also as a, I mean, kind of, free power or something like that, whatever. So that kind of things will be there. Okay. And also infrastructure cost also. So their infrastructure cost, in the requirement initially is a large, so large power plants, megawatt power plant, whereas our systems are kilowatt and all. So that is the reason actually we can able to supply reasonably at low power. Okay. And but government will keep some regulations. Okay, even now if you want to sell the power to the, I mean, grid, so solar, you have solar system is there, even agri PV or any domestic PV, then now you have excess power, then if you want to sell the power to the grid, they will pay as per the policy one. Is it right? As per the policy one. Okay. And even now look at the example of EV charging systems also. Government has set some kind of a minimum and maximum prices. Okay, suppose I wanted to set up EV charging station, then each state government. So this EESL, Energy Efficiency Services Limited, they are given responsibility for the different states. So in our state, we have, Andhra Pradesh state, NetCap has taken the responsibility, and distribution companies also. They have decided the price. So our price is, I think, close to 6 rupees per unit they want to charge. So that they will charge from this, this owner of this EV charging fellow. But this fellow will again, he will charge more than that. Otherwise, he will not get kind of profit as well as operating cost, operational maintenance cost. So maybe that will be typically 15 to 20 rupees cost again. So that kind of barriers will be there actually. And yeah, continues to that actually now many different algorithms we can propose here actually. One is one popular trending now in the, so based on this game theory actually. So now look at this, different games we can, I think we are already aware of in general, but those concepts we can bring into concept and we can build as algorithm actually. So now one is, static game, dynamic and repeated game. This is one concept actually, how the process of gaming. So another is, zero sum and non-zero sum. That is a payoff. Based on payoff, you can create that game. So another is game with complete information, game with incomplete information. That is based on structure of payoff information. And next is one-person game, two-person game, and n-person game. Multiple players also. So that way, because already we discussed trading between the person. Definitely between, two-person will be there, and then n number of persons will be there. And next is, we can also, based on the differences, the behavioral logic of the players. That means cooperative, non-cooperative behavior of the different communities. Okay, because they have some kind of a conditions, restrictions will be there. So because sometimes, people, the community will have some kind of restriction. They don't want to sell solar power. Instead of selling the power, they want to store it the power. So that kind of conditions will be there. And next is some kind of, based on structure of the gaming process information also, whether the perfect information, imperfect information, like similar to complete and incomplete. And then next is different types of strategies, like a pure strategy, mixed strategy, continuous strategy, discrete, and then, infinite and then finite game. And finally, rationality of the players also, where that means, perfectly rational and then bounded rational also. So like that, and you can frame this kind of, game theory algorithm. So based on the conditions and constraints that you do have in the peer-to-peer structure or a platform. And look at the behavior now, if you implement this trading now, so even if the agri PV applications also, now we can see that behavior of the battery and the PV generation. Now what will happen? First one, so feed to grid trading. Okay, feed to grid trading if it is happening. In first case, y-axis is kilowatt power, and then x-axis is time. Now we can see this is a load pattern is this. So this is a load pattern is 24 hours time. Okay, and morning also I discussed sometimes load pattern is very much important because all the times we see the energy balance, and then at the same time here the application is energy trading we are looking into here. So now if you look at solar now, so morning 6 to evening 6 only available. Okay, so we can generate the power using solar, and that will fed to power to load the solar per week. This is the power. But now we have at the same time now battery get charged also, that is also possible. Okay, so this is the load pattern. So now remaining power, now you can see that. So now you will get the battery get be charged remaining power. This is what PV generation. Okay, PV generation. This is a curve actually. Welcome. And now next is battery. This time is now again load pattern is this, but you don't have that kind of PV power. Then you take extra power from battery. So whatever now is getting charged during this time, so that will be discharged. Okay, so that. So this is what here we do that. So now you can see that this is a battery get fully charged here, but there is no option here. But there is no load. There is no. Then in this period, you try to feed the power to the grid. Okay, that's what application. Now look at switch over to peer-to-peer trading now here in this actually. So look at this one 24 hours and then kilowatt power, and load pattern is same, and then PV power. So now as like PV power, now we'll try to give the power to the loading, and now battery get charged here. At the same time you have excess power using solar PV generation. So that excess power you sell the power to the neighbor, other people. Okay, this throughout the power whenever the solar is available. So I will try to sell the power to this thing. But only thing is I will increase the time of the battery charge because I am reducing battery charging percentage, or I mean in terms of power density. That's one. And next is battery. This is also will be increased discharge, and at the same time this is also here. If you want, you can buy the power from the grid, because if you don't have enough power from battery, then you can buy the power from the grid. So here you are selling, you are buying. Okay, but optimally you need to see here which is economically better. So definitely is going to be, because you are trying to sell and buy. So definitely you will get a more charging when compared to the selling to the grid. So that's application. So this way we need to see the techno-economical analysis also. And now this is one of the mobile applications also coming here. Now once you become a trading and sell the power to the grid or something, or another grid, then one can build this kind of platforms actually where, so what is the energy you are trying to generate it, so how much of what is your power rate, so what is the energy, imported energy, what is the local energy, what is the borrowed energy, and then what is the daily average generation, and this way we can make this, what is the peak demand, and you can have a time cycle also, and then what is your if you are participating in different things, what is your rank based on some conditions and all. So this way it is going to be come up, right? Okay. And then awards and rewards you can now use them. So this kind of applications are coming up well. And of course, one can build these dashboards also. Local energy, market, dashboards also is better than mobile. Mobile may be suitable for users only, but in case of other than vendors, other than users, maybe aggregator, maybe some kind of utility companies, if they wanted to visualize this, and they can build a dashboards like website kind of thing, and then what are the feeds are connected, different regions. This way you can network this configuration here. So there are different regions, different peers are connected in this configuration here. So now totally, this is a one complete, IEEE 33 bus kind of arrangement, and then you will form a grid configuration here. And you can see that different contracts when it is happening, cell orders and P2P, self-use, backup, and other things. We can try to visualize in this one single backup. Okay, and we can see generation, consumption, and grid exchange and all. So this kind of dashboards also we can develop it. And this is schematic layout here. Is clearly one can understand this actually easily. Now let us assume that there are three peers: peer A, peer B, peer C. Now, so peer A. Now you can see this is a prosumer. So he has a solar. He can consume the power as well as deliver the power using solar. and he is only consumer battery EV in there, but he doesn't have any solar or EV. Now we can see that energy meter is there. So each peer has a house's energy meter, and then smart energy agent is there. Smart energy agent is there. That is also this is nothing but computational device, your microcontroller. Okay, so that means sometimes we cannot completely depend on this energy meter because we don't have provision to access fully. Okay, because this is supplied by the government actually. We don't have provision. So what you can do is we can try to annex some kind of other microcontroller system with the help of suitable communication protocol. Then we can integrate this controller with this energy meter now. So through this we can try to establish the communication. These are all communication will be established through this SA, smart agents. Okay, communication. Okay. So based on the layout again, actually, whether this layout is enough for based on Bluetooth or Zigbee or Ethernet, so that we need to decide it actually. And ultimately, you will have conventionally connection with the grid also. And now this information will be sent to one database system that we will create using the blockchain technology. So now we will start trading between them actually. So now if they wanted power from solar, if you want to sell directly sell to PAP, PSC also that's possible. And now also if they want to consume power from this, they can borrow. And you can see that how independently these three pins can be connected with the options of EV, LV grid. So low voltage grid actually.
So how can we decide, sir, to whom I am selling? Because my this will be connected to the grid lines only, sir.
No, actually. So we, of course, we are trying to connect to the grid, but we will have that kind of provision to disconnect with them.
Okay, separate lines we are having.
Yes.
Okay.
So we will create that breaker.
Okay.
So that breaker will enable that it will not be connected to grid, but it will be connected to through two other peers through that separate line.
Okay. Can I decide to whom I want to sell also?
Yes, sir. That for which we need to build some kind of interactive platform.
Okay.
Previously, I showed you one interactive platform like mobile phone, web-based and all.
Yes, yes.
So there, people will be already enrolled as a members.
Like
then the member will be, make a request. So I wanted to buy the power.
Okay.
Then people will, if he is, then they will participate bidding here. So if he doesn't have any kind of supply unit, then he will only alone person. Then he will supply the power, whether he will agree or not. That's okay. So that. This is what now you will see some good papers also on this actually between peer to peer, and we can also bring this not only individual, we can bring to community level, like microgrid to microgrid. Suppose best example maybe you can start trading between this campus Vignan Lara versus Vignan University. So because both are operating, both are administratively, financially, both are independent. Is it separate? Then you can do the start trading also. They have solar plant, you have also solar plant. Then you can start doing this one of the pilot project also. They execute this peer-to-peer energy trading as a case study. So let us maybe you generated power, maybe some power. You don't assume that you don't have any load profile as a consumption. Then sell the power to them, and then see that they will consume. After consuming, then they will make a trading to you. So with the settlement. So that way you can do that. Similar. But for which you need to use some kind of microcontroller.
You should have separate lines
So,
also.
microcontroller which should have a communication, a linkage between this campus and this campus. Maybe you can start doing with Raspberry Pi. That is possible. So Raspberry Pi is enough, and then you can suitably add some kind of Raspberry Pi with the communication communication port, which will enable one is if you have LAN connection between two campuses fiber, then you can do LAN. So you can connect with the Ethernet cable. So and then you can this port and that port you can make a connection, and then you can do the transaction. Okay, so that you can do that. Simple project. Maybe this you can take as an example for a BTech project or something.
These things are implemented, sir, in India right now. These things are
no, pilot projects only, and the academic projects I can say. IIT Gandhinagar, they have done it actually. And next is some research is, research publication lot are there, but only pilot project. Okay, pilot project. But this is already somewhat we know with terms of solar. Already solar rooftops are there, solar ground mounted megawatt or gigawatt plants are there. So what they are also doing trading, but they are only, they are pumping it if I have excess energy. Okay. So, but actually that trading, that is not immediate one. So they will try to detect that electricity bill as minus. You have pumped to, your college has pumped this much energy to the utility company, this many units. So whatever total consuming units are 1000 units, you have pumped to only 200, then 200 minus, remaining 800 units you have to pay. So like that. So this one, and next is, this is a kind of schematic representation of hardware software integration, a test bench actually what it built it. So one is the smart agents I said actually this can be extended to some more application actually. One is database actually. Database, there's a database we need to create it. One is meter ID, because each node I said so some meter should be having. So previously also, so this has 1 meter, this has 1 meter, 1 meter. So that means how do you tag that actually? So that tagging we'll do with the meter. So we'll identify what is the location, building and all. So that accordingly we'll try to see the understand that I'm connected to this peer. So peer identification will do the meter ID or field ID number. That is one. Another is historical data. If at all any historical data. Okay. Suppose in previous day, last day, yesterday I have done the trading, and today also I am doing it. So you should be able to store that historical data also. So that kind of storage option also should be inbuilt in your smart agent. That is one memory, and that data should be also utilized for your optimization or forecasting things also. So that is also required, because your things are fixed. Your generation is almost setup is fixed in terms of rating, and then loading also patterns are more or less and easy to forecast the data also. And next is optimize the data. Sometimes you need to take the decision like you have multiple sources will be there, multiple options will be there. So your smart agent should have to take a decision. Suppose for example, so the smart agents of one home, as I mentioned in this previous figure. So this person has a requirement. Now he will get through this smart agent one. So he will get a acceptance from the peer A as well as grid also. Then what is the best economical one? So whether I should take power from the A or B. So what is the advantages? Okay. Suppose if the grid power is less with price, maybe 5 rupees, this is 6 rupees. Still, whether I should go with this, whether any advantage. Okay. So even if you go with whether he will give any reward to me that can be used for next level. Grid won't give that kind of rewards. Is it right? So we should see the feature benefits also, and then optimized one. Maybe that kind of things will be happening actually. Reward kind of things also. That is called, people will popularly in the smart grid, they call it incentive based demand response programs. So people will give incentives. That incentives all will accumulate, and then we will like in the normal life you get the coupon codes and all. We'll try to utilize them for our personal whatever purchase. Similarly, here you'll also get some kind of that kind of scenario, and those can be utilized for optimization things also in the further level, and optimization data also, and node application. So finally, what kind of node you are trying to connect? What is their application? What kind of energy required? Sometimes that node is your node is connected to that particular peer. That peer is required reactive code. So whether other peer can be supplied reactive code, the grid can supply, but whether other peer can supply. So that we need to see the application also. And then finally, this is a smart agent. This will be connected to this is a bidirectional with the communication. So cloud storage will choose it. So nowadays people are choosing different cloud, where popular Amazon where AWS and other platforms also you can choose them. And then we can build one web-based application. We need to create them for interact with them. So the user will interact, as well as utility company, aggregator, everybody should interact with that, and they should be able to access it, because this is blockchain technology. Every peer should access the information. That's what it should be traceable, transparent, and trustable. So all the three features should have it. And then you will maintain one kind of server, and people will make application here as a node. So I wanted to participate it, and through server we will try to run this total system. And of course we can release the blockchain certificates. Okay, maybe previously also I said we can give, this is what is the contribution to your this P2P energy trade. So how much carbon footprint that you reduced it. So where I can give the rewards. Okay, now instead of consuming from the grid, you can also get the power from the solar, and then more you can depend on the solar only. Then you can also contributing to other peers also by supplying solar power to others. Then you reduce the power consumption from the grid. So that kind of scenarios also. So what these peers will get some kind of reward, and we can give some kind of certifications also. So we can analyze. So these are all different innovative ideas people are incorporating to encourage the participation. So similar things, this should come in the encouragement of EV vehicles also. EVs. How do you encourage the EV vehicles? Okay. So how can you prove that your energy consumption, fuel consumption will be, less when compared to the conventional vehicle also. Yeah. And now these are the important topic actually where we are going to discuss as part of this session actually. So performance, assessment, and then key performance indicators. So we popularly it's called KPIs actually. So in case of agri PV, so we need to analyze this performance analysis in both qualitative and quantitative ways actually. So we need to see that what is the potential optimization, design and operation maximum the financial incomes of the farm. So ultimately, the major problem in this everywhere, including India. So the income generation from for that farming, it's very less actually. They have a lot of other expenses, and then natural calamities will be there where they lose the money also, and government subsidies also. Though they get the government subsidies, they will be less income or no profit. So then, at the same time, if you are incorporating this kind of, solar-based technology into this, agriculture one, then what way, this final income should be maximized or rise. So that is one. And we need to see that, one is KPIs related to solar irradiation. So one parameter we can see homogeneity of the light. Okay, this measure the uniformity of the power distribution within the PV area. Okay, so based on that, actually now this parameter whether your PV installation very successful for this farming or not. Okay, this is one parameter. These are all scientifically defined, and then they are trying to impose for this implementation of agri PV system. And second parameter is light use efficiency, the total amount of light reaching the system. Okay, so that means how much of light that already we know that solar cell efficiency is less. Okay, after that, after crossing this solar panel, then how much of light we are reaching the system, that's one other point. And next is light productivity factor, that is the LPF actually. So it will evaluate the efficiency of the solar irradiation sharing for a particular crop and then PV system configuration. That means you are trying to see what is the best combination for the particular crop and then PV system, and then what is the productivity factor. So light productivity. So that means if you are increasing the enhancement of the light, and whether you can increment this income also. So in terms of production, and then generate the more power and then the more income also. That way it is directly benefited. And next is light distribution PV greenhouses also. So already morning we have discussed greenhouses. So we are trying to eliminate the conventional greenhouses with mats and all. Now we'll try to bring with the semi-transparent greenhouse type solar thin film type things and all. So in that case we'll try to calculate that incidence global irradiation within the PV greenhouse house actually. So whether it is suitable or not, that is one parameter. These are all solar irradiation based parameters, performance indicator we need to calculate before installation of the solar agri system. And similar to directly PV system. Okay, the KPIs related to PV system with the performance indicator. So power conversion efficiency, this measures the performance and stability of the PV modules over the time. So this is very generic. Already if you are known being a electrical engineering, so we already emphasize this. Okay. So what is the total? Because in solar, what we do is we have solar. So already solar cell efficiency is less, and then after that, actually we will try to incorporate the maximum power tracking with the using DC converter. That's one stage where we work. And then next is we will convert that DC will convert it AC and then supply to loads or grid. And we have multiple conversions are there obviously, and we need to see power conversion efficiency, how can improve that actually, including power electronic converters and all that, including MPPT. And next is energy yield, so that connects yearly electrical power generation to the land area of the PV system actually. So this we need to calculate. That means I will declare that if you set up this kind of agri PV system, and this is for this particular crop, So I can generate this annually this much of power generation. Maybe I can generate 1000 kilowatt hours. So energy I can produce. So that way we need to highlight your performance indicator using this energy yield parameter. And next is agriculture based, agriculture related. So other side, okay. So then is crop yield. So crop yield is represents the quantity and quantity of agriculture produce harvested per unit of land area. Already maybe you have previously some calculation. Maybe 1 acre area, I'm getting some kind of 110 of production I have done it. So now I have incorporated this agri PV system solar. Then what kind of production whether enhanced or not? Okay, whether I with the enhancement, whether I get more income or not. So that kind of crop yielding we do that, and at the same time energy yielding also. So connect with the same electrical power generation in the land. So that means you are trying to applicable for this energy to the agriculture. Okay, how much of energy? Suppose you put a solar plant for your farming system. Your farming system maybe 100 kilowatt is required, but you have excess power. Okay, maybe you incorporated established 150 kilowatt or something. So excess 50 powers always you try to sell the power to the grid. So in that case, that agriculture based KPI also we should help you to get more income also. Okay, so more generation. So generally these are the parameter indicators actually KPIs. One is one set related to solar irrigation. So that is one we have to see that. And suitably based on one is crop type. So another is solar based on solar irrigation. So you need to choose that particular solar configuration. So morning we have discussed what are the different novel technologies in agri PV system. And in that novel technologies, we need to adapt it suitably for your particular crop. And before installing, you need to calculate these parameters. And similarly, PV side, electrical point of view, you need to calculate these parameters. Agriculture point of view, you need to do this. And next is other parameters also there. So land related KPIs actually. Okay, land related KPIs. So now one is ground coverage ratio. So ground coverage ratio is nothing but the ratio of cover occupied by the PV models to the total area of the agri voltage system. Actually. Suppose you have 1 acre. So in this 1 acre, how much of land your 1 acre farming is there, but how much of area that you are covering for PV system. Okay, so that is another parameter actually. So land related KPI. So another KPI is land equivalent ratio, that is LER. So it evaluates the productivity of the land for the API systems compared to the traditional PV installation. So suppose uh, now if in traditional ways maybe suppose if you want to install 1 megawatt plant, maybe required definitely 5 acres land minimum is required. Sorry. So in 1 acre we can install 1 megawatt. If you want to install, definitely 5 acres is required definitely. Okay. Then similarly here so we need to compare this this land ratio of productivity with traditional system. That's the equivalent here. Okay. So because obviously we have difference definitely. Okay, because there land mounted solar traditional system, we don't care what is under the tree, and based on that we will choose that PV system also. So here differently we will choose that. Yes sir.
So is it possible to take a small PV system, that is a small PV system on a small area, and also I think we can take any crop, maybe tomato like that. Can you do that kind of analysis? Can you publish the analysis in that direction? Small, not large.
Yeah, I can do that actually. Possible.
Small scale analysis.
Possible. But actually uh, then in that case your application is only power generation, also water pumping. Okay, first is you need to farming is okay. First you decided what kind of farming that you are doing it. So that farming application, what kind of energy is required. So that energy is completely for water pumping. Is there in other than water pumping application is there for energy related. So that we need to see. Then is in the same area, then we'll try to estimate like in the same way here as mentioned here, ground coverage ratio or the land equivalent ratio. Then in the same area, we'll see the based on the constraint, what is the maximum size of the PV that I can install, because that trees also, plants also require some kind of a thermal, okay, transparent is required to, they also should get a heat, is it right? So warm, and if we don't completely hide them, okay, we don't completely hide them actually. Suppose you put a some maybe half acre some plants are there, but we cannot put half acre land completely on the solar systems. Okay, so based on the crop need, the irradiation from the sun, then we can keep this kind of solar system that we can incorporate. Okay, that we can do. And of course, we can generate the power as already previously discussed many times today. And we excess power always we have provision to connect to the grid. Okay, and then connect. I mean, we can directly try to see that get the income also. That we do that. Because maybe if you are trying to operate this farming in the remote place, definitely many remote farming places also they not have connection with the grid connection actually. So that is challenge. So wherever the challenging is there, where we can implement this kind of things, that is possible. Of course, we can do some kind of analytics things we can do. As you asked, whether you can do a kind of research-oriented analytics, So you can do with first starting with this. Okay, maybe one subsection of your research paper, so can highlight this parameter calculations. Okay, maybe solar irradiation that particular place. So what is your KPA values related to solar irradiation? Maybe one kind of tabular column with the formulas and calculate them and then present them. And similarly PV related, so you have calculation and agricultural productions also. And that way also you can have contribution to your paperwork, can contribute to major section of the research work. So third one, we were discussing this land productivity factor. This assesses the agri PV systems productivity based on the relative yields per PV production and then part reaching crop level. This is one thing. And we have the formula for land equivalent also here. If the land equivalent is more than greater than 1, that indicates land productivity or API system is higher than productivity of a separate PV or agriculture system. So this advantage here. So that means we need to see that productivity LER value should be always more than greater than 1. Next is water related KPIs also important, because your farming at fields so required water supply also. So water productivity, because you are trying to use the solar also water pumping systems also. So it relates the total agricultural yield to the total water needed to the crop. Okay, so that is a relation water productivity. And what are the water consumption? So it measures the volume of the water consumed per unit of the crop. So that is the water consumption. We will measure in per unit of water area of crop in terms of volume. And then water use efficiency, that is relates the total agriculture yield to the total amount of reference evaporation actually. So that means these are all impact. One is productivity, one is consumption, whether it is usage. So all have three different meanings it has. So that's why it has all three has significance in this analysis. And last one is economic parametrics actually. This was very much important, because we are why our main motto, one of the main motto, so to maximize the financial final incomes to the farmers. So that's why you can bring this these economical metrics also. So what is the net present value? So net present value, it determines the project profitability by considering the cash inflows and outflows. Okay, so that means what kind of how much you are paying for money for like you are trying power from the grid. So how much you are paying, and at the same time how much kind of investment that you do for solar installation. So all these things is a matter also. And another is leveraged cost of electricity is important. That is very popularly LCO we call it. So that is the annual cost of generating electricity by say agri PV system. So that means so we need to declare that what is the actual cost. What is the actual cost? So maybe we need to define that my generated power cost through the solar system is 3 rupees per kilowatt. So that way we need to declare that. so that it's very beneficial to others also to they get to know what is the price that you are generating the power also. Okay, so this is the actual cost of generating electricity. So not the consumption or not the selling power. So that means always we need to see that this leveraged cost of electricity should be come down, so that we will also consuming less price. Okay. So otherwise the governments and other power plants what it tell that we are I mean supplying this electricity, I mean generating the power supply maybe at the rate of right now it is there in average 7 rupees it is there. Okay, where these government companies, NTPC and all, we are claiming that 7 rupees per unit generation they are spending to supply 1 unit. But actually they are, for in case of domestic, they are giving for 2 rupees or 3 rupees. But they will try to compensate with their commercial and industrial customers, where they will charge more there. So somehow they do some compensation. Okay, but ultimate aim is we need to see that your power generation should be at less cost, low cost. Then automatically your consumption, whatever that charge, electricity charges also will come down proportionally. So this is a formula LER. Just now I showed you. So one is yield of plants divided by yield of plants, that is APE. So this is without PV. So with PV, without PV divided by plus electricity yield. So how much of electricity generation you have done with PV, or how much of electricity you have done with only PV. So that is only PV. This is agri PV. This is the only PV. This is no PV. Now you can take the decision making can be possible using this prospective output. So one is your LER value is more than 1. Then agri PV has yield advantages. So that means whatever now incorporated this for particular plant with agri PV, that particular agri PV topology or configuration, that means your system is completely agri PV system is advantages. That means advantages in the sustainable agriculture as well as income also. So that means it's a good combination. Particular plant, so whatever you have to do, solar technology is the best one. So if your LER value, if you are getting more than 1. And next is if your LER value is 1, so agri PV system has no advantages. So you don't get any profit, but somehow you need to get your returns back. Okay, that is another. So if the LER value is less than 1, then it has advantages. You are going to be lost further. You need to overcome with this. That means maybe you cannot change the crop immediately, but maybe you have to see that whether your PV system you can change it to different novel technology. Thereby you can enhance the efficiency and raise the income again. So that we need to see that actually. Okay. Sometimes the solar system also will become a drawback. Like maybe you have put some kind of shielding kind of thing. Maybe your plants again cropping may not be requiring proper irradiation. That may lose your reduce your productivity also. Then your LER will have going to be less than 1, and then you will have disadvantages by incorporating this agri PV also. Okay, so this will be reverse also. Okay, and now you can see the very popular so sir asked the example for tomato cropping actually. So here in this table it is given here. So different crops are mentioned here. Tomato, its LER value is 1. Then your no yield advantages. Okay, so for brinjal LER value maybe 1.1 proposed. This is one reference I have quoted. They have proposed one agri PV. So in that LER value is 1.5. Then they advantage yielded with advantages, and then pepper LER is they got it for this particular agriculture agri PV 0.8 disadvantages. So look at and then 1.6 advantages. Cucumber 1.1 advantages. So snake got 0.4 disadvantages. Rose flower 1.1 advantages. So aloe vera 1.7 advantages. Okay. So that means you can see that. So here different plants we can see, and then but we have taken only one agri PV, only one agri PV system. But we applied for different crops, and then you try to calculate the LER, and then see that this proposed agri PV is suitable for which crops. Then you can define that. Okay, that is the combination. Otherwise, now we have seen that tomato is no advantages. If you want to bring the advantage, definitely you need to change your agri PV. Okay, otherwise you have to change the crop. Maybe changing crop you need to maybe wait for a season or next cycle or something. But if you have option, you can do slightly modification of agri PV configuration. Then see the how we can enhance the productivity in terms of cropping as well as in income also. Okay. And we can see that this is the synergy is required finally. Okay, so in case of agri PV systems, this kind of synergy is required. So one is conventionally three systems are there already. So one is agriculture systems, conventional agriculture system, which continues with the conventional methods, whatever mechanical methods, conventional grid connection, it will run on this. So another is we have PV systems. PV system we know primarily for energy generation, power generation. Of course, we do the PV use for the thermal generation also. So heat. So we can use the heat also, thermal generation that can use for thermal application as well as power applications also. That is also possible. So another area where we know that separately ICT system, information communication technology. Now, how these three technologies can come together? So, agricultural sector and PV and then ICT technology. Then you can bring these are the technologies where we can work on it. So one is these two. Then agri voltaic, that is agri PV system, that is one. And then if you bring this ICT also here, then you can work on this as smart agri PV systems. Okay, because you are bringing the agriculture IoT here, then you can do maybe you can do trading between the different farming one farm to another farm, or you can try to connect with the different fields, or you can connect the grid also. So interaction will happen possible with the ICT. That's one possible. And if you see the interaction between this agriculture and ICT, then smart farm. People are already talking, maybe there is a conventional motor pump set is there. So I'll put some kind of IoT switch. So remotely I can switch on and off the pump, switch on the motor or something like this. So this smart IoT based switches that can be helped, something like. And maybe some kind of where you can use drone technologies also.
Suppose you have a you want to get Bharati solar plant, which is near to Amravati. So actually there is under the fields, it is constructed in the fields.
Fields.
So there is the land is meant for only generation. The land is only meant for generation.
Generation.
I wrote, I think, Prayagas and Chennai like that. Like that, in Prayagas, we installed all the field systems. So for that system, because we need to solve the industry problem, so my other constants are asking, so is it possible to already field systems are there? Is there any kind of analysis we can do for the Bharati solar plant for approving? Actually, that is for carbon like that surrounding surrounding to the Bharati solar power plant. Atal is going. So taking up analysis, we can take analyze.
But you want to introduce that farming in the same place of where the solar system is established? Same place only or nearby?
Nearby.
How the solar system can be contributed to nearby? But they need to establish a linkage between them, because everybody, we they agreed only, yeah, because that is largest system. That's what I'm asking. Yes, under the previous system possible, but we need to see that what is your previously I told you, so what is your yield of the plants. Okay, that we need to do LER because this performance index are there. You can see that ground coverage ratio. Okay, the area of the area occupied by PV models to the area of the photovoltaic and land equivalent ratio and land productivity area. So this we need to calculate that actually. So that means now that is conventional solar panel system that is already fixed tilt. That's not rotating or single axis or dual axis not there. Is it right? So then actually then you know that what is a solar irradiation per a typical day. The first step is what you should do in exercise. Go to one place, that particular place, send somebody, and morning to evening, 6 o'clock morning, and then evening to 6 o'clock. So let us try to analyze what is solar irradiation. So under the solar panels, okay. So with the directions, that is required. First, that analysis we should do, for which we have, measurement. devices are there, solar irradiation measurements are there. Okay, that we can take carry as portable one only, like small one. So you can go there and then keep it there, that particular place, in one place. Maybe you wanted to plant the tree under the panel. So same place we can keep them. And then we can tree morning to evening, how we can observe the solar radiation that particular. And typically maybe you can randomly place in different also. Or you can assume that the same place it is uniformly distributed, so same solar radiation. Okay. Then for that solar irradiation, so what kind of plant is suitable? Now he is suggesting, what cotton. Then for that particular solar irradiation, whether cotton is suitable or not. Okay, if it is suitable for that irrigation, whether it can grow. Before that, let us parallelly we can analyze that. So with talking with the agriculture scientists, okay, agriculture scientists particularly, maybe faculty from agriculture and all. Then let us we will collect the data also. What kind of environmental solar-based environmental system required for growing that crop. So then you can map them. Your measurement, solar irrigation, their crop requirement. If it is matching, then we can go. Or if they are not matching, then anyway you have data of solar irrigation data under the solar panel. So you take the data to the agriculture scientist. They will suggest you which plant is suitable under the conditions, because that will vary to season. That's one point. Okay, they will suggest you based on season. Maybe this season, maybe this is temperature. And also you need to do different exercises. There are differences. India also particular this place. Okay, and we have again this is the winter is going on November December. So temperatures are different. January is different. Again summer is different. Maybe you can do the seasonal wise exercise, or even if better if you do monthly also. So you will get a 12 scenarios of solar radiation, and you can talk to them. They will suggest you if it is 12 scenarios if it generated, and if you tell them I want to do for 12 scenarios solar radiation, you give me 12 crops according to seasonals, January to December. Maybe there are some crops which require days only, is it right? So not months and so they will suggest you that. So that we can enhance our income also. Then we can keep on changing the productivity. So that one exercise we can do. Okay. Or they will suggest you maybe 3 months long, 2 months long, maybe quarter wise. So based on your profile, profile, they will tell. Okay, that is one. But other important thing, conventional thing, we are forgetting actually. We need to see that no sand, whatever, soil testing. Because is it maybe you are already telling that nearby suitable for cotton. The particular in that case that is also suitable for cotton. But we need to map with solar irradiation. But apart from cotton, for the same soil, this thing, okay, analysis. So which other plants also suitable? That data also, soil information also should give to this agriculture science. Okay. Then you can do that. So you do soil testing, do the soil testing. Second one is solar irradiation testing. If possible, different seasons wise. Okay. And next is you try to find out from internet or other sources what is the cotton requirement. Okay. Then you try to map and discuss with them, and then as a trial run, you try to do that actually. Okay. And simply now, as of now, you can compare. So as discussed here now. Yeah, here. So this is a formula you can take here. Okay. Solar system now you can compare here. Solar yield of plants with AP, agri PV system divided by no PV. That means you need to compare without PV. Then you need to see that there is a place, so no solar panel. Normal, same plant. Suppose you propose tomato, so tomato without solar, under the solar. Then tomato under the PV. And similarly here, electricity yield agri PV. So electricity only PV. So typical PV already this only PV you will get from this manufacturer. Manufacturer will give so particular plant this is the maximum capacity are based on. So that you can and you can find out this LER value. Okay. And this exercise you do. And of course, what are the parameters are the relevant parameters? You can see the performance indicators. Maybe here, whatever I showed in more than 20 parameters may not be all required for this particular your case study, but you need to choose that what are the parameter indicators are required to analysis your exercise, and then based on parameters you declare yes my whatever method whatever plan is correct or not. Okay, that you can do that. Okay, small project it can be done as a small pilot project. Huh. Yes, yes, we can do that. Yes, there are some particular papers are there, but I found many of them on conference papers actually. So in IEEE particularly, if you search in agri PV system or solar, I mean this agri voltaic systems and all, but you get mostly on the journals, I mean conference papers, and many of them I see in the country of Bangladesh. So they are done with lot of case studies also. They published also. So same pattern also one can see that, and then we can work on it and then publish it. That is possible. Because each case study is different, is it right? So my case study, my own land, and then my cropping, and then my measurements, and then indicators are different. Okay. So analysis can be different, not a problem. Yeah. So we were discussing this point, and between this ICT and then agriculture, smart farming systems we can build with the help of IoT kind of thing. And next is, this is a PV and then IC. This is already green energy management system. This is already we know that. So whatever now coming with, this solar PV system, now we come up with this smart inverters. So smart inverters now it's part of, anyway the solar systems require smart inverters. So then now we incorporate this ICT with a smart inverter technology. Then we can try to control the loads also. So load monitoring we can do that. So load disaggregation we can do that. All these things we can do with the help of ICT. So finally, if you combine them, so all three technologies, then you will come up across this, smart agri-voltaic system or smart solar agri-PV system that will arrive. And then, if you work on this power electronics, particularly solar, okay, particularly solar. So these are the research, power electronic based research is trending right now, actually. Particularly without power electronics, I mean it's not possible to implement the solar technologies. Compulsory is needed actually. Okay. Now in this case, actually, one is people will talk about power quality. Okay. So based on again here, what is the application? If they are trying to connect with the loads and then grid. So as per the standard, we have the standards. Okay, power quality standards are even here for TSD and then SAG, SWEL. So everything is standard is there. Suppose if you want to declare that SAG, so SAG we declare that 0.2 to 0.9. So that is the allowable SAG. So if it is swell, it is 1.2 to 1.8. It's a SAG. So like that it's allowable thing, and at the same time with the stipulated time also, harmonics also. So this kind of things one can address these problems power electronics based research in solar So with and without additional devices we can do that. So one is that is active filters we can use it. That is a simple technology. Maybe you can incorporate LC filters and all. We can try to mitigate some of the power quality issues. So another is static compensators we can use them. Then multi-level inverters we can use them. Multi-pulse inverters also we can do. So where we can have similar to multi-level, you can have H-bridge converters, different H-bridge converters. We can try to combine them and bring the multi-pulse. We can do that. And multi-stage. Morning also we discussed that. So multi-stage converters. Okay. So one stage we have one stage and then second stage. So using the isolation transformer, you can do that. So same thing we mentioned here. And next is solid state transformers. So you can avoid the conventional transformers now. So we can try to bring the power quality now. So solid state transformers. So that is power electronic transformers. Okay, completely two back-to-back converters will be possible with the bidirectional. So that can be used as a transformer also. That is also possible. And this one reason. Another is complexity reduction. So in this complexity, in the solar PV, what will happen is, people are coming with the different topologies with, to bring the power quality again, we are enhancing the, topology size also. So if you want to increase the size, decrease the size, so definitely we again next step is complexity reduction. People are now working towards, reduce switch count. Suppose I use some kind of inverter or 9 switches are there. So I come up with the same level then 6 switches I will use that. So that way you can use that reduced switch content. Suppose I have energy storage elements are more, LNC elements are more. So that may cause different problems, maybe resonance, maybe storage issues, coupling issues, whatever, or EMIs, electromagnetic interferences. Those are all different issues will come with the magnetic circuits. So then to avoid that, then we can try to reduce the number of those passive elements, particularly passive elements we can reduce them. And next is energy losses, energy and losses we can address. We always see that energy should be improved. So no technology is is equal to 100%. Okay. So then we can try to we have chance to improve the efficiency. That means that is directly we are reducing losses, we are increasing efficiency, nothing but. And then reliability aspect is there because ultimately any technology, power electronic based, particularly solar also, we see that the reliability and stability is very much important. So that's what people in the morning also we talked about. What is the lifespan of the solar system? Like 20 years, if you say, that means you are guaranteed that reliable operation for 20 years without any fault condition. So that's again stability condition, different kind of operating condition. That what is the stability condition? And another one is multi-port converters. This is also very good important. So multi-port, so now what we can do is based on application. So you have multiple applications. Suppose you take agri PV system itself, maybe your water pump required 1 voltage. Okay, maybe your auxiliary system lighting required DC. That is again different voltage. So like that, your loads will have different voltages and requirement will be there based on the application. Then you can build a multi-port converters. So different stages. Maybe one particular port, if you take the output, this is the output. So this is a 10 volt and 5 volts. So this is the power, this is the voltage you get. If you pass on to next stage, then you will get this voltage. So like that, you will have multi-port converters. Okay. So even we see that this is a input side also multi, output side also multi. That is also because you combine them as I discussed in the morning, multi microgrid. So you have multiple sources will be there. When you have multiple sources, that means you are giving multiple inputs. So then multiple outputs also, multiple maybe DC load, AC load, combined loads, and loads also we can define differently also. Next is hybrid and parallel operation that we can discuss. That just now I said solar and wind. Maybe you can integrate them, and like that and all. Maybe you can have different parallel operation also. Suppose you have two different loads are there. Maybe one load is particular to water pumping in agriculture. Okay, another load is heating application or farming dairy application is there. So then how these two inverters are getting parallelly power sharing between them. So you need to share the power from one single source. Okay, so that kind of thing. Or sometimes you will have hybrid. You have solar is there, you have wind is there, and you have two loads are there. So these loads should decide. I should get a power from solar and wind. So what is optimized sharing between them? So maybe these loads are both required maybe 100 kilowatt, and these loads are maybe again 100. You have extra 100 is there, 100 plus 100 200, but whereas load is only 100. Then whether you want to share 50-50 or whether you wanted to get 75 to 20, 75 plus 25, so like that. So this kind of optimization things we can do with this hybrid with parallel operations. And another one is operation under dynamic conditions and analysis. Okay, that means most of the studies in the research and point of view, academic research point, they execute with static conditions, assuming that my load is fixed. I kept a load is constant value, constant power. Then you will get you don't have any changes. Then let us bring in some kind of dynamic condition. Maybe you suddenly switch on some motor, or suddenly you bring some kind of abnormal operations here. Okay, then you try to analyze it. Maybe some previous research work you have done with static condition. Then you try to incorporate with the dynamic condition, do the analysis. Then how the power electronic will support for dynamic condition that we need to react. Okay, maybe this dynamic condition may be required. We require some kind of reactive power. Whether your power electronic will support that reactive power, that is one case study. So that way you can bring that actually. And next is emerging power semiconductors actually. So new devices now beyond IGBT and MOSFETs. Okay, now people are talking about silicon carbide and gallium nitride. So these are wide band wide bandwidth devices actually. So it has more efficiency and more reliability when cut. But only thing is currently it's not available. Anyway, even from Indian market also, many people we are trying to import from the other countries. So that's why government of India also they're trying to populate this semiconductor mission. So to see our visibility in the semiconductor manufacturing in India. So through that mission actually. So this is one thing. So now whatever work power electronic based with MOSFET and IGBT, now people are now repeating the same work with silicon carbide and gallium nitride and see what is kind of improvement there we can propose it. So that is work is going on. And next is novel algorithms for power electronic control. Okay, so novel algorithm. Now people are previously proposed one algorithm. Now we can propose with new algorithms and hybrid. So this is also possible where some kind of in case of dynamic conditions and all. So your standalone algorithm may not be work. Then we need to see that hybrid algorithm for the other case study. So till then maybe you have one type of load, suddenly switch on it. Then our control algorithm should act it. So that means you can bring some kind of hybrid also. Then where people are coming with different conventional algorithm with machine learning. That is also people are coming with a lot of artificial intelligence algorithms also they are coming. And last one is interesting, that is IoT ML and cyber based power electronic converter, that is nothing but smart power modules. Okay, so right now whatever physical modules power electronic switches, okay, starting with so diodes, resistors and IGBT, MOSFETs, whatever it is it right? So those will not be connected right now, it's IoT. But what we connect with directly with driver circuit, is it right? So driver circuit and then you have a microcontroller. So how these power electronic devices can be connected to IoT? Because you already have some kind of microcontroller setup and you have a direct interface with the driver and then switch. So now we can convert them as a smart power module with incorporation of device level. I'm talking about device level communication. So not system level communication. System level communication, I have one centralized control. So through centralized control, I will do that. But here, we can do in the future device level control. So this device level control will happen maybe completely. Maybe you are operating your system at 7 level inverter for power quality. Then you don't need it. Then you can use this IoT based smart power model. Then you can reduce that 7 level to 5 level. Because I will control the switches at device level. So because I make the typical configuration, I will reduce the switch count automatically. So this is the advantage with this smart power modules and all that. Okay. So we'll see some of the general topics which is used for faculty. So now this is the era of professional education or professional journey. Global and self learning is important. Okay. And what is the fundamental? We have discussed a lot of technologies today, agri PV and other solar and microgrid or renewable and other today. Further extension, energy trading and many other topics today. So one thing, first thing is what we should do is, we should know before starting what is the current status of that particular technology. Next is we should analyze what are the problems in existing technology and methods, and then we'll see what is the future development of scope. If you follow these simple three-step models, then every technology is going to be novel. Is it that we are not trying to repeat them? Okay, because we have a reference is there. What is the current status? Okay, maybe let us example previously discussed. We have a one cropping for tomato cropping. Then a crop is there. Then we are trying to apply for agri PV system there. Then we will see that tomato crop. What is agri PV? What is current status and successful one case study. So based on that, I will take that. I will see the problems in existing technology. Then I will propose a new method or extension method. So that way, my starting point should be there always. And generally, what are the steps in engineering solution? As an engineer, electrical engineer, particularly what we do. So we start with the modeling. Is it right? So we start with the model. Any engineering system can be model. Is it right? Model. So modeling. So that modeling we'll do with generally, if you want to start with the scratch, then we'll start with mathematical equations. So maybe differential equations, integral equations. Maybe all our electrical system will have a closed loop system. Is it right? When you have a closed loop system, then you will apply KVL, KCL. Is it right? To simplify the method and find out the unknown values of current or voltage across a particular point. So that way you will complete the modeling detail. Because okay. Nowadays there are some kind of modeling softwares are there. So like a MATLAB is popular. So all the blocks are available. Okay, dynamic models are available. They built it. Now simply we'll try to interconnect between them. So that way you can do. And then is we can do the design, system level device level and then system level design we do that. So that means if you want to incorporate this agri PV solar system or any generalized PV system, then what kind of solar panel? What is your need? What is your load capacity? What is your solar system you are proposing? What is your battery capacity you are proposing? So all these things, we should need to come up with a design. Okay. Then why we are proposing some kind of 2-level inverter? Why 2-level inverter? Is it why not 3-level inverter? Then you are proposing with some kind of energy efficient solar. Why not other? Is it right? So that kind of all questions we should come up. Then if you are selecting a battery, again what kind of battery you are choosing it. So that is a design point of view with the sizing that we need to complete. So then we can do the simulation. Okay, design incorporate with the sizing. Okay, sizing we should do, and we'll do the simulation. Nowadays simulation softwares are there. We'll try to incorporate all our input to the simulation software. And now what we do is we'll do the analytical and critical studies. We do that because mostly this system is known system. Okay, most of the systems what we try to do that is a known systems only. Solar, renewable energy, electric vehicle, whatever it. Then we know the base case study because we'll have previous reference will be there. So we'll try to simulate that and same one, and then we'll try to analyze it, and we'll make some kind of critical studies. Okay, we'll try to bring the critical study, and then we'll work on the control techniques also. Okay, what is a better control technique? Already people, industries or whatever manufacturing, they propose one technique. Then we'll propose with different techniques with advantage. And then finally, we need to see that optimized techniques. In engineering, everything, we should end with optimization. Is it right? So then what is optimized techniques in terms of control, in terms of sizing, mostly is design and sizing and then control. So optimization you need to. So that will optimization to bring your cost down, total equipment, whatever you're trying to sell it in the market. And then next is you will try to compare. So always the comparison is required. So you have one system you're working. Similarly, in market, other system is there. What is the comparative study? It's a very general question. It's not only academician, for industry also. Otherwise, they cannot stand in the market. They should do internally a lot of comparative studies. They do that actually. Okay, they don't disclose to others, but they do that actually. They will make a comparative study. Then only they can prove that yes, my system is superior to others. They can prove that actually. And then you can go with development. Okay, maybe fabrication kind of thing. And next is you can try to integrate. Sometimes you need to integrate with the different parts. Maybe communication part, you have a hardware, electrical, say electrical embedded board, and then communication part. You can try to integrate them and bring more features for better interaction and all with the users and vendors. And next is you can have experimental studies. You can do that, and then performance validation. You can do that. Okay, and this is what here we can completely we can do. So generally these are the steps. Even with academic projects or industry projects, generally they follow this modeling to performance validation. Okay, so this. And sometimes directly we can work on if it is ready-made system. Suppose your college having the solar power plant is there. Okay, one can work on directly experimental studies, performance validation. We don't need to work on previous things because already optimized, they are already feasible by a customer. I mean, manufacturer they installed here. So a BTech student will go and then do the performance validation of solar power plant in Vignan Lara. So directly that is BTech project. So it doesn't need to work on previous. So if at all any kind of abnormal things is there, then he will try to see that dig into previous details. What kind of control technique used, whether his MPPT is good or not, what kind of MPPT is, whether we can propose better MPPT or not, something like that. And now India is right now it's standing at 40th position in the global innovation index as per the last year status actually. And patents we increase our rank, that is we are standing at 7th position right now. So this is we improved actually. So India has improved to 60th rank actually. So compared to previous 79th rank in the 2019 as per the network readiness, because now we completely depending on network readiness, is it right? So internet connectivity and other things like that. Now I'm going to, since it is a FDP program, I just give you some kind of a glance on what are the wings of the faculty profile, research profile. So one is faculty generally will have 4 domains to work on it apart from academics, administration. So one is paper publication. Is it right? Paper publication where you have journals, conferences, and book chapters. 3 are important for us, for academics. And next is funded projects. Okay, funded projects for our projects. So we will seek the support from state government. There are sometimes state government will call for it, and or we will try to go with our own proposal. If the fund is available, they will give us. And next is central government, DST, and other agencies like UGC, AICTC, or many ministries also nowadays they are advertising the post. I mean, this grants. That's one. And then of course internationally, if you have any collaboration with any universities and all, they will give also grants also. And next is industry. If you have you have a solution to the industry problem statement, then if you I mean prove that proof of concept, okay, then they will ready to fund your project also. This way you will get a try to fund the projects. And apart from this, one can work on this IPR. So directly, instead of going with now this journals and all, if you have novel work, then you can go with IPR. So you can go with patents and technology transfer. You have a patent and then technology transfer, you can do that. And if you have those patents and technology, if you want to use them, you can start your own startup and then launch your market. That is one. Or you can go with the consultancy services. Maybe you can have government related and the industry related, or you can make your own venture startup house. So that way also in the consultancy also you can get. So many engineering colleges also they try to get consultants from state governments also. So electricity, pollution board, and irrigation, lot of things. They give consultancy, colleges also, where we can generate the consultancy slowly. So that is, we can generate that. So this is our final, four wings of faculty research profile, any faculty. And this is one project actually where we have, DSR, Common Research Technology Development Hub is there. So where myself, Sandeep, and then Dr. Shankar. So both we are, project managers for this actually. So where we are working on closely on renewable energy with integration with the electric vehicles also. We have good set up state of art facilities are there. We can go to detail. We have list of equipment is available. One can visit to our center and then they can try it. Our aim is here mainly to collaborate with MSME companies. Okay, our research should be catered to the needs of their requirements. So we should take the MSME problem statement, we should solve them and then deliver this technology to them. So that way. So in between, if anybody wanted to involve and participate, we will welcome. Suppose you have any problem statement or nearby MSME company, but you wanted to help them. You have knowledge is there, but you don't have facility. But then you can approach us. So we have facility, you have knowledge, and you want to help your own industry nearby. So who contacted you? Then you can bring them here. Then that way you can be as a part of the collaboration, and you can also get involved in this research work also. So this is one of the unique platform where we have built at NIT Andhra, our Department of Electrical. And how to execute plans generally. So one is allocate time. This is general tips for a faculty. So allocate time separately, and we should engage it. That's that needed. Okay, so that is compulsory needed. Next is motivate students first year to final year, and then mentor their project work mini and major. So don't wait for the project in a final year or something as per curriculum. So then you will be lagging in research. So whatever in the first year to final year, you should motivate the student for many project works. Okay, and that somewhere they will have some kick start actually. Maybe from first year itself or second year itself, we try to motivate to do some mini project, and third year itself we can do some major project instead of final year. So that way they will be trained in first year onwards or second year onwards. And also you can collaborate with other faculty within institute, outside institute. This faculty already doing it. Most of the places they are doing it actually. And of course you can build your research time and strengthen it. Okay, this is a final solution, and you can also launch your startup on the team. So this is also another practice one can do that, because now colleges and government they are allowed to make your own startup, and we can contribute to research also. That's option. So now main successful execution is, so you need to build your research team. Okay, engineering colleges, any college, even IIT, NIT also. So faculties are not alone. Okay, they have a team with the majorly with the help of students only. So we do have PhD students, JRF, and then MTech students, BTech students like that. So we have a research team are there. They are trying to execute our project first. We give them. So similarly also, so you need to build your research team with the help of students. If you have available only UC, then build your students, two students, three students, and connect with the group, and then give the task from second year onwards, and then that's how you can do that. And tips, one is open access. I think good news last 2 days ago, government is subscribed for one nation, one subscription. So most of the colleges, all the colleges may get the access to all the journals, including engineering colleges, I believe. So we'll wait for it. I think then you don't need to depend on only open access. Then even all subscripted journals also one can download it. Okay, government is approved it, central government. Okay, yeah, all journals.
Even IEEE.
All journals. Government will subscribe and they will give to free of cost to everyone. So that is recently, just 2 days back, cabinet, central government cabinet has approved it actually.
Okay.
So maybe that will reduce the burden of all engineering colleges and faculty. So previous to that, I was recommending open access. You don't need to worry, but that will resolve our problem. And next is read the papers carefully, understand technical language because sometimes we do, but we have failed to put them on paper, technical language. Okay, because already we have references will be there. So let us simply follow that. What kind of how the reference paper has. He has followed same pattern. We should also do that actually. Okay, and then you should choose a mentor. So mentor will be useful for guidance and collaboration, publication, and then select a research area with minimum no experiment. So starting stage. Okay, if you don't have teamwork properly strengthened, then choose your area. No experimental, no minimum. Even without hardware, also one can publish with electrical engineering journals IEEE transaction. That is possible. Okay. And next is execute your work with open source tools. Sometimes we don't have any tools. Okay, proprietary items like any software. So if you don't have it, that then you can go with open source tools. Okay. I think yesterday. Huh? Kaggle is one. That is a good platform. Homer is there, but there is a trial. 21 days they will get a trial on energy optimization between hybrid energy systems. Actually. Okay. And I'll share. I have a list. Python power electronics is there. We have some power electronics, and then next is this power system related is there. This tab is there. That's one. And one more is there. Many are there. I'll share that. Okay. Of course, other programming based nowadays fully depend on Python. Very popular actually. No. It's not like. Then is publish your papers only Scopus and Web Options. People will recognize that, and then publish in IEEE conferences. And types of sources, open source we will get in software and then coding, also server and cloud computing, hardware. Hardware means in open source, some of the hardwares we can try to change the manipulate them. I mean, suppose you have Arduino and Raspberry Pi, so we don't have restriction to change this kind of configuration. There are some companies, if you buy it, we cannot change them. We don't permit us to change them. There are some hardwares we can try to change them the configurations of. That means the open source hardware. Okay, that's the example. And then these things are free to use, free to share, free to change. You can sell the work to others also. This is advantage going with the power open source. And if you have any startup idea, and in case of electric vehicles or agri PV or any other electrical related, I think we welcome you to us actually. So we will brainstorm you, and then we will help you from scratching to build this, launch your startup. So that way, even NIT also we encourage incubate startup, but we are not so far incubated other startup outside startup. We incubated inside these startups only, NIT online startup. But still we welcome anybody is there, we can approach us directly. Okay. So with idea, without idea, still you have interest, you want to launch your startup, you don't have idea, then still you can come us. We have ideas, we will provide the ideas. Okay. So that's it. And finally, three important learnings. One is continuous learning is important, otherwise you will be get outdated in the professional journey. And is self-learning, because once you graduated, nobody will be there to teach us. So everything every day is faculty or engineers or scientists is going to be learned through self-learning process only, and global learning. So whatever technology you are learning, so that can be adapted to any area. Is it right? Global. Now that's what many times today morning we discussed a lot of agri TV applications and trends well established in the USA. Then we are trying to see the reference and then we will adopt it in India. So that is what global learning is very much important all the time. And this is my final slide. Opportunity types. One is opportunity will come and knock your door. So your duty is you should open the door, and whether you want it required or not. You have to take a decision. Is it right? So that you should do that. And you need to search a long way and get the opportunity. Sometimes you need to spend time, you need to travel. Is it right? That you should do. And sometimes call for opportunity will be there. You need to come forward or apply. Maybe this FDP is announced now, very innovative topic. Then seats are limited now. Then you need to come forward and apply for this FDP. So that's the one thing. And next is plenty of opportunity around you always, but those are invisible. But your duty, you should identify and grab them. Is it right? Maybe you think that maybe some ML faculty is not there, but in our own department there is one faculty who is working. Maybe other department is working, so you don't know that. But you need to investigate yourself that those are invisible. Nobody will keep that a faculty no nameplate board. These are my working here. This is my paper. So, but your duty you should search his Google Scholar, his publication, and then go and talk and interact with them. So that is what invisible are. So sometimes call for opportunity, first come first service base. Many places, okay. Even like whatever bus, train, is it a seats are limited? Cinema hall, is it a food, whatever the capacity is same, whatever they eat. So guest house, whatever it is. So many times. That's why you will get an opportunity in life, professional way. So any form you get it. So don't neglect it. Whatever now you gain the knowledge today may not be useful today directly, but it will be used in other way tomorrow, any other format. Okay, that's what opportunity you should take it part of. Okay, so thank you. And finally, the summary of today both sessions, morning and afternoon. We started with morning, challenges and opportunities with the agri PV system, and we have started with the energy demand and then renewable energy, and what is the significance of the solar PV system, what is the role in particularly in the agriculture sector. So starting with the solar water pumping systems, and with the reference to different industry statistics, and then parameters we have seen, and of course government guidelines also we have seen. We are related support to the agri PV systems actually, and we discussed with reference to NREL, US, and then the DOE also, Department of Energy also. So like that we have discussed, and finally we understood what is the importance with reference to the sustainable. If you want to bring the sustainable agriculture, so what way this agri PV will help? PV solar PV will help you. That we discussed it. And then next is, we have seen this real challenges. So what are the challenges? So because the crops are different, technologies are different. See, we try to mix them. So whether you try to enhance the productivity or income also. So what are the challenges? And overall, then we have seen the opportunities also. Also, afternoon session, we have discussed, future opportunities, not only solar, maybe you can incorporate beyond the solar small wind, because that possibility is there. And then you can bring the bio also. Bio is very closely connected to the agriculture sector. Then you can combine them all three sources, and then you can form a microgrid application also. And then finally, we have discussed the key performance indicators. So we have set up performance indicators are there to analyze the performance of this agri PV, and we need to calculate the as per the formulas and see the particular crop, and whether you are that performance index are within the limits or not. Okay, beyond that constraints or not. Then you can judge that whether that PV system is suitable for your crop or not. So that way you can judge it. So those are all things we have discussed today. So this was the summary of today's both sessions, morning and afternoon. Okay. So if you have any questions, and I'm open to any question and answers, please.
Sir, regarding this agri-PV, can you publish papers theoretically only and theoretical analysis using?
Yes, maybe you can take help of data first.
Okay.
Data is maybe in terms of solar irradiation is a data.
Oh, yes, that is data.
And similarly, crop data also.
Crop
Like
data.
we have taken one case study we discussed today. So like,
How much
yes.
irradiates that data will know.
Yes. I suggest you to go to with some kind of modeling software. I showed you one slide, where the modeling we can do with the PV and then crop modeling.
Okay.
There are some softwares together are there.
Okay.
So where you can take the software reference, and then you can put the both data, PV and crop data, and analyze it with the different crops, different solar and all. Then you can do that actually.
MATLAB only.
Not MATLAB.
Okay.
It's a different software.
Okay.
Thank you.
Thank you, sir, for sharing valuable knowledge to the participants. So actually, sir, I explained so that these sessions will be very useful to the research scholars and faculty members. So thank you, sir. Actually, we have given the titles, opportunities and challenges of agri PV systems, but you have given me opportunities participants also because you have explained many things. So thank you so much, sir. Thank you for accepting the invitation, even in your busy schedule. So now the felicitation, respected HOD of OEEE, Rajini Madam. Madam, speak something about sir.
Good afternoon, dear participants. Sir given very useful information. I hope that all of you implement those points in your research work, so that that will be helpful to the students as well as to your organization also, and your career growth also. Thank you.
It's okay. I think not visible, better to stand. వాళ్ళు కనిపించాలి. పర్లేదు కనిపించాలి. థ్యాంక్ యూ.
Thank you, sir. Thank you.
Thank you, sir. Thank you.
Dear participants, now we'll discuss the article discussion. So here the first paper is all of you take the papers. If you have any difficulty, attender will come and will give the papers. So the first paper is all of you see the first paper. So the current status and agri-voltaic systems and their benefits to energy, food, environment, economy, and the society. So this paper is published in Sustainable Production and Consumption in the year 2022. This is the latest paper. So this paper actually, so the given the definition of agri-voltaics and different structures of agri-voltaic systems, and how the agri-voltaic systems are useful for uh, uh, to save the energy, food, and environment, economy, and the society. So this is a very good paper actually. So those who are working in the agri PV systems are those who want to write the articles, research papers or conference papers. So this is a very useful research paper. So now these all of you take the papers, research papers. Then we'll start the discussion. All of you take the papers. If you have any doubt, I will come. The integration of a solar power generation with the agriculture activities referred to as a agri-voltaic systems, representing the promising solution to address the dual challenges of a growing energy demand and diminishing agriculture land availability. So this paper highlighted um, in the abstract the innovative approach between the PV systems and crop production. All of you see the abstract. All of you study the abstract. I highlighted the points in the abstract. All of you go through that. So the agri-voltaic systems, which the PV system, the crop production. So this paper is related to production and the PV systems. That is known as agri PV systems. The two systems are mentioned in the this paper. So see the keywords also. The keywords also identified: agri-voltaic system, conventional solar power plant, land use efficiency, net electricity demand, solar power generation. So these are the keywords. All of you try to modify you study the paper and note down the points. So in the abstract, two systems are proposed. One is agriculture activities on available land in pre-existing PV facilities. The second one is systems intentionally designed and installed for co-production of agriculture products and PV power. So these two systems are discussed in detail in this paper. That is abstract of this paper. They have given from definitions to so the existing all the literature. My suggestion to is first see the all of you study the abstract, then note down the key words completed, see the introduction. I highlighted all the points in the introduction. The solar energy is a cleanest and the most abundant renewable energy source. So in the studies, you might study the conventional energy sources. So that is a thermal power station. The thermal power station is by burning the coal, the environment is pollution. So that is not a clean energy source as compared to the solar. Solar is a renewable energy sources. Nuclear power station. So basically we are using the steam turbine. We have to give the steam input to the turbine. The turbine output is given to the generator. So the generator converts the mechanical to electrical. So therefore here also the environment is polluted. So as compared to the conventional energy sources, the thermal power station and the nuclear power stations. So the solar energy is cleanest. So that's why they have written. So they made the comparison between the conventional energy sources and the solar energy. That is the first point. And also, so these most abundant renewable energy source. So because the yes the solar PV systems converts the solar converts we are going to get the DC voltage. So that point is mentioned that the PV systems. Mentioned in the introduction. So the one agency is there. So that is International Energy Agency. So they every year they will publish the data related to energy. So in the paper it is mentioned 2021 photovoltaic power systems program. They mentioned they have given the global PV power plant capacity at the end of 2020. So you can 70 gigawatt according to the paper 2018. So they have given they have compared the solar system in the countries that are China, Europe, and United States also. They have given the amount we see the references, the more number of references also given in this paper. All of you go through that. So all of you open the paper number 1 and see the reference also. Then you can get the idea. So many reference papers are included. So it does not include the numbers here, but the format is different. So there is not a IPA format. In IPA format, we are going to get numbers. Here numbers are not available. So then this styling, reference styling is different, right? So the introduction they have given the about the solar development in other countries like that. So the next highlighted point is according to the global development ground mounted PV generation plants, demand for the solar power plant land construction will increase. So the resulting in increase in the combination of agricultural land. So the that is a PV system to generate the large amount of power by using the PV systems. So the more land is required. One side the population is increasing. So we need the more power. So suppose if we want to generate the more power by using the PV systems, we need more land. So there is a there is a commutation, okay, between the land use and the power generation. So that point is as mentioned. So the next one is to solve this problem. So that is at the same land. So the crop will grow as well as the generation of power is possible. So therefore the one solution, okay, this is one solution, agri PV systems. So they have grown dramatically in the recent years with a global installed capacity 2.8 gigawatt by 2020 from 5 megawatt to 2000. They have compared the year, that is a 2012 to 2020. So that they have given. So there are two recommendations for agri PV systems implementation. After the highlighted lines, you can see the two recommendations of agri PV systems. So the one is the pre-existing PV facilities. The second one is the system intentionally designed and installed for the co-production of agricultural crops and the PV power. So these two ways the article is discussed. According to the research conducted from 1980 to 2022, PV panels land use focuses on installing the PV panel systems with the agriculture plants. The land can be valued by designing and installing the PV panels in such a way that the plants can capture the enough sunlight while minimizing the associated problems. Okay, this point is highlighted here. If you see this point, so the next we will see the advantages. We have mentioned the advantages of so the advantages of implementing the solar plants in the agriculture are very significant. So in the end they have given the future direction in this how the integrate agricultural activities into the pre-existing PV panels by utilizing available land benefits from the agri-voltaic concept. In a systematic way they have given. So this number one introduction. This is introduction. All of you go through the introduction and note down the points. So if you see the next one, that is agri-voltaic ideas. So that here in the literature, actually these are not a for India it may be new, but in the other countries. So actually agri-PV systems conceived by 1980. That is Jastro 1982. He developed the agri-voltaic systems. So the different names are appearing in the literature. So that is agri-PV system, agri-voltaics, agro-photovoltaic, like that. So in the most recent papers you can see the agri-voltaics. So that is a 1982. That is a starting point to review to write the literature review. So this point is important point. And the PV panels were installed 2 meters above the ground. So with 6 meters between the individual PV arrays. So this configuration allowed the sufficient solar radiation penetration under the PV panels for the plant growth. In the year, so the 2004, Japan developed an agri-PV systems prototype. So the Japan developed in the year 2004, they developed the agri-PV systems made up of multiple systems known as solar sharing. This prototype was transformed and improved until Japan had over 1,000 agri-PV system sites. So the term, so the agri-voltaic system was first used in the year 2001. So the research papers it is in 2001. So it is actually so that is 1918 to they developed something. So it is popular in the 2001. In the India also in the year 2012, in the Gujarat state they implemented agri PV systems. The government given so the many funds to agri PV systems implementation. So the under the scheme, so the PM Kusum scheme, so we will get the PV panels subsidy will get, solar pumps also will get. So that they utilize the opportunity, so that they install the agri PV systems. So the very in India in the year 2012 the experimentation started in the direction of agri PV systems. So this paper they have given in the Japan. So the Japan cited in this paper. So then you will see the co-production. You will see the co-production. Co-production. So the co-production has received significant global research attention. So for example, in the year 2022, so the design analyzed in the tracker PV system tracking and band tracking technique between the rows of a olive grows in the 1.3.0 meters students are discussed the various today's session. So the sir discussed the many performance indicators of agri voltaic systems. So these are one performance index. So they mentioned the one performance index. So that is a land equivalent ratio (LER) for agri PV systems. So in this study, so the ranging from 28% to and 47%. So the multi-scale modeling techniques are used. Let me go through that. So the point number 2, all of you see the papers. Point number 2. So the agrivoltaic ideas are given. Agrivoltaic ideas are given. All of you try to note down year 2011, 1982, and 2022. Okay, so these years, what are the mentioned in the paper? Okay, all of you try to study that. Next, go to the agrivoltaic systems. That is the number 3. We'll move to the number 3. So the 3.1 land used under pre-existing fixed PV panels. Under that, that is planting under the PV panels, planting between the PV arrays. So these two points are mentioned. Planting under PV panels. The limited sunlight intensities, agriculture planting under the PV panels of a fixed PV systems without agricultural pre-plants. You will see the figure number 1. All of you see the figure number 1. First see the figures, then we can study the paper, then we can understand easily. That is one way of these are figure number 1. All of you go through the figure number 1. Try to note down the points. Then we will see the table number 1. All of you move to the table number 1. Table number 1. So the beautifully they are written. So the agriculture land use under the PV panels of a fixed PV systems without the agriculture plants. Without agriculture plants, only PV systems are there. So that we have mentioned the first year, pattern and condition, the results and discussion, and the reference also they have mentioned. So in the year 2005 publication under PV panel. So that here the condition is here that is a panel installation, type of plant or animal, the variables. So they are mentioned in the 2000 year paper under the PV panels. So the panel installation is fixed and the type of plant animal that is so the T variables, the internal rate of a return. So the is one of the performance index of a agrivoltaic systems. That is our next parameter. The considered is the net present value (NPV). That is another important parameter. So if you see the results, IRP of 15.74% discount rate. So the greater than 3.3% and the NPV of. So that they have mentioned in the dollars, US dollars. Planting T under the PV panels was discount to be economically feasible. They concluded the paper. So this under the PV panels, so the T is economically feasible. They concluded. So that is a reference number 2015. So that end you can see the year, so that you can identify the references easily because here this part this general that is references numbers are format is different. So normally we are going to identify the IEEE papers so number 1, 2, 3, 4 like that. So this paper is sustainable production and consumption. So the reference styling is different. So in the next year 2016.
2016 pattern they have given between the PV arrays. So the type panel installation is fixed. So the now the type of plant aloe vera. So the here they have considered a variable that is a co-production, the co-production. So that in the year 2017 between the PV arrays, so the type of panel installation is fixed. So they consider the plant is grape, grape. So the efficiency of a PV systems and feasibility in relation to the production. So that is a variable they have taken. All of you note down the points. All of you need to submit the report. Article discussion number 1 report. Then year 2017, there is a 2 papers are mentioned. 2015 1 paper, 2016 1 paper. 2019 under the PV panel. So that here also they have used the fixed panel installation. So the type of the crop, the chilies are taken here. The variable parameters of power output. Okay, they have taken the power output. So that here all of you to identify the references. All of you see the years so that you can identify the references easily. So it is possible to download all the papers also in the SCI hub. Some papers can be downloaded from the SCI hub. So the you can get if you type the title, then you will get the DOI number. If the DOI number is given into the paste into the SCI hub, so then you can download all the papers. Sir told Dr.V.SANDEEP sir told that so that it is easy to download the papers. The government of India so that taken the permission to download all the papers freely. So that is another opportunity. So now this even it is possible to download the papers. So that yes, you have used some papers normally some paper the latest papers 2024 23 papers may not be downloadable, but so the previous years the paper will be done. Most of the papers are it is possible to download. Then we can so the see the entire thing. So that is what they have written, how they are getting the different performance variables like that. So in the table number 1, lot of information is given. So the related to agri-PV systems and so the type of crops, so like that. So like in the recent years also there is a 2020 under PV panel and between the PV array. So that here fixed the installation is fixed. So that here the sheets are taken. So the next one is here the power output and CO2 emissions taken as a variable. So here 2022 under the PV panel system. So the here also installation is fixed, but here they changed the there is a weight, there is a animal, there is a so that see the thing. The next one is here the parameters are power output and cultivating crops. So in the recent publications, all of you see the table number 1. Try to complete the table number 1. All of you see the table number 1. So this is related to table number 1 is related to. So there is a agriculture land use under the PV panel of a fixed PV system without agriculture plants. Without agriculture plants. This is our table number 1. So all of you move to so the table number 2. Table number 2. Table number 2. So they given lot of information on land use under the PV panels planned for agrivoltaic systems installation. So the table 2 given so the lot of information on the second. So the in the initial there is abstract we so we have seen that this paper reviewed the so the 2 directions. The direction number 1 is completed. So there is a table number 1. All of you see the table number 1. Table number 2. So the table number 2 they have given the second type of system. Second type of system. So all these figures you can observe the different PPTs they explain. Business persons explain all the figures.
So see the figure number 3, the PV systems under the animals. Animals under the PV systems. This type of analysis also reviewed in this paper. So the all of you see the move to the table number 2. Table number 2. All of you see the from here they mentioned the year, condition, panel installation, type of plant. So the variable here also results and discussion and the references are given. So the year 2010. So the year solar energy applications for agriculture. So this paper given how the solar power is used for agriculture purpose. So the research persons also explained the different applications, solar applications for agriculture purpose. So there is a solar pump is one application. So the solar pump is an application. So the Dr. Elan Sastrigar explained the different solar energy application for the agriculture purpose. So this paper reviewed that one. Next year 2012. So here the panel installation is fixed and the type of plant is salad vegetables. So here the variable is shading. So the shading effect is considered in this paper. Here 2012 greenhouse. So the condition is greenhouse. Next one is here the type of plant or animal. So is here onion. Onion is taken. There is a 12% PV on greenhouse. Allow me try to identify. So what is literature? Previous literature work. Previous literature work. There is a 13. So here there also the panel installation is fixed. 12, 13 also 13 fixed. See the type of plant, animals, variables. Then all of you see the results and the discussions. So here the table number 2. So the more number of references are there. So all of you see just to go through the results and the discussion. Then you can understand how the agriculture PV systems. In the year it will take more time. So that these are very this type 2 system. So the literature is more number of papers are mentioned in this one. So the latest one you can see, latest one 2022 like that. So you can see the 2022. If you see 2022 papers, so the fixed and greenhouse. So the fixed and greenhouse. So here type of semi transparent PV systems modules are taken. So compared with the other STPV modules, crystalline silicon modules are commonly used in agri voltaic systems due to their low cost. So the cost is less, that's why they have used in this analysis high stability and high efficiency. These are they have completed the paper like that. So the year 2022 between the PV and array system, olive tree, okay, they have taken so the plant is olive tree. So the tracking and back tracking techniques for the horizontal track and PV systems. And 2022, so that the type of installation is fixed. So here a blueberry. So here so the plant they have taken is a blueberry. So here fixed bifacial agrivoltaic. Fixed bifacial both sides. So there is for the based on the surface. So you can select so the bifacial agrivoltaics. You cannot use anywhere all the conditions you cannot use the bifacial agrivoltaics. So based on the surface, so you can select so the bifacial agrivoltaics. So next 2022, the type of installation is that is fixed and they are taken. So the thermomaric, the efficiency of a system of 3 different designs are taken. So they have uploaded for average yearly revenue. They have calculated the revenue. So the LER and the payback period. So the 6 kilowatt agrivoltaic system with double row array design capacity is the best system. Resulting, so that they have mentioned the values also. So that in the dollars, so that the payback period, everything they mentioned. So the second type of analysis and the equivalent ratio of agrivoltaic stations. All of you move to figure number 4. The top views of a installed agrivoltaic systems. Top view they have mentioned figure number 4. They mentioned the installed the installed agrivoltaic systems. Different top views are mentioned in the figure number 4. So here the aim of this paper is that is relation between the energy, food, environment, economy, and the society. So that point is mentioned in the paper that all of you move to. So that is page number 598. Page number 588. So all of you see the papers already. So the papers are distributed. Go through that. PV system installation on a greenhouse rooftop. All of you see the figure number 5. Figure number 5. All of you see the figure number 5. All of you see the figure number 5. PV system installed on greenhouse mounting. So that here they mentioned the energy impact, food impact, energy impact and food impact, and the environment impact. Next one is the economic impact. The paper idea is so the impacts of the food, energy like that. So therefore they have written all the points: energy impact and food impact, environmental impact, the economic impact. So then you see the figure number 6. See the figure number 6. Here the relation between the energy, food, environment, and economy and the society with respect to the agri-voltaic systems are given in the beautiful figure. All of you see the figure, then you can understand. So the electric distribution, see the solar power plant, agrivoltaic, agriculture, and then electricity. So the electricity is where the electric distribution. So the decrease the CO2 emission. All of you see the flow chart. Then you can understand. So the relation between the energy, food, and environment, economy, and society with respect to the agrivoltaic systems. Social impact. Social impact is you have to write in the article report. Social impact. Okay, so that is important point. Social impact is very important point. You have to write. So all of you. So go through the 7.5 social impact. 7.5 social impact. Read that. All of you read that. Social impact. What is the social impact? So they have some positive effects on economy and the society for upstream and midstream and downstream stakeholders. Agri-PV systems foster the connection between energy, food, and environment, economy, and society. In addition to these three, increase the electricity generation, ensure energy and food security, reduce the gases, the emission, add value to the land use, improve the access to the electricity for agriculture lands and the communities with the power outages and expansion opportunities at a power plant and required co-production. However, these systems implement has been limited. The system maintain necessary requires the specific skills that most of the agriculture struggle with. Only write so in your own words in the article discussion report. There is a social impact. So the point number at the end of the paper they have mentioned. So this 8 and 9. 9 is a conclusion. 8 is the future prospects. So the future prospects also mentioned in the paper. So with the continuous advancement of a solar energy production, the mathematical models for predicting the effects of a planting agriculture and the PV panels that are used for solar power generation would be beneficial in order to shorten the time required prior to the practical implementation. So this point future prospects also you should mention in the article discussion report. Now we are at the conclusion, almost we are reaching the article discussion number 1 conclusion. So here the 4 points are mentioned. 4 points are mentioned. So in the conclusion, in order to shorten the time required to investigate the effects of a cultivating land under the fixed solar panels on solar power generation, a mathematical model for predicting agrivoltaic systems should be investigated. So these feature these direction. So the crops suitable for planting under fixed PV systems along with crop growth parameters should be identified. Agrivoltaic systems must water plants on a daily basis. The material corrosion should be monitored since moisture under the solar panel may affect the plant structure. Appropriate agrivoltaic policies should be implemented to reduce the competition for agriculture lands and forest and to also support the local people. So the support is very required because the farmers so you have to motivate the farmers okay to use so agrivoltaic systems so that to increase the so the income revenue generated from agrivoltaic systems because this is a new technology. So the in India, so therefore you have to motivate the farmers so that to use agrivoltaic systems. Okay, now all of you take. So I will show you how to write the report also. These are two systems are so discussed in this paper. So here the definitions, the definition of agrivoltaic systems. So we started in the year 1982 and so year 2011 there is 2011. So here 2011 the paper is very important. There is a if you see the download the paper. So there you are getting the more information on agrivoltaic systems. Different. So if you don't know anything, so is the best paper. So they explain the beautiful way. So what is from definition to so the different definitions related to agrivoltaic systems. This time I am giving the model how to write article discussion report. So for this paper, so this model only. So the first you have to write in the previous article discussion also I given the format. According to the format you have to write here your name, your institution name. So the title of the FDP like that you have to mention. So this I am giving the related how to write. So the first one is introduction. How to write the introduction. So the next one is this literature paper. So therefore you have to write a literature work related to agrivoltaic systems. So the next identify we have to write key highlight points. Key points. There is a type of agrivoltaic systems. So in this paper, the two systems are mentioned. The pre-existing PV systems are utilized for agriculture activities. That point you have to write here. So the intentionally designed system to co-producing the crops and electricity. Okay, so this the main aim of this paper is. So the two systems are discussed. Okay, so you better to mention these two systems. Next, what are the benefits? Okay, you have seen so the energy, food, environment. So the next one is social impact. So write these points in the under the heading benefits. You write your own words, that is energy, how agri systems improve the energy efficient, food, environment, and economy and society. I have given simple points, all of you go through that. So enhance the electricity generation capacity and efficiency through the better land utilization. The next point is food complementary land use ensures the agriculture productivity is not a compromise. Next, environment reduces the forest innovation and the carbon footprint by maximizing the land efficiency. Next, economy provides the dual revenue. So the one from crop growing, other for generating the electrical power. So therefore, the economy the revenue will be generated for the farmers. Society supports the rural communities, promotes employment. So some of the rural areas, some if we give the training to the student, those who are completed 10 plus 2 or degree, so you can give the training. So then, so that is we will generate the opportunities for the rural people. Okay, how to write like that. Next one is challenges and the current status. So this is a limited research on agriculture use under the ground-mounted PV systems without prior planning. Ongoing global solar projects indicates the rising trend in the agri-market adoption. Yet the practical implementation remains in its the initial stages. So these are the challenges and the current status of agri PV systems. So next is how to better to include the policy implementation. Policy implementation. So that is the only model. Whatever you feel, so all of you go through the paper and write your own words. Okay, don't copy because most of the participants are new to Atal MDP. So that's why I'm explaining. So you have to write the paper like this and you have to submit. Now, so the critical discussion. You have to do the critical discussion. The dual functionality of agri-voltaic system places them at the next. So the energy, food security, and crucial in the world. So the climate change and the increasing the population. However, the potential for so the widespread adoption faces several challenges. So like this, we have to submit the article discussion report. This only model. Don't copy from other. Okay, so the next you have to give the conclusion. Next you have to give the conclusion. Okay, so this is about the article discussion number 1. Next we will see article discussion number 2. Article discussion number 2. Okay, so this first paper discussion is completed. Now you can see the second paper, article paper. So these are very interesting. That is this paper. So that is a case study on the power generation from the agri-voltaic system in India. So this paper is published in International Journal of Environment and Climate Change. So the year 2023. So this is the latest paper. 2023. It is published in so the International Journal of Environment and Climate Change. That is a 2023 paper. So the title of the paper is the case study on power generation from the agri-voltaic systems in India. So these are title. All of you take the paper number 2, especially this paper. So that discusses they have taken the one case study. They explained each and every parameters. So in the Indian context, this topic is discussed. This study focuses on evaluating the performance of 7.2 kilowatt solar photovoltaic power plant installed at the Renewable Energy Department of College of Agriculture, Engineering and Technology, Junagadh Agriculture University, Junagadh Agriculture University in India. So that there they have made they have constructed 7.2 kilowatt agri PV systems. Okay, so they have studied for 1 year. So they are studied for 1 year. The findings offers insights into the efficiency and energy output of a plant, contributing the broader understanding of a agri PV systems applicability and integration with the agrivoltaic systems. So here the key points. So there is paper key points are. So there is performance the performance indices. Performance indices are average. So the system efficiency and the capacity factor. So the performance ratio. PR. They have taken the way. So the Dr. Sandeep sir explained the different performance indices. So the second session. So these are the three parameters they have taken into the account. So that they analyzed so the agriculture university, that is so the renewable energy engineering college of agriculture engineering college is this is situated in the Gujarat state. So I already explained the year 2012. So that's Gujarat state. So the government is given so the lot of funds to install the agri PV systems. So I think this is one of the funding project, I think. So so they have done the analysis for the capacity 7.2 kilowatt. Yes, so all of you see the go through the abstract. Abstract they also mentioned that is this study evaluates the performance of a 7.2 kilowatt. So the solar agri PV system power plant that was installed in so the field of Department of College of Agriculture, Engineering and Technology, Junagadh. So they have mentioned that is 70 point east. That is if you LR Shastrika have explained. So it is possible to take the data. If you give the 2.5 year and 7.1, you will get the solar data. So like that they have mentioned that you can check with the help of software also. According to the International Energy Agency. So the agri PV systems power plant performance was evaluated. So this paper is evaluated the performance according to the International Energy Agency. So this agency will every year they will produce the data related to energy. So the especially solar power, wind power. So the energy sectors data. Okay, every year they are publishing. Even if you see the electrical vehicles, how the electrical vehicles are increasing by year. So these are one of the source to get the increase. That is how the research trend is going in the different direction. That is PV systems and electrical vehicles. So like that. So this is a IAI, International Energy Agency say so that they will provide data, good number of so data for the various topics, not only so the solar systems, so the other parameters they will give. That is a power plant was properly observed for the whole year. Okay, 1 year they observed. So finally they have computed they calculate the average system efficiency, capacity factor, and overall performance ratio were found to be. So that they have given the values. Three performance indices are given. So the 80.83%, next 60.03, and 12.07. So they are given the values also during the experimentation. 1 year they have studied. So the total the capacity of 7.2 kilowatt capacity agri PV systems. So they have three performance indices are calculated. So here they have mentioned so the was total. So the energy produced during the experimental period. That is a 1 year they have studied. In the 1 year the agri PV system how much. So there is a power is generated. So that value also given in the paper. So the performance of this agri PV system is produced equivalent solar power as it is from a PV systems installation. So this abstract of this paper. So now we see the note down the keywords also. Here agrivoltaic power plant. So the final and reference yield and efficiency. So if you want to change the in the report. you want to change the keywords, you have to write. So that the report you have to write. So that's why. So there is no need to copy from directly from paper. Okay, study the paper. So that from that you can get that. So that is first you see the introduction. So here in the introduction you can see. So that is we have mentioned. So it is the world population. So as the world population is increasing. So here the food requirement is also increases. So they have given so the good number of papers in the introduction number one. Introduction number one. So these are literature related to the agri-PV systems. So the next point, that is objective. What is objective? Objective already given in the abstract. Again they have repeated here. So in this work, 7.2 kilowatt agri-PV systems of plant performance is carried out with the following goals in mind. So the one is to assess the agri-PV system plants energy generation performance in accordance with the International Energy Agency. So that is the description of a agri-voltaic system is given in point number two. Point number two. So all of you go through the figure. All of you go through the figure. So the figure number one, they have mentioned. So all of you note down the isometric view of a power plant. So they have mentioned. So that is the directions. That is north, south, east, west. So the reference distance is mentioned. So the height of the structure. So the PV panel. So the what is the depth. So there is, if you observe the figure number one, there is a gap is observed between the solar panels. Okay, let me observe that. 1, 2, 3, 4. So the four rows are there. Four rows are there. So I see the structure also. So that under the PV systems you can grow the plants. So there is isometric view of a zona guard region. So the tilting angle also mentioned in the paper. Majority of a solar radiation, the tilt angle of it, so that is fixed. Okay, so the tilt angle is normally so the 20.5 tilt angle, so which is equal to the latitude of a zona region. So that they have taken they have given the description of the agri-voltaic system also. So the experimentation purpose. This is the Department of Renewable Energy has considered for the assessment. So here the overall rating 7.2 kilowatt. So the spread across the area of so the 153 meters. So the agrivoltaic power plant was constructed so that the amount of shade that affects the crop is minimized and that is land is used for comparable to the traditional so the power plant design. So the meaning that the quality of energy produced per unit land is unchanged. To ensure that agri-PV systems get measured solar radiation and a tilt angle of a so the PV systems is fixed to 21.5. Okay, so the view now it has a as a researchers you can so the apply it. Okay, to get the optimum value. So it is possible to apply. So the genetic algorithm, next one is the TLBO. So you can produce the papers. Okay, so this tilting angle is so one of the important parameter. So in the agri-voltaic systems, so it is possible to implement so the how to maximize the output. Okay, so by adjusting your tilting angle. So the different if you see the literature, so the few optimization techniques are available. So but it is possible to implement use the genetic algorithm and so TLBO. So I published one paper related to the agri-voltaic systems based on so the genetic algorithm. So that is that way also you can do the you can produce the papers. So that I think next one is figure number two, schematic diagram also. So the SVPV power plant is given. So you can understand the PV systems. So this PV figure number two. All of you go to the figure number two. So the schematic diagram of a so the power plant output. So here we know. So that is PV systems will get so the DC output. So we need so the electrical output is all the loads are okay. All the loads are basically AC loads. So the if you see in our house, the fan is AC load and light is AC load, and all these are AC loads. Okay, so but here the power output of a PV system is a DC. So therefore there is a need to convert so the DC to AC. So that's why we need so the inverter. So inverter function is basically so to convert the DC to AC. So that is a so the converter or inverter is required. So the Ravindra sir in the first day, so the sir explained the different types of inverters used for agri-voltaic systems. So the these are one component of a agri PV systems. That's why so we included the so the inverters concept in the this particular FDP. So that is a so here so the every if you take anything any agri-voltaic PV system, that is a controller is required. So the here the daytime power is generated. So the is suppose the excess power is available. So that is stored in the so the battery pack. So the battery pack the DC voltage is stored. So that can be utilized for so it is possible to convert the energy stored in the battery is converted to the so the load AC load. So by using the inverter. So that is the schematic diagram of a so the power plant power plant mentioned in this so the paper. Next we will see the methodology. So the methodology performance analysis of the agri PV systems. So the specifications of a solar panels are listed in the table number 1. So the, all of you see the table number 1. They have mentioned so all the specifications at table number 1. So there you can see the specifications of a solar photovoltaic there. So the PV module specification and the type of material. So that is a polycrystalline material. The maximum power so the 150. So the open circuited voltage is mentioned 22.3. Short circuit current the 8.82. The maximum power voltage 18.83. The maximum power current 8.2. The number of cells in the module. So the 36 numbers. So the modules and CPU cells. So the beautifully explained by the Dr. D. Ravindra sir. So the if you want, if you have any doubt, so the refer the slides. I already sent the slide to group. So the all of you go through that. So the PV cells and modules are mentioned here. So that is the number of cells. That is 4 into 9. That is 36 numbers. So the module dimensions also given in the mm. So the 70 and 35. Okay, so these are specifications they have studied. So then they produce the this is the so the specifications of a solar PV model they have taken. Okay, so this is experimental study. So we can also they take the same R. So the for our applications you can select the so the PV systems specifications you can get the. So the next one is the results. So next point is the results. So the all of you see the specifications once again. The results and discussions are monthly total energy generated from agriculture. So monthly basis they have studied. They have given the so the analysis. So the solar modules transformation, solar radiation they collected into the usable power. Okay, all of you see that. Solar module transformation, the solar radiation they collected into the usable power. The total amount of energy produced was expressed in the kilowatt hour because energy unit is kilowatt hour. So the figure number 3. So the figure number 3 collected the monthly energy output for the experimental period. That is a monthly basis they have given in the so the energy produced during the experimental period. So the experimental period they have observed this agri PV systems 1 year. So all of you go through the uh, figure number 3, and also so the what are the performance parameters of agri power plant. So the Sandeep sir explained the different parameters, the performance indices. So they also mentioned the table number 2. So the table number 2 and the table number the figure number 3. So I will show you. So they are the different performance indicators. So the agri PV systems. So that is total energy generated by PV system. That is the first parameter. So the final yield. So the next one is reference yield. So these are equation. So the for every parameter the equation is given. So the next one is a reference yield, performance ratio, PR ratio, then it's a capacity factor. So the system efficiency. Okay, so by using, so these are the important formulas related to agri PV systems. Okay, so all of you, so this table is important to analyze the agri PV systems. So the next see the what is our monthly base, so power generation, monthly base power generation. So they have taken starting from January. So the to December they have given the values. So these are January, February, March, April, May, June, July, August, September, October, November, December. So the, if you see the May, okay, so the May, so the power generation is more. You know, so the why the power generation is more, because the May month, so the that is a summer. So the that is a, so the, it is possible to generate the more power. Okay, so that's why you are getting that is a monthly the May month they have power generation is more. Okay, so that is the thing. So the next, if you observe the graph, so the July month I think so the 89. Next one is August also 575. So this each one is August. Okay, each one is August. So the from the graph you can see the power generation in the monthly base. So the next one is these performance indices mentioned, and the monthly energy generation for the different months of a agri stations are plotted. This figure number 3. So next we will see the final yield and the reference yield for the different months of a year. So that is a 4.2. All of you go move to 4.2. There they mentioned. So the final yield and the reference yield for the different months. Okay, I will show you. Okay, so this is the figure number 4, the final yield and the reference yield for the different months. So they have given two bar charts. So the first one is yield, final yield. So the next one is reference yield, two colors. So all of you try to observe. So the two final yield and reference yield. So the figure number 4, figure number 4. So the main objective of this paper is the performance ratio. Okay, so the performance ratio. So the next graph is that is a performance ratio graph. So the see the here also the ratio for the different months. So the x-axis they have taken, so the month January, February, March, April, May up to December. Then they have indicated the performance ratio. So the all of you try to observe the value. So the highest value is February 0.87. So the all of you try to, so the write a comment on so the why we are getting February month we are getting 0.87 performance ratio. Okay, so that is that you have to study and write in the review article review report. Next, the performance efficiency also they have calculated. Efficiency also they have calculated. Efficiency also they have calculated. The efficiency also calculated with respect to the different months. So I will show you. So this is the efficiency. So again, the February month efficiency. So the next one is December. Okay, so the if you see the efficiency, the February month is more 14.09. So you have tried the reason for this system efficiency for the different months, and then they have concluded the paper. They have concluded the paper. So this is actually that is experimental results. So the number of papers also less in this work. So finally they concluded the conclusion.
So the Department of Renewable Energy Engineering at JIU Junagadh build and install the experimental SPV power plant with a design 7.2 kilowatt capacity that covers an area of 53.86 meters. The total energy output during the experimental period was obtained as a, so the value is given. Daily energy output was observed higher in the month of May. Already we have output, we have seen the graphs. Okay, the same thing they have written here. The energy output. You have to write the conclusion in such a way that with respect to the graphs, with respect to the graph. During the monsoon season, the month of July, August, September, and October, the energy generation is found was found lower other months. So the overall performance ratio during the experimentation period was observed was 80%. Overall system efficiency during the experimental period, that is a 1 year period, was found to be 12.07%. So this agrivoltaic technology is making a significant difference for the future energy needs in India, where the solar energy is available all the round. So these are conclusion. So the similarly, we are able to write the papers, or we are able to do the experimentation. So for the small area, so it is possible to do the for duration of 1 year for your region. Your region take the, so the crop, different crops. So the like that you can produce the papers. So these are article. So the discussion paper number 2. So this paper is published in so International Journal of Environment and Climate Change in the year, so the 2023. So that is this paper is completed now. So now how to write some how to submit. So that is a summary report. Okay, summary report. So the typical one I will show you. So the based on that you can write. So the all of you try to identify the key findings. So the here what are the performance matrices? Okay, so performance matrices. So the here the performance matrix average system efficiency. Okay, system efficiency is mentioned. That is the figure number 6. Efficiency is mentioned. So you can write the performance matrices. So the capacity factor mentioned, like a performance ratio. Okay, these three factors are mentioned. So therefore all of you move to the there is a equations also. Equations are given in this paper. So the more than three performance indices they have mentioned. So finally they have given. So they compared the three performance indices. Okay, so that is important point. So the next one is the energy output. Okay, energy output. So what is the total energy generated over the experimentation period? So the 1 year, how much energy is generated? Okay, so that is also we have to mention. Now this potential of agri PV system generating the significant power output under the various field conditions. Okay, you have to write that point also. Next, agrivoltaic potential. Potential Indian scenario, the study. So this paper concluded the performance indices in the agrivoltaic settings is comparable to the conventional PV systems. So then agrivoltaic system will produce solar power while maintaining the land use for the agriculture. So in this way you can write what is the strength of this paper. So the high efficiency, system efficiency is 80% is recommendable, showing the effective, so the energy capacity and conservation. The field observations. So they observed the 1 year long. So the monitoring they monitored the so the agri PV systems reliability and accuracy of the data reflecting the real world conditions. So in this way you can write. I will show you. So the thing. Next one is dual use. So we are generating the power as well as we are generating the power as well as we are producing the different crops. So there is a, so we can get the revenue for two sides. So therefore the farmer income will be increased. Okay, so that is the main advantage of agri PV systems. Okay, agri PV systems. So what are the implications of agri PV systems? The results agri PV can achieve the satisfactory performance
write the points. In that direction, you have to write the points. So the most important point is you have to include the future research. Future research. Okay, so that point also you have to include in the article discussion. In the article discussion. So all of you go through that. So the next I will see the I will show you the report. I will show you the report. So let me open report. How to submit the report. Okay, first write the title of FDP and our name. So the next one is our college name or institution name. The next title of article discussion. So here the case study on power generation from agri-voltaic systems in India. You have to mention that. So because we have discussed the many papers. Okay, so that's why we have write the title case study on power generation from the agri-voltaic systems. The next one is write the introduction. Okay, so this is a case study. So the experimentation. So the write some points related to the included in the introduction. So the next one is here are three parameters. Three parameters. So the if you see the graphs, you can write the performance indices easily. So the PR is a one parameter. PR is a one parameter. So that is a performance ratio. Okay, performance ratio is a one parameter. So the next one is a capacity factor. Okay, so the capacity factor. So in the paper they have mentioned the values. Okay, you have to include in the report also. So the capacity factor. So the capacity factor is the 16.03 and the performance ratio. Okay, so that's a 12.07. So you have to mention that. So the efficiency also efficiency is mentioned the 80.083%. So these are performance indices mentioned in the paper. So the next one is energy output. Okay, so here in the month of May, okay, energy output is more. Okay, you have to write a reason why output is more. So the total energy generated over the experimental period is, so they have mentioned the value. Okay, so they have under the specifications. So they have taken the specification based on that they have observed the 1 year. So based on that they have calculated the energy. The graphs you have, so in the paper it is available. So you have to mention that point. Also, don't copy from anywhere. Okay, you have to study the paper and observe all the graphs. Okay, so from that you can write the article discussion report. Okay, don't just I'm giving the model. Why I'm giving the model? I already told you. So there is most of the participants are new to the Atal FDP. So there is a difference between the normal FDP and Atal FDP. Atal FDP procedure is different. Okay, different means that so we have a article discussion. You have to write the exam. You have to give the feedback. So the next one is industrial visits like that. So that's why. So the normal faculty development program is will come 9 o'clock and will listen something will go. Okay, so now it is not like that. So it should be so it should be so they have to learn something from the. So that's why they are giving the funds to different organizations. That is the aim of a Atal faculty program. So the Atal aim is to enhance the knowledge of a so the research scholars, PG students and faculty. So that's why they have given the funding. Okay, to improve the skills. So just don't take it as a so the easy. Okay, you have to work. Okay, so that's why I'm explaining each and everything. So if you, so the participants who are juniors, okay, so take the help from the seniors and try to write the article discussion papers. So I think the almost all the participants submitted four article discussed so far. So we are conducting the faculty development program from 9 o'clock to 5 o'clock. So they don't have any time. So that's why in the accommodation rooms you can discuss with your seniors. So that try to get the knowledge. So that is a aim of a faculty development program. So these are the 2 weeks. So the means you have to learn something. At the end of the faculty development program, we have to, so that you can get the confidence. Yes, we learned something. Okay, like that we are planning all the sessions. Okay, not just like that. Okay, so we are giving lot of importance to giving the knowledge to the participants. Okay, so that's why we are discussing each and every point. So I think next one is you have to mention the energy output. Okay, so the all of you see the graphs. So from that you can get the information. So the next one is the potential of a agri PV systems in significance of a, so the fields agriculture. So I have write the output. So the key performances. So the Dr. V. Sandeep sir explained the many performance indices of a, so the agri PV systems. Here in this paper, only three performance indices are mentioned. That is average system efficiency, capacity factor, performance ratio. Okay, these three performance indices are so the discussed completely or experimented. So those practical results are presented in the article in this paper. Okay, so these are, so the one practical example. Okay, for doing the, so experimentation on agri PV systems. Okay, so that is a thing. So the now try to write. So that is the next point. The energy output. So the all of you see the graphs. From the graphs you can, so the write the, so the potential for agri voltaic systems. Potential. Okay, so the I collected the two points from, so the by studying the, so the this paper. So the PV system performance in the agrivoltaic settings is comparable to the conventional PV systems. So the next one is this viability of agrivoltaic systems to produce solar power while maintaining the land use for agriculture. Okay, so these are the, so the agri PV systems. Okay, potential. So the then next one is a critical discussion. Okay, how to add? It is possible. It is add. So the write in your own words. Don't copy it from other, but learn. Okay, so learn the things. So the up to this, all of you go through that. So then try to complete. Try to complete. So the if you have any doubt, take the help from seniors. Some seniors are here. Dear participants, write a critical discussion on this paper. Okay, so the 1 year they have studied. So that point also you have to mention. That point also you have to mention. So the next one is strength. You have to mention strength. They have calculated the efficiency and the field observations. So in the paper there is a graph. See how discussed the efficiency. So the average efficiency they have calculated system efficiency is 80.83%. So that is compared with the effective energy capture and conversion. So the next is the field observation. So the here they have observed 1 year. Okay, 1 year they observed. So based on that you can write 1 point. So this strength of agri PV systems. So the next one is you have to write challenges. Okay, what are the challenges of agri PV systems? So there is a low performance ratio while efficiency is high. PR of the agri PV systems is 12.07%. So the suggests a room for improvement in the design. So the system design operational factors such as so the shading, maintenance, and the inverter performance. So the first day, the Dr. D. Ravindra sir explained the inverters. Okay, different types of inverters. So he is an expert in designing the inverters. So therefore you can use the slides, go through the slides and identify what kind of inverters are used for agri PV systems. So the possible compare the existing inverters and so the how you are able to improve the performance so how to improve the performance ratio. Okay, so this field study states that only PR is 12.07%. So therefore there is a promise with the inverter. So therefore how to improve the inverter? Okay, so to increase the performance ratio. Okay, so that is a one challenge of the agri PV systems in the inverter side. Okay, so that is a 1 point. So next one is the capacity factor. The capacity factor as per 1 year observation, they included they include so the value that is 16.03%. So that is here also. So the what how to design. Okay, how the model orientation and tilt angle. So the tilt angle here I will give you one way of optimizing the tilt angle. Okay, so the here so that you can use so the different optimization techniques. Okay, so to maximize so that is a capacity factor with respect to the tilt angle. So the in the article research that is a paper, 2011 paper I have shown. So there they have discussed the definitions of agri PV systems and tilt angle, the terms related to agri PV system. Each and every definition is available in that paper. So all of you please try to download that paper and study the terminology used in agri PV systems. Okay, so here the tilt angle is very important in the design of agri PV systems. So the how to get the maximum capacity. So the what is the tilting angle. But they so this is one way of one challenge in the agri PV systems. So those challenges I have written the 2 points here. So if you study the total paper, then you can get the more points. Okay, what I feel I written for the purpose for explanation purpose. So if you feel some other factors, the major factors, the three factors are there. So that's why I included these values. Okay, so the system efficiency is somewhat better. The 80% is okay. So, but these two performance indices, that is a low performance ratio, that is a performance ratio and a capacity factor. These values in the paper they mention. So the 12% and 16%. That's why I have taken these 2 points. Okay, if you feel some other points, you can include in the report also. No problem. So that is a thing. So the next one is what are the implications of agri PV systems? Agri PV systems. What are the implications? So the agri you have to motivate. So the farmers, okay, so farmers, so the to main side they are so elite trades, okay, how to educate, we have to educate. So the main side in India, the agri PV systems are on the testing stage only. So that the practically there is no, so the PV agri PV systems, okay, so they are testing, okay, so the in the Gujarat state, so they have installed 1 acre land, they are testing. So the and also the Kerala state. So these are on the farmer land. So the installations of a PV systems are less in India. Okay, so that is a, so the implication, that is the implication. So that is a increased adoption of agri PV systems in the regions. So the in the regions of in the different conditions. So that is also you have to include in the report. Okay, how to in the report in the report. So the next you see the feature research. So the feature research, the comparative studies, okay, to assess the different so the system designs in the agrivoltaic contest. So the here research persons explained the different configurations. Okay, agri PV systems are different configurations, different crops, animals. Okay, with respect to the animals you can study, with respect to the crop you can study. Okay, so the with respect to the design system, so the PV systems are, that is a fixed rather than the fixed. So that is a that is a so the tilting. Okay, so the both sides are tilting and single side tilting, like that they have discussed the many point. So the how to improve, so the performance of agri PV systems. So that is another future directions to the agri PV systems. So the next one is so this point exploration of a crop compatibility with agri PV systems to maximize the land utility. So today's session, Dr. Sandeep sir explained. So the how to, okay, for already existing PV systems. So the how you are able to grow the crops. Okay, so to get the income from income. So that point is a very valid point. So the in that direction, so you can work. So there is exploration of a crop compatibility with the PV systems to maximize the land utility. Okay, these points I have written. If you have any other research directions, okay, you can include in the report also. Okay, so up to this, try to complete. So that if you have any doubt, okay, so ask me now, or any senior persons. Okay, some senior persons are available. So take the help from the senior persons. Try to complete the all the research article discussions reports. Okay, so that is mandatory. Okay, so this document is mandatory. Okay, so so to get the certificate, okay, you have to submit so the this document. Okay, article discussion papers and amendment. So if you have any doubt, I will come, I will discuss. Like that you have to complete all of you. So then at the end you can include the conclusion. So the here the paper discuss the main three parameters. So the about that they have to describe the so the here the type of system, there is a capacity 7.2. So the agri PV systems, that point you have to frame the proper in proper words. So you have to write the conclusion. Okay, so the finally, so this paper so experimental results are produced. So the three performance indices are so the discussed, and then so the specifications of a agri PV system, the specifications are given. So the like that you have to write the conclusion. Okay, so the that is the article discussion number 2. Okay, so I think so the today's two article discussions are completed. So the next one is next thing. So I will give the schedule. So then what you have discussed, what you have learned in this day. So these are that is the today's research research person Dr. V. Sandeep Garu taken the two sessions. So that is a session number 1. So the challenges and opportunities of a agri PV systems. So the topic in the topic are explained the many points related to faculty and so the research scholars how to do the how to produce the papers and how to guide the small projects to the students. So the what are the opportunities and the challenges in the agri PV systems. So the sir explained the very beautiful way. So that is session number 1. Session number 2. So the is about performance indicators of agri PV systems. So the SAR mentioned the many performance indices. So the in this and after that we discussed the two article research discussions. So the first paper that is a review paper, the current status of agri PV systems. Okay, so in this paper, so the from the definitions. Okay, so what is the agri PV definition? What are the different names used for agri PV systems? So that is the next one is so the worldwide where the agri PV systems are constructed are successful. So those things are mentioned in the paper. So the next one is so that there are two directions. Okay, so the two directions are table number 1, table number 2. Okay, all of you go through the so the research article number 1, table number 1, table number 2. So there lot of information. Okay, lot of papers are available. Okay, so all of you try to download all the papers. Okay, in the table number 1 and table number 2. Then you can so with the help of these two table number 1, table number 2. So you can write. You are able to write. Okay, review paper on agri PV systems. Okay, you can send it to the general paper or conference. Okay, so the some conferences so they are accepting the review papers also. So that is the article discussion paper. So the first paper current status of agri PV systems. So the second paper, so that is experimental result related. So that is Junagadh Agriculture University. So they tested the agri PV systems 1 year. So the finally they concluded the paper with 3 parameters. So they have given the challenges also. So the 2 parameters, so the PR, especially PR. So the PR is very low. Then there you can do so the lot of research work to improve the PR ratio. Okay, so that is a thing. So these are the activities completed today. So I will as a coordinator I will give them. So the what is tomorrow session. So that tomorrow we have 2 sessions with Dr. Pedapati Shankar Garu. So he will take 2 sessions and we have so the 2 article discussions. So that is a plan for tomorrow. So the all of you take all of you so that try to complete all the works. So that is we have sent so the feedback link. So that try to complete that. So the next one is a quiz. Okay, have sent the quiz also, quiz link also sent. So the try to complete that work. Next one is article, 2 article research report. Okay, article number 1. So the, all of you try to save your the article discussion reports with your roll number. Okay, so send to mail. Okay, so the send to mail. So if you send to my WhatsApp, it's very difficult to find. So the who are submitting like that. So that's why we have given the mail. We have created the mail for this particular FTP. So try to send all the PDFs to the particular that particular email, so that you can collect all the things. So all the things. If anybody is not submitted, then we definitely will ask you. So you will not get the certificate. I'm telling you. So that you have to complete to get the certificate. You have to complete all the task. Okay. So you have not after 5 o'clock. You have a some participants from the outside. Okay. So they are staying here only. So that is try to utilize this opportunity. Okay. So thank you. Today's session completed. Okay. So thank you all of you.